to be Matteo Monti, speaking about a long-track GeoSAR MIMO twin formation.
Thank you. Good morning, everyone. I'm Matteo Monti from Politecnico di Milano, and today I will present you our work about an long-track GeoSAR MIMO twin formation. Here is the outlook of the presentation. I'm starting from a brief introduction about the geostationary SAR and the mission concept and requirements for MIMO GeoSAR, together with the orbital configuration, both in terms of temporal baseline and normal baseline. Then I will present an analysis of performance comparison between a monostatic X-band GeoSAR and a MIMO Ku-band GeoSAR. At the end, I will present a preliminary long-track APS estimation and compensation algorithm for the geostationary SAR. Nowadays, low Earth orbit suffers from limited daily coverage with a revisit period in the order of 12 days for a single satellite. In GeoSAR instead enables persistent supercontinental observation with a maximum revisit period of 1 day. The near-zero inclination geostationary orbit allows for very long integration time from minutes to even hours. Thanks to that, it can compensate for path losses given by the huge distance, approximately 37,000 kilometers. And with this, you cannot require huge antennas and excessive power. But the long integration time makes the system highly sensitive to spatiotemporal variations, such as the atmospheric delay, both for troposphere and ionosphere. In GeoSAR, you can have very different orbital shapes depending on the orbital elements of your orbit. The most common is the high inclination orbit with the typical H-shape orbit. But in our work, we will concentrate on the near-zero inclination GeoSAR, which is characterized obviously by nearly zero values of eccentricity and inclination, regional coverage, and low relative orbit, lower relative velocities, which leads to very long integration time. This type of orbit, however, is governed by the ITU regulation, which sets the longitude slots from a minimum of plus or minus 0.1 degree to a maximum of plus or minus 0.5 degree with respect to the nominal longitude. The concept of our mission is to exploit a two-satellite GeoSAR MIMO formation in Ku-band that can provide a finer resolution with respect to X-band and C-band, but can face severe decorrelation and high power constraint. However, it presents several advantages. For example, you can increase the signal-to-noise ratio by a factor of 4, depending on the number of the satellite. You can guarantee a short revisit time and so high coherence, enabling multiple interferograms and solving decorrelation issues. It can also unlock highly coherent and continuous monitoring for near real-time change detection. Here are the requirements for our mission. So the satellite should remain between plus or minus 0.1 degree of its nominal longitude, as said before for the International Telecommunication Union regulation. The inter-satellite distance should always exceed 1 kilometer to avoid interference and collision between satellites. The normal baseline should not exceed 4 kilometers. And the integration time should be 1 hour in order to observe at every hour of our orbit a different area on ground. To achieve the 3 times spectral bandwidth and resolution, the temporal separation between the satellites should not exceed 2 hours, which is twice the integration time. Here I reported the selected orbital parameters of our orbit in order to satisfy the ITU requirements. And here on the left, you can see the ground track of the selected orbit together with the 2 satellites. On the center, instead, is represented the velocity throughout the orbit, the launch track, and relative with respect to a target on ground. And you can see the maximum velocity is approximately 5 meters per second in the correspondence of apogee and perigee. To satisfy the requirement of 1 kilometer, we need a minimum temporal baseline between the two satellites of 7 minutes. And you can see on the right the distance between the satellite throughout the orbit. And you can see that it oscillates between 1.1 kilometer and 2 kilometers, satisfying the requirement. For what regards the normal baseline, we analyzed two different targets on ground. The first one is the nominal ground target, located at 10 degrees of longitude and 33 degrees of latitude. And you can see that the normal baseline is practically zero, so you don't have the effect of the topography in this case. For the second analysis, we went targeting the extreme points in the European area, and you can see that the values are in every place are very low, with a maximum value of 1.5 kilometers, but always satisfying the requirement of a maximum of 4 kilometers of baseline. We are interested in the impact of the atmospheric phase screen on the generation of the image, and for both tropospheric and ionospheric turbulence. For the troposphere, we considered a joint time-space variogram model that is an extension of the Kolmogorov power law. And to validate this model, we performed we processed over 1 year of high-resolution meteo dataset using the weather research and forecasting model. For the ionosphere, instead, we consider a delay, that the delay can be efficiently modeled by a one-dimensional temporal variogram. And also in this case, we validated this model with a validation of 1 year of vertical total electron content maps from the NGV ESRA database. After that, we decided to compare the performances of a monostatic X-band geosar with a multistatic Ku-band geosar. Here I reported the parameters of this analysis. And you can see that in Ku-band, you have an impact of the ionosphere that is 10 times lower than the X-band. On the right, I reported the azimuth resolution of the two cases with respect to the velocity of the spacecraft along the orbit. And you can see that in Ku-band is almost half of the values in X-band, and a maximum azimuth resolution in Ku-band of 50 meters. By analyzing the monostatic X-band with a temporal baseline of 24 hours given by the characteristic temporal revisit of a geostationary SAR, we have a lot of decorrelation principally given by the temporal decorrelation of the scene that is a direct consequence of the 24-hour baseline. We have the effect of the topography because in this case we cannot consider the normal baseline negligible. We also consider the effect of the signal-to-noise ratio, in this case set as equal to 1 with a coherence of 0.5. In the case of the geostationary SAR, is important the effect of the atmosphere both during the integration time of the orbit and between the acquisition of the two satellites. In the case of the atmosphere inside the integration time, you have to consider both the combination of the temporal contribution given both by the troposphere and the ionosphere, while the spatial contribution only by the troposphere. Instead, between the two, the acquisition, I reported here the expression of the coherence, which depends on the temporal variogram of the atmospheric phase screen. And you can see that in this case, the effect completely decorrelates in 24 hours in X-band. For the monostatic Ku-band, instead, we consider the temporal baseline of 7 minutes found before. And in this case, we also have the temporal decorrelation, but the effect is lower due to the shorter temporal baseline. We don't have the effect of the topography because we demonstrated before that the normal baseline is almost negligible. Also in this case, we consider a signal-to-noise ratio equal to 1, and we evaluated the atmosphere intra-image and inter-images as in the previous case. And in this case, you can see that the results are way better than the first case. Another advantage is that you can exploit a shorter antenna and obtain the same performances as the X-band with an antenna. This is almost half of the length of the previous of the case of the X-band. We evaluated the interferometric phase accuracy, knowing that we have, in this case, have 3 interferograms, so we can increase the number of loops by a factor of 3. On the right, I reported the evaluation of the interferometric phase accuracy in 2 different cases. In the one case with only troposphere, and the second case with troposphere and ionosphere as a function of the velocity of the spacecraft and the average transmitted power. And you can see the difference in the results given by the high temporal variability of the ionosphere during the acquisition. So we decided to analyze and present a preliminary APS estimation and compensation algorithm based on the along-track interferometry. So starting from the 3 raw data of the images, so the raw data of the first image, the raw data of the second image, and the bistatic configuration, we divide the total integration time and total aperture in different smaller subaperture to obtain 3 sets of subimages. Then we compute the interferograms by combining all the different combinations between the subimages, and we perform a phase linking exploiting the redundancy between the acquisitions. And we can estimate the differential atmospheric phase screen with respect to the first image. And through an integration and interpolation strategy, we can then derive the absolute atmospheric phase screen. For our simulation, we assumed a monodimensional scene, and to consider the worst case scenario of estimation, we consider the minimum velocity of 1.8 meters per second. We also evaluated which is the optimal subaperture integration time to obtain the better performances. And we discovered that in the case of only troposphere, we have the values of the optimal integration time in the order of 10 and 9 minutes, while in the case of both troposphere and ionosphere, the value is almost half of the previous, with a value of 4 or 5 minutes. Here are the results, the preliminary results of our algorithm. In this case, with only tropospheric turbulence, both in coherence between full resolution images and interferometric phase accuracy. On the left is represented the generated by the simulation real atmospheric phase screen, and on the right the estimated one by our algorithm. And you can see by the results the improvement of the results given by our algorithm, both both in single look and multi-look for what regards the interferometric phase accuracy. When introducing the ionosphere, the algorithm still works, but we obtain worse results than the previous case. You can see the value, for example, the value of final coherence. But I would like to underline that this is the worst case scenario because we are considering the minimum velocity, and by increasing the velocity, you can obtain even better results than this. And another important aspect is that in the future, our idea is to mitigate this temporal impact of the ionosphere by exploiting external strategies, for example, by exploiting permanent scatterers. To conclude, a long-track GeoSAR combines wide coverage, fine resolution, and short revisit time. A compact KU band formation enhances power and revisit frequency. To satisfy the 1 kilometer minimum satellite distance, a temporal baseline of at least 7 minutes is required. The proposed close formation ensure almost negligible normal baseline, and the MIMO formation enables APS estimation without reference data, overcoming the 24-hour atmospheric decorrelation of a single satellite system. A preliminary subaperture along-track interferometry strategy has been proposed, and by the results demonstrate that an optimal subaperture integration time can be obtained that is different from the monostatic case, allowing effective APS compensation, in particular for the case of only tropospheric effects, even at the lowest velocity. Thank you for your attention.
All right, thank you, Matteo. Are there any questions? There's plenty of time for questions. Scott, right down here. Oh, sorry, you're so far away. Was there...
When you're estimating the atmosphere, you included the all three reference, secondary, and bistatic. What is the bistatic inclusion by you? Like, why does that improve the atmospheric estimation?
Because the most important impact of the atmosphere in the for the estimation is the distance, is the temporal distance between interferograms and how much time you have between two acquisitions. So for in a monostatic case, you need, for example, a reference image to estimate the atmosphere, for example. But using two satellites with a very small temporal distance between them, you can evaluate directly the variation in that time between the two satellite acquisition, and not relying, for example, of other external data. You can directly exploit it by the two satellites.
Thank you.
Okay, Michele, did you have a question? Oh, no. Giorgio.
How does the temporal variogram of the ionosphere look like?
I can go back. Here is the one on the bottom of the slides. We evaluated the variation of the ionosphere both spatially and temporally, and we analyzed a lot of value of vertical total electron content, and we found that at the mid latitudes, the spatial variation of the ionosphere is very, very low, almost negligible, while the dominant factor is the temporal one. So we performed a fitting evaluation, and we found very, very low fitting errors in the order of maximum 10% of fitting errors. So we decided to evaluate the ionospheric variogram as only a one-dimensional in temporal.
And if you would say how much it varies in time for, or in tech for certain time, can you give numbers, like a couple of TEC in a minute, or
the
parameters of the variogram?
It can vary in order of 1 TQ in few minutes. You have very few minutes. You can obtain a 1 TQ of variation. It's fast, very fast, the variation of.
within the minute is a slow variation within the minute, but
Sorry, the slow variation.
so you said it's fast. Okay, so you said fast because it's changes of 1 TEC within a minute, and then continues changing. But within the minute is low variation, or does it have also additional turbulence within this minute?
I don't think anybody
Yes.
knows.
Yes.
I don't think anybody knows. Okay, I think we need to move on. Thank you very much.
Thank you.
So then we welcome the next speaker, which is Andrea Monti-Guarneri, and he's talking about interferometric performance of a geostationary CERN.
Okay, thank you, Irena. Here is it. Okay, thank you very much. And I thank all my colleagues of Hydroterra Plus MAG, including Christian, who presented the concept of Hydroterra Plus. This is not a talk on Hydroterra Plus explicitly, but it is something more general about a geosynchronous SAR in C-band. So we already, so Matteo already presented this. You have a steering orbit. Steering orbit, the only position is very high from the Earth's surface. So it means that you have the opportunity to access a continental scale or over continental scale. You see 1/3 of the Earth from that point, and you access 1/3 in no time at all. Moreover, you image a huge swath. And in order to exploit this orbit, you need, of course, resolution, and you need an all-weather, all-time sensing system, that is a synthetic aperture radar does. And more than that, a synthetic aperture radar is sensitive to water variation for the microwave. So this is perfect for addressing the cycle of water in the air and in the snow and the force soil moisture. That is why we are considering the C-band and not, or L-band can be good, but not, as we'll see later, but X-band, of course not. And this is Christian talk of yesterday. So let's go to this is artist representation of the geostationary ring. All the geostationary satellites are there, and the ITU regulates the occupation box. As Matteo told us, you have a limit for experimental stations that is wider than the limit for commercial stations, that is 1 degree. So when you see the orbit, you will see this ellipse, basically in the horizontal domain, that is west test. West test is main azimuth direction, and the satellite is looking south-north or north-south, depending which hemisphere you want to look. And this total excursion, this azimuth excursion of 700 kilometers, you can decide to partition it in small blocks that are the colored block, and each color corresponds to a swath. A swath is 700 by 300 kilometers, so a very huge swath. And so you cycle the coverage over area of interest. And if you look at the color scale, every color, in this case for Hydroterra, is repeated 4 times every day. So you have 4 observations of all this area every day, and still you have 4 taskable swaths that are for other observation. And so you trade here spatial coverage and the resolution. Of course, in 1 hour, the resolution is not as good, but there is another trade-off that you can make. That is also the flexibility of a GeoSAR, in which you can collect echo all around 12 hours, but on 12 hours, only 10 are available for a synthetic aperture. And you can decide to make 4 azimuth resolution each, 4 azimuth subaperture, each of 15 minutes. The resolution is very bad, as you see, but it's good enough to estimate the atmospheric phase screen. So this is a monostatic concept, so it's different from Matteo. However, observing 40 times a moving object on the ground, of course, now you are staring only on 400 by 700 kilometers, something pretty interesting in 10 hours. You can decide to collate a subaperture and observe only 20 times, but now the resolution improves, and so on and so forth. So if you want to observe steering for all 10 hours, then you have only one observation, but you have 2 meter azimuth resolution. That is not that bad. Just to comment, the signal-to-noise ratio does not depend on this subdivision, because as when you increase observation times, the resolution gets finer. So you compensate these two factors. And the others that you can do on a single pixel by pixel basis. So as a SAR processor, you could imagine a scenario in which you can adapt your processes single scene and decide to have 40 observation at coarse resolution when the scene is moving, and what is stable, you can have a very good resolution. This is a dream for a SAR processor. Okay, and well, the product, the interferometry product, here we are at Fringe that are also backscatter, are all the products related to the cycle of water, and including also some product that relate to the fast deformation, so other change map and deformation. And you see on the right, this is a very nice zenith white delay that is integrated water vapor, that is very helpful in supporting forecast for intense storm, but not very useful for Sentinel, because you need this product, according to meteorologists, between 4 and 8 times a day, and now we have only one every 3 or 6 days. In fact, the revisit is this one. If you consider Sentinel-1 that and LUSAR that make one orbit in 100 minutes, then the coverage over world is pretty good, is what you can do. But if you consider the coverage only in Europe, for example, in 1 day, it's not that good. In 2 days, you have also the red strip. These are a little better. In 3 days, you still don't have the full coverage of Europe. In fact, if you have the constellation of 2 satellites, you need 3 days to cover the mid-latitude. Of course, at the north and south, the coverage is pretty dense, but in Europe is not so much. Of course, you have Sentinel-NG, as Julia presented yesterday, that is improved so much. You will have maybe the daily coverage, but not the sub-daily. And here we are, because our area of interest, for example, for Europe, is Mediterranean, because Mediterranean is an hotspot, as a big pool of water, very, very big in mid-latitude, is subject to contrast in the temperature between the cold Atlantic and the very super hot East Asia. And so you see how much this is hit by the climate and will be it in the future. So it's where agriculture and so soil moisture, it's where snow means water for the summer season are to be monitored and to use for forecasting system. And Volta Basin is another area that is interest, because it's hit by severe storm. And the point is that now we go to performance part. Can a GeoSAR observe European Union? I use European Union, so let us theoretically assume we want to monitor the European Union, that is 4.2 million square kilometers, only once a day. Of course, we have one satellite and our capability are limited. So once it means, or twice a day, because we have in 10 days, we have 20 subaperture of 1 hour, 300 by 700 kilometers. So we have the 4 million kilometers. But we have a lot of problem with the spread loss, because we have a huge distance, this 37,000 kilometers, and you see spread loss is account for 65 dB more than LUSAR. So is that good or not? We can compensate with an extended integration time, so this is 1 hour. 1 hour limit our coverage, of course, but here we assume the same power of Sentinel-1 in order to say the same technology. We have a little bigger antenna that can be done. This is duo in Earth Explorer, for example, and we should account for the coarse resolution of the level 1 product, not for the level 2. The level 1 is coarse resolution than Sentinel, And in the end, we cannot hope to have that good signal-to-noise ratio of Sentinel because the nests lose again 4 dB. Then with this constraint, let us go to the evaluation of performance. So this is a processing from the level 1 to the level 2 product. And the core for the sensitivity is a complex multi-looking because there you make the phase accuracy. So if you evaluate the phase accuracy, the phase standard deviation with the Kramer-Rao bound, you see this depends on coherence and depends on the number of look. The number of look basically is the ratio between the level 2 products that depend on geophysics. The requirement may be 1 kilometer, for example. Here we assume 1 kilometer, that is for meteorologists, but you can use other number. And the level 1 that is different from the GEO and the LEO. Of course, the LEO is much better. And then you have coherence. And as for coherence, you have topographic decorrelation. This already Matteo told us the story. So we need to dimension the baseline to have this at a very low level. So you want a high elevation of ambiguity. And then you have the noise-related decorrelation. And we estimate this thanks to the noise equivalence sigma naught. And we can take advantage of the C-band mosaic. This is one of Alaska SAR facilities that is very helpful. And this is not the only decorrelation effect because you have also the atmospheric phase screen. So Matteo already talked about this. Yes, we have model in literature. This decorrelation now depends on the velocity. You see, this is why we try to apply for the widest dot available in the ITU. Nonetheless, we want to check the number in literature, so that is why we process the WRF dataset. We fitted the estimated variogram to, you see, 200,000 variogram, and the fitting error, yes, is good, is less than 10% in most of the case. And then we see coherence. Coherence on the right says that coherence means the variation due to the part of the turbulent atmosphere that you cannot estimate and compensate. So the very, very fast component that move far faster than 15 minutes. And you see coherence is 0.9. We assume this to be the normal atmosphere, but we consider that for forecasting in 10.7, we assume a very strong atmosphere in which coherence goes to 0.5, basically. So we have these two level of seal. The 100 millimeter is the one that everyone also in yesterday's section, you see 1 centimeter is the value that we apply. And then we go to temporal decorrelation. This is unavoidable in Sentinel, is unavoidable in geosynchronous, but of course, you can estimate thanks, for example, again to Alaska SAR facility. This is a unique opportunity to use a Z model, that is a temporal decorrelation model, in which Alaska SAR facility has mapped both the infinite decorrelation and the decorrelation time on a scale of 1 kilometer. So the one you reconstruct on the left is, on my right, is the Sentinel coherence in 6 days, but you can also apply to coherence in different days. And you see from 6 to 3 to, from 12 to 6 to 3 days, how much the temporal coherence improve. In fact, this is a predicted coherence for a GeoSAR when you put together all the effects, and you have a lot of gain due to the fact that you have this one-day revisit. Of course, in the stable area, it's not as good as Sentinel, but you see, this is an important graph in the center because the histogram tells us that as the system has been designed, the topographic, so the variation of target in the resolution cell, and the APS, the atmospheric turbulence, are more or less at the same level, and this is the same level of the spatial, the temporal decorrelation that is due to the 1 day, and of course the C-band. In L-band, you will have a less unbalancing of this. And this gives you a very pretty good coherence that is 0.4, it goes to 0.2 only if you consider a very strong atmospheric component. And with this design, then you get the standard deviation of the accuracy for the GeoSAR and for the Sentinel. Of course, now the lower value, the better. And you see that the GeoSAR is average very uniform. Because it balances the thermal noise contribution with the temporal decorrelation, whereas in Sentinel, of course, when the scene is very stable, so Sentinel is an Earth global observation system, so it's made to estimate the stable component. So in the desert, the accuracy of Sentinel is pretty good, and you see also in the histogram. But you can tell that for the GeoSAR, in both normal and turbulent atmosphere, the range of standard deviation is within the range of Sentinel. And this ensures that the quality of the product that you generate by a geosynchronous system is not different, not so much different from the quality that you already experience with Sentinel. And all the users are very happy with the present quality of Sentinel. So what I'm asking is, I should have this product 4 times a day, not 1 time every 4 days. And so this is just the last before the conclusion. I mean, Sentinel and GeoSAR are not competitive, are really complementary system. In fact, Sentinel is a very, very good system. We all experience the quality, particularly the noise equivalent sigma naught, and we like the fact that it is worldwide coverage. But if it is worldwide, then you accept that you have to take a long time to make a revisit, to make a stack. And so this is perfect for the stable component of the Earth. But when you address the fast-changing component of the Earth, now we are proposing a change of paradigm that is not only to go to the GeoSAR, but you see the GeoOrbit is providing this, in which you have this balancing, so a perfect complementary with Sentinel. And I can say, coming to the conclusion, that what are the basic findings? First of all, if you want a persistent point of view to image huge SWOT, for the small SWOT you can have a dense constellation, but these dense constellations are mostly in X-band. We don't need the X-band for the soil moisture, and are for local observation of very high resolution. So here resolution is coarse, and the GeoOrbit is unique. And this has a problem because there's a huge spread loss, but we have shown that a careful design can eventually balance all the components together. And in this, the choice of the C-band seems a very good choice. And so if you like this concept, I think you have to attend the UCM, in which Hydroterra will be evaluated as a competitor, as a possible candidate Earth Explorer mission. And finally, this is not written here, but there is another level of complementary, because I think in the future the LEO orbit will be very, very crowded. And so making a small satellite, this could be a very good idea, because you can also, you have less risk, let us say. But if you make a very big satellite, the risk increase and will increase in the future. So I think that playing for the GeoOrbit is much higher regulated, because of course it's a very precious orbit. And so thinking to put a synthetic aperture radar in diversifying the orbit could be also a de-risking for the future of Earth observation. So thank you.
Yeah, thank you, Andrea, for this very comprehensive overview, and we wish you all the luck, right? For
Okay, thank
in
you.
2 weeks, you said, right? Is
Yeah,
it?
3 weeks.
It's
yes,
three
yes,
in 3
yes,
weeks'
yes.
time. Okay, we'll see how it works. Okay, some questions to the presentation. Yes.
Yes,
In
Michael.
front. Would you like to have my one? She's coming. Yeah.
Okay.
You mentioned you're dealing with very small signals, and radio interference could be a problem. How far are you away from thermal emission of the Earth? I mean, compared to the...
I mean, you're right. It's a problem, maybe. And in fact, when we applied for the C-band, there is another reason for which we did, because in order to do this, you must have an idea of what is the radio frequency experiment population. And we have an opportunity because you know that Sentinel has this TOPS mode. In this TOPS mode, for a small portion of the time, but it's significant to sample the acquisitions, the system is only listening. So there are some pulses that have not been reflected by the ground, and still the system is on. For some serendipitous application. We are measuring this since many years because basically we are able to make a map of radio frequency interferences and the evolution. This is also a radiometer. We also calibrated it with other radiometer, but it's not so useful a radiometer. But so this is a way we address radio frequency interference. So if you ask now what's happening in radio frequency interferences, in the present time, it's very different from 6 years ago, okay? Because you have a very, very strong and very, but I hope this will not the time of the future when this satellite will work. And by the measure we are doing, however, we evaluate, of course, you see more, and you have more radio frequency interference. But you are far from the Earth, so also the radio frequency interference are attenuated. So we consider 850 degrees of total noise temperature instead of 800, that what you see in the table. This can be a rough comparison, as evaluation has been done by ARESIS by using Sentinel constellation measure.
But I didn't get it. What's the Earth's surface temperature? Does it play a role? Or is it just the system noise?
It's overall, I think. But if you, it's nice because with Sentinel, if you look at these pulses, you really see the temperature of, you have a radiometer. You see the variation with sea, ice, earth, and of course, sometimes you have the spot of interference. Of course, there is a limit. Sentinel observe at 6 and 6, and on dawn dusk, not all the day, but it's what we can do now.
Okay, great. Yeah, thanks. I think we need to proceed now. Sorry,
Okay.
no questions anymore. Okay, hand over.
Okay. Thank you. The next speaker is Michele Manunta. He'll be speaking about Nimbus.
Okay, good morning, everyone, and thank you, Paul, for the introduction. So, as my title suggests, I'm going to talk about a new X-band SAR mission. It's the Nimbus SAR mission, and in particular, my talk is focused on the interferometry performance of the Nimbus SAR mission. So, Nimbus SAR is part of a large Italian Earth observation program, the IRIDE program. IRIDE will be completed in 2028 and is managed by ESA with the support of the Italian Space Agency. Within IRIDE, we have more than 60 satellites. Not only SAR, of course, we have optical, hyperspectral, multispectral systems that will be grouped in 6 main constellations. One of these constellations is the Nimbus SAR mission. The overarching goal of IRIDE is to deploy, to design and implement 8 different advanced services that will serve 8 different communities. In this work for the Nimbus mission, I will focus on the ground motion service in particular, but of course Nimbus will serve not only ground motion but also the other services. Okay, now let's move to see the main parameters of the Nimbus SAR constellation. We are talking about an X-band constellation. We will have 12 satellites that will be grouped in 2 different batches, so 6 + 6 satellites. The orbital tube of the constellation is quite good. We are around 500 meters and 3 sigma. The constellation has the capability to acquire in left and in left and right looking mode. The imaging capability are quite good. We are talking about small satellites, so the range SWOT is around 30 kilometers. This is an average number because the SWOT will change beam by beam, but an average number is 30 kilometers, and the spatial resolution is around 3 meters. So in this work, the aim was to design the best or a good solution for the orbital design in order to guarantee the whole Italian coverage by preserving, of course, the high resolution capability of the system and reducing as much as possible the interferometric revisit time. To give you an idea of the problem that we tackle, here we have the sun-synchronous coverage. If we launch the constellation in sun-synchronous orbits, assuming a 6 days revisit time. As you can see, in 6 days, we are not able to cover Italy. We need 12, but better 18 days to have a full coverage of Italy. An effective way to overcome this limitation is the exploitation of mid-inclination orbits. You know that mid-inclination orbits are not largely used in Earth observation initiative because these orbits do not allow us to perform global coverage acquisition plans. However, when the focus of the mission is a mid-latitude area, as the case of Italy, we can benefit from the capability of the mid-inclination orbit to reduce the inter-track distance when we are very close to the northern part. So in this case, we can benefit from a large number of passes over Italy because if we select properly the maximum latitude that is covered by the satellite. So here we have a solution that we found is based on a right-looking observation, and the inclination of the orbit is 49 degrees. In this case, we have a 6 days interferometric revisit time. So in 6 days, we are able, with this orbital configuration, to have a full coverage of Italy. In the slide, we have the comparison with the equivalent orbital design with the sun-synchronous orbit. To be honest, there are very small areas, in particular in the southern Italy, that are not covered in this plan. However, there are some additional beams that are available in southern Italy that we can exploit to have, let me say, 100% of coverage. Here we have the same exercise, but with the descending passes. Also in this case, we have full coverage of Italy, except for a strip over Sicily that will be covered by exploiting additional beam available in southern Italy. So, once we understood that this orbital configuration, this inclined orbital configuration is suitable for full coverage, we investigated the INSAR performance. So in particular, we investigated the impact of mid-inclination orbits in the main INSAR parameters. And we start our investigation from the critical perpendicular baseline. Here you have the mathematical expression that we use to estimate this parameter. Let's move to see the number that we retrieve, and we analyze two different scenarios. First of all, we assume the orbital tube as parameter, so 500 meters. In this case, we retrieve that around 95% of the points have critical baseline larger than 500 meters. But if we wanted to be a bit more conservative, so we wanted to analyze a real scenario, so we can assume 3 times the orbital tube, so 1.5 kilometers, we see that we are around 85% of the points. To give you a comparison, we estimated that the same parameter for Cosmos SkyMed, that is an X-band mission, and we found exactly the same numbers. So this means that we don't have a negative impact of mid-inclination orbit on the critical perpendicular baseline. Then we estimated the impact on the geometric distortion of the inclination of the orbits. Also in this case, we don't have a negative impact. You can see that the shadow is not a problem at all. Less than 0.1% of the points are impacted by shadow, but also layover distortion are not an issue. Less than 4% of the points are impacted by layover. To be honest, we have, let me say, a small issue, in particular in the northern part of Italy, because now we are talking not on sun-synchronous orbits, but when we have an inclined orbit and we move in the higher latitude of the investigated area, there we don't have the two passes, so ascending and descending, but we have only one pass that is moving from west to east. So here, also there, we have only one pass, so we are losing the double view of ascending and descending. So we, let me say that we have only a partial acquisition of this area. In order to overcome this limitation, we decided to launch the second batch of Nimbus in another inclined orbit, but with the left-looking acquisition mode and an inclination of the orbit a bit different, 43, 44 degrees. In this case, in the northern Italy, we have two acquisitions, left and right looking, in order to guarantee the double view, of the system. Of course, in the rest of Italy, we have 4 acquisitions for each area by benefiting from ascending, descending, left and right looking. Okay, the INSAR performance are good, but when interferometric guys think about inclined orbits, the first idea is which is the sensitivity to the north-south, because let me say, a benefit from inclination of the orbit is the capability to estimate the north-south component. In this slide, I show you the impact of the north-south of the deformation component in the line of sight. And you can see that more or less 40% of the north-south deformation components is projected in the line of sight direction. Of course, we have a variation of the sensibility from south to north Italy. And to give you, again, a comparison with SSO, this number is around or less than 10%. So when benefiting from the inclination of the orbit, we have the sensitivity to estimate the north-south. The methodologies, the results of this work has been published on TGRS paper, recently published. Of course, I cannot show you any analysis with real data, because the Nimbus mission will be launched in December 26, so in the next 6 months. We are a bit excited and finger crossed when talking about launch on new satellite, but we are confident, or ESA is confident to have the system in orbit at the end of the year. But in order to carry out an analysis on the impact and the quality of the mid-inclination orbit for interferometric application, we benefited from the availability of Capella space constellation. In this case, we perform an experimental acquisition campaign over Campi Flegrei Caldera. It is an active volcano in Italy, in Naples. In this case, we acquired 4 different data sets between mid-July and mid-December 2025, so more or less 5 months. Here you have the footprint of the area that has been acquired, and then there is also the table of the with the parameters of the system. We use the Capella 13 satellite. The acquisition parameters are quite similar to Nimbus, so we are talking about an X-band system. The spatial resolution in this case is very, very good, less than 1 meter, but the range SWOT is around 10 kilometers. And the revisit time is 3 days, or the nominal revisit time is 3 days, because when we use mid-inclination orbits, we have a drift of the acquisition local time, so the correct revisit time is 2.95 days. However, okay, we acquired 4 data sets. Here you have the details, more or less 200 images, so 50 images for each data set. Here, I want to focus on two of these datasets because you can see that the look angle of this dataset is very, very small, 16 and 22 degrees. You know better than me that when we have interferometric application, often the angles so small are not the best. So we have the amplification of the layover effects that reduce our capability to map the area. However, these are the data set that we got, and we're working with this. Let me just say that during the acquisition campaign, an earthquake occurred in the area, is the yellow star in the map. So we work and we live there, so it's not a good event when an earthquake occurs. But from the interferometric point of view, this was a good possibility to test the capability of the system to analyze not only, let me say, continuous movement, but also a jump, a single event movement. So it's been a good possibility for us. So let's move to the results. Here we have the 4 mean deformation velocity maps that we retrieve by processing the 4 dataset with the small baseline subset. I wanted to focus on two of this dataset, the 44 degrees and the 16 degrees of look angle. You can see as in the 44 we have, let me say, almost a full map of the area, but in the 16 degrees we completely lost this area because this area is in layover in the 16, so we are not able to completely map this part of the area. And this area is where the earthquake occurred in September 25. So by combining the 4 results, the line of sight results, we retrieve the 3 components of the deformation from left, north, south, east, west, and vertical. The results are perfectly in agreement with independent analysis over the caldera. And benefiting from the GNSS network managed by INGV, we evaluate, we assess the quality of the time series, so GNSS in red and SAR in black. You can see we exploited only 3 stations because this comparison has been performed just 10 days ago before EUSAR, so it's very recent. You can see that we were able to estimate the jump relevant to the earthquake, in particular in the Akai station. And in general, the agreement is very, very good. The standard deviation is around just a few millimeters. We have just small errors relevant or related to the atmospheric filtering of the line of sight. So, last but not least, in order to squeeze the information that we have or we can get from this analysis, in this case, we integrated Cosmos Chimes and Synchronous with two Capella datasets. And in this case, we analyze, okay, I'm going to the conclusion. We analyze only the earthquake, and so not the time series. And here we have the line of sight results. In this case, we have deformation maps, not velocity maps. You can see that now in these results, the coverage is very, very good because we are not using the 16 look angle data set. And inverting these 3 deformation maps, we retrieve the east-west, vertical, north-south component relevant to the earthquake that occurred in September. So let me say that I'm confident, we are confident that with Nimbus we will be able to do very, very good interferometry application. So Paul told me that I'm a bit long, so these are my conclusion. I can jump to be shorter. Thank you.
Very nice. So you're going to launch Nimbus later this year. Is that what you said?
Yeah,
okay.
December.
Wow. Great.
The first batch. The second batch, I think it's around February.
Fantastic. All right. Any questions? We do have time for one or two questions. I'll ask a question. So you're focusing on Italy, I guess, in terms of optimizing performance, but what's the duty cycle for these satellites for other places in the world?
Okay, the mission has been designed. The aim is the background mission is Italy. Italy will use more or less 20-25% of the orbits. Outside Italy, the planning is on demand, but the system is a dual mission, so civil and defense. So the high priority in general is for defense and intelligence. But however, there is the on-demand possibility for commercial and scientific use. What we are asking to the Italian Space Agency is, however, to cover the other areas in the world benefited from the inclination, if not high priority requests are available, so to exploit the satellites. Let me say that we are talking about small satellites, so the duty cycle is around 2 minutes, so 120 seconds, so this is a limitation. Also, but in general, the system will be available also for commercial scientific exploitation.
Great, thank you.
Thank you, Paul.
Okay, we'll move on to the next talk then.
Okay, yeah, the next talk will be given by Scott Staniewski from Capella Space, and he will talk about operational high cadence, mid-inclination X-band INSAR from Capella constellations, 2 years of displacement monitoring results.
Thank you. So I get the privilege of presenting a lot of work where I have come into Capella about 7 months ago, and so almost all of the hard work and preparation has been done over many years by many people. So Craig has been the director of radar. Gordon has also been at Capella since the beginning. Ron came from JPL and about a month after me. Martin has been in charge of orbit control, and Shaunak has done everything at Capella. And so we've also had Davide and others lead up the beginning of the INSAR. We've had a lot of people work on the INSAR for a while. So just a background of Capella, we have a constellation of small satellites. The first INSAR design was done back in 2017. We had first opportunistic collects around 2020, and so they kicked off the INSAR project in 2022 to start planning what they would sell and how they would advertise and market INSAR specifically. In 2024, we had our first mid-inclination repeat ground track orbit working. And finally, last month, we've announced for the first time that you can task your own INSAR on our console, as well as we put our first polar orbit in SSO. So now we have 2 repeat ground track orbits going. Some of the design parameters. So this is for the 53-degree mid-inclination. Capella 13, so we just named them with a number. So C13 is the satellite in mid-inclination. The top is the expected coherence, and bottom is colored by number of revisits you can do per day. So all these satellites are pretty nimble, that you can look left, look right, depending on what you task. And so combining that with ascending and descending towards the higher latitudes, you can see that you get up to 4 revisits per day. And so you can revisit these mid-latitude areas many times in the 3-day cycle. We have a up to 600 megahertz bandwidth, which is around 25 centimeter range resolution. The azimuth, depending on the dwell time, you can get down to 5 centimeter. Nominally, it can be for strip map about centimeter 1.2 meters for strip map resolution. And you can have a large incidence variation as well, with a swath width of up to around 10 kilometers. And Michele was showing some of the mid-inclination results and designs that we have. So this is just to acquaint you with what mid-inclination looks like versus polar. You have these tilted orbits, so at any given point, rather than something that's north-south, ascending, descending, you get more of a diamond shape. So on the right is the yellow is the satellite track, and then those triangles are the zero Doppler plane. So rather than something looking east-west and you get up-down, here you get kind of a mix, and that gives you some north-south sensitivity. The other difference from a large Sentinel NISAR mission is that we don't have a planned acquisition campaign to try and cover as much area as possible. We have customers that ask for images in certain areas, and for INSAR, we've planned our own to kind of show and demonstrate a bunch of varieties of environments and applications that you might do. So at this point, we've done several hundred campaigns of INSAR, ranging from pairs of images over cool areas to stacks of 150, approaching 200 images since about early 2025. We'll walk through some of these soon. And as Michele was saying, the other unique thing about our 3-day repeat is it's actually 2.95 day repeat. And so if you have a stack of images over, this is downtown Mexico City, if you just plot the amplitudes over time, you can see variations that will happen as you walk backwards about an hour each day. And so if you're looking at the roads here, you can actually see that at the 1 a.m. local time, you're not going to see cars. And at rush hour, you have a completely different look for the streets because it's a packed in traffic jam. So that's a funny example, but that is a example of the kind of interday variability you could see if you wanted that. In some cases, it's a nuisance, but in other cases, like glacier monitoring, people are really wanting to see this variability in time of day. One of the big satellite performance things we needed to hit to start reliably getting INSAR is the orbit control. So our GNC team had been working for a while. As we've had about 4 generations of satellites. The thrusters have gotten better, and our automatic orbit control has gotten better, so that now we have stacks of data that for about a year and a half have quite good perpendicular baseline and orbital control. So we aim for about 500-meter tube, but occasionally we do fall out, but that was about a year ago. And so you saw previously that we have stacks of data where it's nice to have some perpendicular baseline when you want to estimate heights from a PSI reconstruction, but we often hit well under the critical baseline, which, if you remember, that higher resolution means a larger critical baseline. So some of the geometries we have like tens of kilometers of critical baseline, meaning these 200 perpendicular baseline are very high coherence. The other practical operation thing that we had was better orbit estimation. So everyone is used to Sentinel having 3-centimeter precise orbits all the time, and that is possible for a number of reasons, but one is that they have the planned acquisition, so they're not slewing all the time. We have that giant reflector that kind of acts like a sail in the wind, and so the drag can be hard to estimate. And when Ron came on, he actually, in his first month, wrote a procedure to take long arcs of orbit data and re-estimate after to get a much more reliable orbit estimation, more on the order of like 10 to 50 centimeter precision. And so before that, when we had precise orbit jobs fail, and sometimes you try to make an interferogram and it would look like this, where the up-down is azimuth, and so you'd have these crazy phase ramps. And then after running the new orbit estimation, then you get actually usable interferograms. So the acquisition data was not wrong, but simply our orbit estimation was bad, and now it's become much better. And it's in fact good enough that nobody else at Capella really cares about geocoded SLCs, but I like them. So I wanted to see if it was possible, and this is a stack over Rosamond that I tried just forming a stack of geocoded co-registered SLCs where you correct for the topographic phase and then immediately geocode them. And we actually get coherence. This was fun to see. I didn't expect this, and I don't actually expect many of our customers to use geocoded SLCs, but this was a good test of how good our orbit estimation was. And then recently I also checked, we have a stack of about 150 over Rosamond in both spotlight mode and a different strip map collection. And so this was a geolocation analysis from the corner reflectors over Rosamond. And I should have scaled them properly, but we have about 2x worse in azimuth as range, but
the standard deviations for our estimations of the corner reflections was about 25 centimeters in range and 50 centimeters in azimuth. But you can also just look at the interferograms that we can make. And so for that strip map acquisition, the first 3-day repeat, 2.95 days, is the top, and it's just extremely high coherence. And on the right, as you see, the middle of lake bed occasionally floods, and so after a couple months, a lot of it is decorrelated at some point. So that correlation plot where you have the sharp drop, that is just a point in the lake bed that it stays coherent until one day it doesn't, and then it has decorrelated. But even after about 450 days, the bottom, there's a lot of coherence in the area around the lake bed that's still dry desert. And so I'm going to walk through some of the campaigns that I've processed. I haven't set up all of these for tasking because, as I've said, they've been tasking and having campaigns going since mid-2024, but I had a lot of time series processing code that was very fun to work with all of these data. So one, just to get acquainted with what the X-band interferograms look like, this is a strip map. It can go anywhere from 5 kilometers wide, or you can process it to be 10 kilometers wide. Each wrap is about 1.5 centimeters. And so this is a 2-month interferogram in the oil fields in California, where there's not too much atmosphere here, and so you can see the very strong signal that all the satellites see of the oil extraction right in the middle with the nice concentric fringes. To give an idea of how big these are versus Sentinel, this is the main reason why the constellations of small sats are not really the same product as a Sentinel NISAR mission, because one image covers this much for Sentinel, and the spotlight data for Capella is that tiny red box. So this is looking at South Florida. The red box is centered over Miami Beach. But the reason you may like and want to use these small sat high resolution data is the urban area for Sentinel-1 looks something like this when you zoom all the way into the red box. So you can kind of see the buildings and see the outlines of the dark water. But if you look at the Capella data, then you can actually see all of the objects. That blue direction is showing which way the satellite was looking. And so if you haven't seen these high-resolution, high-rise images, it can be disorienting, but all of the buildings are leaning towards the satellite. And so this one is the Miami Porsche Tower that is about 200 meters, and it leans way into the water. So it's kind of interesting to process these data. And you really need to account for the DEM error, but if you take a stack of images, and so here I processed about 60 of this stack over Miami, you can get very cool 3D height reconstructions after getting the DEM error and the density of the point cloud that you get from lining it up after you kind of unlay over the data is very cool when laid upon Google Earth. Another example of why it was nice to have 3-day repeat and kind of agile tasking was over the volcano Piton de la Vernaz in Réunion. So this is one where at certain points they've had automated tasking, like a tip and queue system for disasters or certain events that you want to immediately look at. Since we don't have global coverage, earthquakes are harder because it's hard to get a before image of everywhere on Earth that may have an earthquake. But something like a volcano has precursors. And so in this case, the tip was our colleagues at IPGP sent an email with urgent in the subject line that said, a volcano might go off, can you start tasking? And so then I did, and then within a day we had the first collects, and we happened to catch one of the eruptions. So there were 2 eruptions, one in January, or 2 large deformation events over this area. And we had 3 different acquisition geometries to make sure we covered it. This one is from early February of a dike intrusion, and the coherence shows the lava flow quite nicely, and we got new images every 2.95 days, and so you can see the evolution of the lava. After seeing Brian's talk yesterday, it was a very cool visualization of showing it color-coded by when there's a coherence drop, and so this actually looks nice that the green, as it gets redder, that's later in the time, so the green is the first long lava flow that happened, and then yellow, it expanded, and red, it expanded further. We also, the first campaign that I started when I joined to figure out how to task our satellites was I knew the landslide at Palos Verdes was still moving. This is something that in 2024 was the subject of a lot of study, and Al Handwerger and Eric Fielding and others have studied this landslide a lot. So it had a lot of attention in 2024 as it was causing some serious destruction when it accelerated to about 10 centimeters per day. This was way too fast for Sentinel-1 to capture, and so they tasked UAVSAR. It would be great if UAVSAR could fly everywhere all the time, so that's kind of the gold standard of like L-band, very high resolution, can repeat at will. But we were also able to task, and so if you can picture this having an acceleration event that within a day or so we could start collecting INSAR images. And so we have now a stack of about 60 images or 50 images over this area. I tasked at spotlight mode, so it's 25 to 50 centimeter resolution. The geometry is, it's an ascending left-looking acquisition collect here. And here we have about close to a meter of line of sight deformation on average. And this looks nice, and the extra good thing about this area is that Al has collected a lot of the GPS data, and so this is one of the few areas where in a tiny 5 by 5 kilometer, we have dense GPS comparisons. And the INSAR nearly captures all of the data. I was actually surprised how well it agreed because I knew this area is moving very fast. It doesn't quite capture the slope, but if you use pixel offset tracking instead, and so here on the left we have the range offsets, and on the right is the azimuth offsets, we get the full trend because this is like sub-meter resolution, and so there's a lot of redundancy available for the pixel offset tracking to capture the full motion. Just to illustrate the problem with Sentinel for these very fast-moving landslides is that it does give you an indication, and so you see on the left is the average velocity for about the same year time period. I extended it back a little further into 2025. But the course resolution and the 12-day revisit means you do get a bunch of aliasing, and so it's hard to capture the very fast-moving part of the landslide. But it still shows you the signal, and so Sentinel does provide the early warning system of this is an area of interest which you may want to look at with higher resolution data. A few other cool examples. One, this is from Stacy Huang that we've been working with her, and she has been doing studies for the Surface Deformation and Change mission, so SDC, that she was seeing, can you use these very long dwelling spotlight data collects and estimate the troposphere and the deformation simultaneously? And so we did some custom processing for her of making images at the beginning in the forward squint, zero Doppler squint, and backward squint. And so she created interferograms from the three geometries, combined them, and her paper is in review and coming out soon, but she was able to add some regularization to get a good estimation of the along track, the range, as well as the atmospheric solution. So that was very cool to see. And then we have a bunch of other analytics partners who have shown very cool things with their data. Michele just showed the great results over Campi Flegrei. We have 3VG, who's one of the first people to compare our results over a mining site to the TerraSAR X simultaneous collect, and they compared us favorably, we'll say. And one of the early INSAR good orbit control data that we had was over Mexico City, and so Gamma had a nice write-up for us. That's one of our most popular blogs, where they showed a small slice of the deformation of Mexico City. So if you're interested in trying out the data, we did a contest, an IEEE data fusion contest. We were the sponsors, and so we dumped a lot of data on the open data catalog, and it, 10x'd in size. And so now there's a couple ways you can browse it. One, it's a stack catalog, and so there's a felt.com website that you can browse around. If you're also interested in just the INSAR ones, you can ask me. I have a few other ways to visualize the campaigns, because stack isn't, it's easy to crawl but hard to search for INSAR. I also added on public GitHub a simple Python reader to help parse the metadata. It has an ICE3 integration, so some of my processing was actually just wrappers around ICE3 for the co-registration and the early SAR processing, and then you can directly hook up with our Python reader. But we also, if you use Gamma, since they had that study, Gamma definitely works with Capella, and many of the commercial SAR processing softwares do work with Capella. So yeah, looking forward to seeing what people can do with the data, and come talk to me after if you're interested.
Thanks a lot to give this overview. I mean, it's a lot of different applications that you're targeting in the moment. It's great, so really good to see. And also the spatial resolution, very impressive images, I would say. I'm really impressed about it. So this is what you can do when you do more commercial stuff, right?
Yes.
But yeah, looking globally also, I mean, Sentinel data are great, actually,
Yes.
to combine both and to see more. Are there some questions? Yeah, here below.
Thank you. So impressive resolution. With that, you can see the traffic condition that other free data cannot usually see. Does Capella Space work on any traffic condition related product? You show 1 a.m. versus 3 p.m. I guess you have to consider Doppler shift. Empty road is not actually, may not be actually empty, but off the road. The cars show up in off the road. But you have a lot of stack of like reference data you can potentially use to track them.
That's a very interesting idea. We don't have a traffic condition product right now. As far as I know, I haven't seen somebody try to do that. I just wanted to see what the visualization looked like, and so that was kind of my first and only attempt at that. But that somebody doing that may want. So we have about 8 satellites in orbit right now. ICEYE has many more, which aren't yet in a repeat exact ground track, but that may be something that a like amplitude change detection product would be able to catch.
Thank you.
I think if there are not more questions or some questions, no, I don't see it. Okay, again, then thanks again, Scott.
Speaker. Okay, our final talk for the session is on MDA Chorus, and it will be given by Jin Beck.
Good morning, everyone. I'm Jin from MDA Space in Canada, working as a geospatial analyst at MDA. Today, I'd like to talk about the advanced INSAR algorithm for 3D deformation monitoring with MDA Chorus mission. So I'm gonna start my presentation with the overview, and then I will move on to introduction to our MDA satellites, and then I will briefly talk about our 3D INSAR workflow, and then 3D deformation simulation for testing, and our satellite beam optimization algorithm. And then I will present my test result with the different deformation types, and then I will finish up my presentation with the conclusion and any other applications that we can do with the Chorus mission. I think many of you already know that we can do the 3D INSAR monitoring with the mid-inclined orbiting SAR satellites. But for those of you who wants to know what Chorus can do and why and how we do the 3D INSAR monitoring, I have this overview slide for the better understanding. So most of the currently available synthetic star aperture radar satellite, like a Sentinel or RadarSat-2, they operate in the near polar synchronous orbit. And then those satellites can provide the line of sight measurement, which are very sensitive to the vertical or up-down and the east-west displacement because of its orbiting system. And then they don't have a sensitivity to the north-south component of the surface deformation. So those 1D or 2D analysis can introduce substantial bias when the north-south component of the surface deformation is not negligible at all. And 3D components of the surface displacement can be obtained by at least 3 stacks of the non-coplanar LOS measurement with the different viewing geometries of a star satellite. So CURS, our next mission, supports both left and right-looking imaging system with a mid-inclined orbit and a wide range of instance angles to choose from. And CURS, this mid-inclined orbit, can also provide the improved sensitivity to the north-south component of the displacement. And it can also provide precise 3D INSAR measurement with its highly controlled orbit path. So in this presentation, I'm going to talk about the LOS surface displacement simulation for my testing using CURS and radar set 2 imaging geometry. And then I will also present the 3D deformation decomposition test result using the combination of CURS and radar set 2 satellites. And this is a list of our STAR satellites. We have radar set 2, which is currently in operation with good health. And it is C-band STAR satellite with a fine resolution of 3 by 1 meter. And it has a 24 days of repeat cycle. And our course is scheduled to be launched at the end of this year. So hopefully we can expect to get the first data set around early next year. And it is also C-band satellite, but it has a little tiny tailing satellite after C-band satellite. So it takes the X-band image 1 hour after the C-band satellite takes the image for the same area. And it also has a fine resolution of 3 by 1 meter. And it has a 9.85 day of revisit time, which is shorter than the radar set 2. And the radar set 2 has a polar orbit like that, so it can do 1D or 2D INSAR. So we need at least 2 stacks of satellite images from radar set 2 to do the 2D INSAR. And it's going to give us deformation measurement every 24 days. And it's going to be shorter if we combine more image stacks. And CURS is orbiting in that way with the side-looking system. So it's going to allow us to do the 3D INSAR with at least 3 stacks of images. So we need at least 1 stack of the image from CURS for the 3D INSAR. And then we'll get the deformation measurement every 9.85 day with a single track. And it's going to be shorter than that if we combine more image stacks. This is a simple illustration of our 3D INSAR workflow. Because we don't have the CURS images available yet, so we had to simulate the CURS and radar set 2 images for the 3D INSAR testing. So in order to do that, we first simulated 3D surface deformation in up, down, east, west, and the north, south direction. And then we also have an algorithm for selecting the best beam combination for the specific area that we are looking at. So we implemented the beam optimization to select the 3 beams, so 2 CURS and 1 radar set. So using this information, I simulated the LOS deformation image stacks for the cumulative deformation retrieval. So we have 2 stacks of LOS deformation images from 2 CURS beam mode and 1 stack of LOS deformation images from the radar set 2. Then we ran our 3D INSAR algorithm to get the cumulative up, down, east, west, and north, south deformation component. Then we created the deformation map and the time series profile for the analysis, and we validated our result with the expected deformation that we just simulated. So let's talk a little bit about the 3D deformation simulation. So we use a simple deformation model to simulate the 3D ground surface deformation. So this is going to be our 2 deformation for the validation. So the images at the top rows are our 3D deformation simulated along all directions. So in the last image, you can see that this example shows the ground subsidence with the red color in vertical direction. And you can also see the north-south and the east-west deformation that's moving towards the middle of the image with the subsidence. And in using this simulated deformation, we also projected this deformation into the LOS of the selected satellite beam modes. For example, the first image at the bottom is this subsidence projected onto the LOS of radar set 2 beam mode. And the rest of 2 images are the same deformation in the LOS of 2 cross beam mode. And then we need to simulate the stack of LOS deformation images as an input to the 3D INSAR. So those LOS deformation image stacks were generated using the simulated 3D deformation, which I just showed you in the previous slide. So we assumed 2 different deformation types for the 2 test cases. And then we also simulated the typical SAR noises like a decorrelation and the atmosphere. And then those noises were added to the deformation signal for more realistic test scenarios. Then we generated a stack of first and second sequential interferograms or LOS deformation images. For example, for radar set 2 stack, we have a 24 and the 48-day interferograms as an input simulated. And the images at the bottom are just an example of the simulated LOS deformation image stack. So the first one is one of sequential LOS deformation images from the first course. The next one is another example of sequential pair from the second course. And the last one is another sequential pair from the radar set 2, so with the time interval of 24 days. So you can see more amount of subsidence in the radar set 2 simulated image because of its longer time period. So our input images for the 3D INSAR were affected by this much of the noises. Like you see, like we have a random noises here and there from the atmosphere. And then we also have a decorrelation noise for every single pixel in the input images. And this kind of like a 2D, 3D decomposition involves the inversion of the ill-posed the system, because our input images are from the individual satellite tracks, and then they're kind of creating the disconnected subsets in time. And especially for the 3D decomposition, we also had to add one more unknown parameter to be solved, which is the north-south component of the displacement. So this addition is gonna make our inversion problem more ill-posed. So all these issues were like solved by our 3D algorithm by using the regularization. So by using the regularization, we were able to mitigate the noise as well as handling this ill-posedness of the inversion problem. And we can also optionally apply the additional weighting to the input images so that we can get more robust and reliable measurements. And this is a list of satellite beam mode which I selected for this test. So we have the optimization algorithm to select the best beam combination for the specific area. So I chose actually 2 cross and 1 radar set, but for that area I chose for testing, I have a best beam combination of 4 cross stacks, but I chose this combination because I wanted to investigate my algorithm performance when we have a radar set 2 images in the input data. So we have 2 curves with ascending right looking and descending left looking, and then 1 radar set 2 with the descending right looking, which doesn't have a sensitivity to north-south component. And we've been testing this algorithm for many different kind of test scenarios. So one of the examples was to compare the test result from the optimal beam combination and suboptimal beam combination that was presented at the Tailings Conference in March this year at South Africa. So in short summary, the suboptimal beam combination shows a very noisy measurement, cumulative measurement from the 3D INSAR algorithm because of the wrong selection of the beam combinations. So that presentation was highlighting the importance of selecting the best beam combination for your site. And I've set up 2 test cases. So both test cases were sharing the same monitoring period of 1-year period from 2024 to 2025. And I assume this area was located at minus 27.8 latitude. And then the first test scenario was assuming the linear subsidence. So we're going to see the maximum subsidence on the last date of the monitoring period. And the second test case was assuming the non-linear. So it has like a Gaussian shape of the deformation behavior over time. So we were going to see the maximum uplift in the middle of the monitoring period. So this is the 3D insert result for the linear deformation. So it's 3 images on the top are the expected deformation that we just simulated. And then images in the middle, they are our result from 3D insert. So you can see that we were able to recover the deformation component from all directions pretty well. And the images at the bottom are just residual, simply the difference between the expected and decomposed deformation. So you can see the residual maps are showing only the noises, not capturing any portion of the deformation signals. We also calculated RMSE for each direction. We have a pretty lower RMSE for the vertical and east-west direction, but we have a slightly higher RMSE for north-south direction, which is expected because we used the one stack from the radar set 2, which doesn't have the sensitivity to north-south. Then we also did the temporal analysis with the time series plots. So this is a vertical deformation for the point location in the middle of the image where we see the maximum subsidence. The gray line is the expected deformation, which is kind of answer. And the red line is our decomposed result for the vertical directions. You can see nice alignment between them. And this is the east-west component. So you can also see that the temporal behavior is pretty much similar to what we expect, although I see a slight shift between these 2 lines around the end of this monitoring period. And this is north-south component for this linear deformation, which you can see the good alignment between them with a slight shift in the middle of the period. And this is test 2 result with non-linear deformation. Again, our decomposed measurement in the middle row are pretty much similar to what we can expect. And the RMSE for the north-south is slightly higher than the RMSE for the up-down and east-west direction. And the residual doesn't show any portion of deformation, which is good. And then time series for the vertical for this test case, you can see this Gaussian-shaped nonlinear deformation along the vertical direction is well captured by our 3D insert algorithm in the middle of the image. And this is the east-west component. So we were able to get the east-west component of the deformation as well. But I see the measurements around like the beginning and the end of monitoring period are a little bit fluctuating at this point. And this is north-south component at the point where we see the deformation towards north. So you can also see that our the measurement from the 3D insert was able to recover this component, but I see a little bit of underestimation at the maximum deformation date. And I also see a little bit of a fluctuation in the measurement around the beginning and the end of a monitoring period. But overall, the temporal behavior is pretty much similar to what we expect. So in conclusion, so our cross mission can provide the north-south component of deformation with the mid-inclination orbit. And our 3D insert algorithm can combine different beams like radar set 2, CUROS, and even Sentinel-1 and other SAR satellites. And it can mitigate the noise to get the best 3D component of various types of surface deformation. And our data optimization algorithm can also offer the best beam mode for your application. And this is the last slide for the additional applications that we can do with the course mission. For example, we can do the maritime surveillance like vessel detection and tracking, and disaster response and environmental monitoring, and then geospatial analytics. So feel free to reach out to me. I have an email address over there if you have any comments or question about our 3D install or course mission after this conference. And you're welcome to visit our official website for more information about the course mission. So thank you for your attention.
Questions? Dirk?
Thank you very much for the talk. Just a quick question. How agile will course be in terms of changing from right to left looking mode? Can you do it from ascending to descending, or how much time do you need in order to change the look direction?
To changing the imaging mode at the satellite?
No, from left to right or
Yeah,
vice
well,
versa?
I don't have a specific number for that because it's more like a technical question for the satellite team. But well, yeah, we have ability to change the switch the beam mode like left right looking, but I don't have the specific number for the time taking.
But it's a mechanical, it's a roll.
Yeah, it is
it's
mechanically.
a roll, so it takes
it's
time,
possible.
so it needs, you cannot just quickly change. Okay.
But we have so that is actually planned by the user's order. So we can like previously like design those switching mode based on the order from the customers and then our priority. So that's going to be planned ahead of the imaging acquisition time.
Yeah, okay, thanks.
Michele, here.
Oh, thank you for the presentation. Very interesting. My question is about the acquisition plan. Are you planning to have a background mission or to systematically acquire some areas, or the system will be only on demand?
So acquisition planning is based on the order. So this is order-based acquisition. So whoever has a plan to have an image for the specific area for the certain time or period, that's going to take the high priority. So we won't be able to image the other area while the satellite is taking the image of that specific area. But if you don't have that kind of order in advance, then we will do whatever we can do for the rest of the areas.
Okay, I think there are no more questions. So then we can conclude this session, and we thank all the speakers and also the audience being active with us, and enjoy your coffee break.
presenta lei? Sì. Penso di sì. Questo me lo sono letto, questo è un essay. Poi abbiamo... Ah, è questo. Ah, è lui. Irene, aspetta. Perché anche questo è un lavoro sì, con due costellazioni, perché c'è Strix e Isai, e questo è il così. Anche questa, ecco quella lì, questo è Otmar, sì. Ok. Mancava quello. Allora, come facciamo? Quando iniziamo? Adesso sì. Presentiamo alternativamente? Sì, uno e uno, così è lo stesso. Chi vuole introdurre la sessione? Working. Do you hear me? Yes. Okay. Good second part of the morning, and I think people are coming here, but we are nearly to start. And just to introduce myself, I'm Andrea Montiguarnieri of Polytechnic of Milano, and my colleague.
Yeah, Andrea Manconi from WSL SLF in Switzerland.
Okay, as for this session, we have it's a new system. We have a really spaceborne system, but also ground system, and we have also applications. So it's a very diversified session. And for the first talk, I would like the first talk is about ISI constellation, and I would like to introduce Valentin Tolpekin, who will present a SAR interferometry with a proliferated daily ground track microsatellite constellation.
Thank you, Mr. Chairman. Can you hear me? So I'm Valentin Tolpekin. I'm presenting this work on behalf of ISI INSAR team and, of course, entire ISI engineering team. That's the structure of my talk. I'm going to talk about how new space small satellite constellation differs from old space. And I'm going to provide some examples of INSAR modalities of ISI and to talk about our improved ground track repeat orbit. So ISI constellation is more than 70 satellites at the moment. I lost the count, honestly. And we offer frequent revisit. We offer fine resolution. We do it, it's a new space. We innovate, develop and iterate fast. So we produced four generations of satellites. And that's our plans for launching more. Not all of them are in a ground track repeat. So not all of them are ready for INSAR. So what's the value of this microsatellite constellation? A high revisit actually helps you when you are looking at a fast deformation, and longer period induces decorrelation. And here I'm showing examples of grounding line produced by UC Irvine team. They're presenting 2 talks today. And on the right, you see an interferogram, 1-day interval. That's fast-moving glaciers in Greenland. So you see correlation is quite high. On the background is a DEM we produced from formation flying in pursuit monostatic, but I'm not going to talk about it today. So another advantage is very high spatial resolution. Basically, it says what it is. When details matter, you can track finest details. And on the lower left is a coherence from famous Natalie Meremy story, when a farmer drove a truck to propose to his fiancée, and that was a success story. But you need coherence to see that from space. So what are the challenges of microsatellites? The first and the biggest, I think, is orbit stability and baseline control. We started this in 2021, and our first generation GTR orbit was not ideal. What you can see here is a wide orbital tube. You see one case of anomaly, where we jumped out of the tube and returned. So day-to-day baselines might be short, but there are long correlated pieces of data where data is not independent, and you run into troubles in PSI analysis when you try to uncouple the variables. So once you collect this orbit for a long enough time, you need a couple of full periods of that oscillations, then you can do something. Then the second challenge is a tasking-oriented system. There are no archive. We are not collecting all the time. So if you want to ensure there is a stack, you need to task it. So that's a change of paradigm for stakeholders. You need to make sure data is collected. Otherwise, the chance of finding something suitable is very low. And finally, co-registration complexity. The high resolution, the longer baselines, and not ideal geolocation accuracy pose problems, and the software should be up to it. I want to start with a CCD example. This is one-day interval coherence, and it shows how coherence changes over a field. So red means something was coherent and turned incoherent on the next day, and blue is the opposite. It was incoherent, but it turned coherent. There is some agricultural activity, and that's what happens next day. You actually see where the tractor was moving, and day after, activity changed, but we can track in very fine detail where and what has changed. Of course, it's not a commercial product, it's just, and not scientific, I think, but it's a nice illustration. Next, you can do differential in SAR. We cooperate with Icelandic Met Office. They have ongoing series of eruptions in the Reykjanes Peninsula, and we observe deformation. So there were a number of eruption cycles. I actually don't recall how many in total, and I think we covered all but one with ISA interferograms. So here's an example of interferogram month before the eruption. You can actually see some residual topography from old eruption lava that became new terrain, but the DEM doesn't know that yet. We used Copernicus DEM. Then day before an eruption event. And this is just a few moments before or during the eruption event. So you can observe deformation, dike formation, and there is a low coherence area. It's not lava yet, it's just the displacement is too large. And we can capture some of it with residual pixel offsets from the co-registration. We are missing some here. I was wondering what's going on. I think we were too restrictive in reporting thresholds, but something to check. But still, we have a clear signal. And the units are pixels. We can do amplitude change detection and see, well, something is changing clearly, but it's not very clear. With coherence change detection, so before the event, it is coherent. Then we see coherence is lost. There is new lava pouring. And then we can actually see what's changing over time. And we can see even fine details where how lava progresses over time. It's very hard to see that from amplitude. So now the most challenging application for INSAR is a PSI, where we need long stacks and nice orbit control. I'll show the generation 1. By the way, it's my naming for this presentation. It's nothing formal, but that's what we had. And I show some examples what we could achieve with those stacks. So here you see a spot or spotlight mode, subsidence examples. You can see critical baseline in red. And you can see when stack is long enough, we can actually do PSI. Oh, sorry, I didn't say. There was unstable slope in open pit mine, and you all know famous Mosul Dam sinkholes. But we need a long stack for that. A bit more challenging example is subsidence monitoring due to subway tunnel construction in Sao Paulo, Brazil. We had more problems with orbit control, as you can see, but we could actually see the subsidence. Upon closer inspection, we could see it's nonlinear, but here we only present a deformation rate. And we could also see that construction was happening in segments. It was not from beginning to the end or vice versa. It was happening in segments, and it was confirmed by local contexts. So now, what can we do with the new generation GTR? We changed the hardware. It's much more reliable. We improved our software, and we still need to improve it further. You can see the last example, we have some anomalies. And of course, they happened just before Fringe. So the example we wanted to present is actually the worst case scenario with the new generation orbit control. So not all our satellites are in GTR. We currently count 6 in daily GTR orbit. We are planning to move more. We have 1 satellite in 12-day GTR, more as an experiment to see how it works. And yeah, still anomalies. But we wanted to look what we can do with those. And that's a Sao Paulo case revisited. So different geometry and different time. Construction ended a year ago. So what we could see is only some residual settlement of the surface. And that's basically where the metro station was built. Here you see a bit lower density of the points. We selected at first only the most stable point. But what was important is for comparable stack duration with a new generation orbit, we got higher amplitude stability, we got higher temporal coherence. We could do 3D analysis of that data, and in fact, it was much better than Gen 1. We could go all the way up to the tallest building here, but we missed the top at 150 meters. We have some suspects. We currently think it's focusing. So when we focus on image far from the terrain, from the DEM, we have some defocusing in range which we are going to improve. And that's a very short example of a mining case. It's not a shining example. We just wanted to see what we can do with a very short stack. And in fact, amplitude stability is high. We have some signal where we expect to see deformation and residual height, but of course, longer stack will confirm. That's what I wanted to present. I want to highlight that we started providing open data with a permissive license, which is a big difference compared to the past license system. So if you are interested, please follow our portal. We have 1 GTR stack currently. We are planning to add more. And if you are interested, please talk to us. Thank you.
Thank you, Valentin, for your talk. Are there questions about this? Yes, please.
Thank you. Hey, Valentin, great talk. One kind of stimulating question is you can look at the baseline drag as a problem, or you can look at it differently, and you can look at it as a feature. And especially like from the industry perspective and in the mining vertical, it could be really nice for generating rapid DEM products, right? As the mine progresses, you can quickly generate residual height estimates and get some interesting product out of that. So we can look into that.
I totally agree with you. And I think if we deviate from this narrow orbit for tens of kilometers, it's not nice, of course. But even when orbit control is ideal, we considered to have this jump introduced just to improve sensitivity to height artificially. Yeah, so totally valid point.
Thanks. Are other questions? Well, I have a question. Since here is Fringe's symposium, we are all interested in interferometry. And we also know that ISI is also a commercial-driven company. So how much of the market is pushing toward interferometry or in the other direction?
That's an excellent question. And from what I understand, it doesn't. The market froze and doesn't know what to do with one-day interferometry. I mean, there are nice scientific applications. There are change detection applications, which are at the moment most prominent market force. But I think we need to actually talk with you, with academic community, to find good application cases. This is a new capability. With one-day repeat everywhere, you can do a lot of stuff. So let's find it.
So just to complement this question, as change detection with a short revisit, I think is totally different with long temporal revisit, because with long you have so many changes. But this could be a killer application. What is your opinion about this coherent change detection opportunity for the market in the future?
Coherent change detection is very popular now. It's a absolutely top hot topic. Yeah, and even with a volcanic deformation, if you can see what happened, let's say within 12 days, you can see every day what happened and what deformation didn't happen at a certain day. Right? So this is a new superpower.
Thank you very much. If there are not questions, thank you for your talk again.
Thank you, Valentin. We introduce now the second speaker is Yu Morishita. So he's going to present high frequency, high resolution ground displacement measurement using the Strix constellation. Thank you.
Yeah, thank you. I'm Yu Morishita from Synspective, Japan. Today I will talk about our recent achievements using our own Strix data. So first, let me introduce our Strix constellation. So we, Synspective, has been developing our own X-band small cell satellite called Strix. So the bus size is very small, only 1 meter, and the antenna length is 5 meters, and the weight is only 100 kilograms plus. We have launched 9 satellites so far, and we will launch 4 more satellites this year. And actually tonight we will launch 10 satellites from New Zealand. And next year we will launch 12 satellites, and around 2028 we will achieve more than 30 satellite constellation, which enables us to observe a specific area every hour, which is very high frequency. And regarding the INSAR capability, it is currently limited. It's only opportunistic and experimental, but yeah, we are improving the INSAR capability, and we aim to achieve the operational INSAR capability around 2028. And yeah, STRIX satellite has 3 observation modes: strip map, sliding spotlight, and steering spotlight. And one of the characteristics of small satellite is its high resolution mode. And in our case, we can achieve 0.25 meter resolution at highest. And another unique point of small satellite constellation is its orbit type. So we have both SSO and MIO. So in SSO, sun-synchronous orbit, the satellite can reach to the high latitude region, and we can get global coverage. And in our case, STRIX has the one-day repeat orbit. And yeah, in MIO, mid-inclination orbit, the satellite cannot reach the high latitude region, but the benefit of MIO is the frequent revisit in mid-latitude region. And also, INSAR can, by using INSAR, MIO can get north-south sensitivity, which cannot be obtained from SSO. And yeah, by combining these two different orbit type and ascending, descending, left and right looking, we can have such various observation geometry. So today I would like to show 3 case studies using our own STRIX data. So first one is corner reflector based validation of millimeter level INSAR accuracy. So we placed 5 corner reflectors in Tsukuba, Japan. And yeah, we manually moved 2 of them, these ones, up and down by 1 to 2 millimeters several times. And we measured the height by leveling. And we also acquired images using STRIX for satellite in MIO with highest resolution mode. And yeah, we collected 11 images in December last year, and with nearly 1-day repeat interval. The baseline range was 1.2 kilometers, which is significantly smaller than the critical baseline. And I conducted the time series analysis using this dataset. And yeah, this is the result. And the left figure shows the PS points. And yeah, we can see many PS points around the corner reflectors. And the left figure is the time series result and from INSAR and leveling. So we can see they are very consistent each other, and the standard deviation of the difference is less than 0.5 millimeters. So this demonstrates that our STRIX INSAR can achieve less than 1 millimeter accuracy. Yes, so next let's move on to the second case study, high resolution pixel offset time series analysis. Yes, this table shows the comparison between INSAR and pixel offset. And as you know, INSAR can achieve very high accuracy, like millimeter to centimeter order, and a high resolution, like 10 meter or finer. But there is a limitation. So INSAR cannot measure very large meta order displacement because of the decorrelation and phase unwrapping difficulty. And on the other hand, pixel offset analysis using conventional SAR data like L2 3 meter resolution data, we can measure meta order large displacement. Yeah. But the disadvantage of pixel offset analysis using such 3 meter resolution data is accuracy and resolution. So the accuracy is about 10 to 30 centimeter. And the resolution is about 100 meter, which is significantly lower than INSAR. And yeah, this is the main reason why pixel offset analysis was only applied to these glaciers or large earthquakes. However, the important point here is the accuracy and resolution of pixel offset analysis is proportional to the SAR data resolution, SLC resolution. So this means if we use higher resolution data, we can improve the accuracy and resolution of pixel offset analysis. And as I said, we have very high resolution data from STRIX, less than 0.5 meter. And yeah, if we use such high resolution data, we will be able to achieve like 1 to 5 centimeter accuracy and 10 meter or finer resolution, which is almost comparable to INSAR. So there is no disadvantage anymore. So in order to demonstrate the usefulness of high-resolution pixel set analysis, I conducted the case study using Strix data. The AOI is Cushing in Oklahoma, US. So there are so many oil tanks here, and yeah, this area is called pipeline crossroad of the world. And yeah, this area is very important for oil industry and worldwide economy. And yeah, each oil tank has such floating roof. So this means the height of the roof changes depending on the amount of the oil for each oil tank. And if we can measure the height of each oil tank, we can estimate the amount of the oil. And this is very important information. So I tried to measure the height change of roof using our own Strix data. So we collected the Strix4 data from 4 different directions: ascending, descending, and left and right looking geometry. The observation period was around December last year, and the revisit time is nearly 1 day. And yeah, I used the highest resolution mode, and the baseline range was relatively large, in this case, 45 kilometers, but still the pixel set analysis was possible. And yeah, I produced stack of pixel set analysis result and conducted the time series analysis. And yeah, this is just one example of the pixel set analysis. So left one is the optical image, and the second one is a color composite image between 2 dates, January 1st and January 2nd. So we can see the oil tank shape clearly, because the pixel spacing of this image is only 0.55 meter, very high resolution, even with 2x2 multi-look. And we can also see some colors here and here. So this means, yeah, these oil tanks, the height of these oil tanks changed between these 2 dates. And the third one is a range of set result, and the right figure is a correlation coefficient, which is very high. And yeah, we successfully measured the height change of these oil tanks from pixel set analysis. And yeah, in this case, I used relatively small window size, like 16 by 16, and the pixel spacing of the result is 2.2 meter. So very high resolution, even with pixel set analysis. And yeah, we can use larger multi-look window size to get more stable result, like yeah, 64 by 64. And in this case, still the pixel spacing is less than 10 meters. And yeah, this window size was still sufficient to measure the oil tanks. So I used this window size for subsequent time series analysis. And yeah, this is a result of time series analysis from 4 independent observation geometry. So the color represents the height change between these 2 consecutive dates. And yeah, we can clearly see very active movements for each oil tank, especially in the eastern side and the southern side. And yeah, these independent data sets shows very consistent results. And yeah, I picked up some of the oil tanks. And yeah, let's see number 1 oil tank. So this shows very interesting time series. Yeah, so in the beginning of the period, it was very stable, but suddenly it increased the height 1.5 meter and stable again and uplift, stable, uplift. Then suddenly the height decreased to almost 0 meter level at this timing. So this means at this timing, the oil was extracted from this oil tank. So yeah, from this analysis, we can estimate the change of the amount of the oil for each oil tank. So this is very important information. And another point is the very consistency between the independent datasets. I plotted 4 independent datasets here, but they are very consistent to each other. So this implies the measurement accuracy is very high. And in order to estimate the quantitative uncertainty, yeah, I computed 2 uncertainties, yeah, theoretical one and empirical one. So first, theoretical uncertainty can be computed from this equation, which depends on the cross-correlation coefficient. And the empirical uncertainty can be estimated from the RMS of residual of each observation from the least square solution in the time series inversion. And the right figure shows the result of the uncertainty estimation, and the heat map is empirical uncertainty, and this shows that most oil tanks have correlation coefficient larger than 0.7 and residual RMS of less than 5 millimeter, not centimeter, 5 millimeter. So this means, less than 1 centimeter. And this result is very consistent with theoretical uncertainty, this red line. So this means that this measurement has less than 1 centimeter accuracy, even with pixel offset analysis. So let's move on to the third case study, volcanic activity monitoring. So the target is Mount Shimodake eruption last year. So this volcano erupted June last year, and the eruption lasted longer than 2.5 months. And we conducted many observations. We collected 63 images over 96 days using our STRIX satellites, STRIX 2, 3, and 4 from SSO and MIO. And we clearly captured the topographic changes caused by the eruptions using high-resolution data. And these are the acquired images. These are radiometric terrain collected intensity images. And we clearly captured some changes, like denoted by red arrows like this. And let me pick up some of them. The eruption started around the northeastern side of the big crater, and this is a new crack caused by the eruption. And then, 1 week after the first eruption, the new crater appeared here, the southeastern side of the big crater. And then, the new crater appeared around the center of the big crater, and after more than 1 week after the first eruption, 1 month after the eruption in August, these craters expanded because of the big eruption around this timing. So we clearly captured these topographic changes caused by the eruption using our high resolution and high frequency observation data. But these are just visual inspection, but we can also quantitatively measure the height change caused by the eruption using repeat path INSA. And we call this technique INSA DDEM. This is our unique technique. And generally, the DEM can be created using single path INSA, but unfortunately, we don't have single path INSA data, but repeat path INSA can also measure the height change or create DEM under some condition. So in this case, we used post-eruption 2 data, which can be used for INSA with 1-day interval and with some perpendicular baseline. Not too small, but not too large. And we created the normal interferogram using reference DEM, and I removed the long wavelength component and applied the noise filter and phase unwrapping to remove these phase component other than topographic phase. Then I got this interferometric phase, which is almost composed of the topographic phase. And we can easily convert this phase into the height component in the meter unit. And this is the height change caused by the volcanic eruption. And here we can also create the refined DM, reflecting the post-eruption topography using this technique. So these are the conclusions of my talk. So the STRIX constellation enables high-frequency, high-resolution ground displacement measurement. And I showed 3 case studies, 1-day repeat path INSA, high-resolution pixel offset, and volcanic monitoring. And we will expand our satellite constellations more, and we will deliver more frequent observation capability. Yes, that's all from me. Thank you very much. Thank you for your attention.
Thank you very much for your presentation and these impressive results. Is there any question from the audience? I would have one question about the pixel offset analysis that you have been showing. So if I understand correctly, you analyzed the theoretical accuracy that you can achieve. The theoretical accuracy that you, theoretical, did you have any validation data to confirm that this is actually the displacement?
Yes, I think the empirical uncertainty is kind of the validation. Yeah. And yeah, this is from the real data and the residual, and yeah, this is consistent with theory. And also, I have just one simple comparison. Yeah, this one. Just I compared just single pair of the pixel set result from different independent direction, almost the same timing, and yeah, some of them shows meta-order displacement, but they are very consistent to each other. So this is a good demonstration of to show the accuracy, centimeter order accuracy.
And also, similar to the question we had before about INSAR, so do you think that there is a kind of drive for this kind of application? So pixel tracking in daily mode, do you feel this is a kind of commercial application that could be pushed?
Yes, I think so. Actually, yeah, this kind of oil tank monitoring has some demand, especially in the current war situation. And yeah, actually there is a demand in the commercial. Yeah.
Okay, good. Any question? No? If not, thank you very much again for your presentation.
Yeah. Thank you.
Thank you. So for the next talk, we would like to invite Irina, who is presented a new mission, but also application, because this is Agri-Roselle, that is an airborne experiment for land cover, vegetation parameter, and soil moisture. So, thank you.
Thank you, Andrea, for this introduction. It's not about a new mission, sorry. I'm now presenting really a campaign that we have conducted within the German Aerospace Center with the FSAR system that we have. And this is in order to simulate new mission products, for example, for Sentinel, but also new mission progress more related to ROSE-L. But let us go a little bit more into the campaign itself, because that's the main idea here. Agri stands for agriculture, and ROSE-L, therefore, the new missions. And also what we had in addition, we had not only radar, but also hyperspectral imaging conducted, which is in principle the KARMA mission. Yes. Just, you see, we have a lot of authors here. It was a big team that were collecting ground measurements, but also flying their instruments on different sensor platform in this case. So we had radar, but also hyperspectral imaging here. This is actually an ESA study, or is in principle an ESA study that is led by Julia Kubanek and Marco Celesti. So both, one from the radar side and one from the hyperspectral side. Okay, let us go to the test site. The test site is very close to the DLR's test, in principle, station. So we are in southern Germany, which is close to Munich. And you see DLR already as a dot. And then the test site itself is called Puch test site. So it's in southern Germany. So the main motivation, as said, is simulation of simulation of satellite data using airborne systems or platforms. And the main idea here is to simulate a 6-day repeat time. This is important. Collect data for selected times every 3 days also. Observe structural changes over diversity of crop types, and collect, as said, even other ground measurements. One of them is soil moisture and also vegetation parameters. Okay, this is a test site. You see already the test site is conducted, in principle, is a huge area where we have a lot of different agricultural fields. This can be well seen here, and also some forested area. If you now just overlay these Google Earth image with one of the acquisitions that we had, this is an airborne acquisition. in a Pauli display, which means RGB is displayed in surface, dihedral, and volume scattering. Everything that's red is very strongly dihedral, and we see we have really these kind of very well-known flashing fields, which are very popping up very strongly. But we have also fields which are darker a little bit. Bluish means surface scattering mainly obtaining, but also the green parts, which are the forest here. What are the field size? So the fields that we are doing ground measurement on the same same test site here, we see we have a diversity of corns that we were measuring. We have rapeseed, oat, wheat, ray, alfalfa, corn. I think that's the most important parts. And we have in principle two displays. The one we call Eitelsried, which is more on the right part, and then on the left part we have a huge amount of other kind of fields. So these are two kind of stations that we had. The one we're collecting ground measurements from the DLR site, and the other one we're collecting ground measurements from the Ludwig Maximilian University. Okay, what are the main variables that we have? You see already we have collected a huge bunch of variables from the optical, for the optical campaign, but also for the radar campaign, which some of them can be also used in a merged manner, right? But just in principle to see where we are sensitive to. We have a lot of, in the optical domain, we have a lot of parameters which are related to the vegetation itself. And in the radar part, we have also very strongly the soil contribution, but also soil moisture parts. What are the sampling strategies? Here you see a little bit how the Ludwig Maximilian University was sampling some of the fields. Just as an example, we have vegetation samples, which are dots, green dots in this display, which means we have around 3 samples or 3 areas where we are sampling within one field over the time. And we have also more narrow grid for soil moisture estimation. So like these, that we also get in principle the diversity, the spatial diversity, actually in order, to capture them and to collect in principle the data over these regions. There have been a lot of, a huge amount of sampling. In general, you saw already the variables that we have collected, but there's a really huge protocol behind it, a sampling protocol that they have filled out for each of the campaign dates. You see it here, and using in principle different techniques in order to estimate, for example, the leaf area index, but also looking for soil moisture itself, doing also hyperspectral calibration, as you see it here in one of them. Yes, and cutting also the vegetation itself, which was, the cutting was around of a 1 by 1 meter. They cut it already a quarter of it in order to investigate this in later in the lab. So they're cutting the samples. We had around 1,800 samples collected in terms of the vegetation samples. And then in the lab, they needed to spread these in terms of stem, leaf, and fruits. And you see it is quite a tedious work where you separate these 3 compartments of a plant in order to see where is the biomass or the moisture content very strongly related to during the growing stage of a plant. We had also, in addition, a LiDAR drone available, which were very in the beginning of the campaign, measuring the surface roughness. So we have a very, very high digital elevation model actually over all of the fields conducted. So what are the EFSAR campaigns? So the radar campaign dates that we had. So we started in April and we finished end of July. These are the days that you see here in green. We were collecting every 6 days, sometimes also 3 days in between, so 6 and sometimes 3 days. And then you see on 3 of these parts, it's written by 3 or by 2. And these are the days where we're even within a day collecting 3 times data, which means we were flying in the morning, in lunchtime, and then in the late afternoon again, in order to see also the variation within the day, specifically for moisture content, but also for evapotranspiration. Okay, that's a little bit the flight lines that we had. Here it's only one direction. You see already we were flying quite several passes over this region. I will come later on why, because we have done also tomographic acquisitions over these regions. But this part that you see now is our main flight path, but we had also perpendicular to it for each of the date also a flight, so that we had also different incidence angle capture, because that's also sometimes important for people which are looking for incidence angle diversity in order to resolve soil moisture models, but also vegetation models. As said, we had tomographic acquisitions, so we were flying a lot of baselines. You see here a range, a variation between -50 to 130 in two frequencies. Mainly we have in L-band and C-band, so these are the main frequencies that we had. And if you think about, I mean, we have the baseline, but what are the, in principle, the vertical height resolution, because this is something that you would be probably interested into it, is here in the table written down. So if you have a near range with 25 degree, you see we have a vertical resolution of 1.2 meter in L-band, and in centimeter range, so less than half a meter, 45 centimeter in C-band. If you go in mid-range for L-band, around 2.5 meter, and less than a meter in C-band, and far range, it's increasing, it's clearly 5.7 or 5.8, and 2 meters for C-band. So this is in principle the ranges that we have. So in order also to capture, because we are starting very early in this season, and then with the growth also the crops are growing, and it's good to have this diversity also in terms of vertical resolution. So as said, so this has been the radar campaign data, but we had also collected images, or let me say hyperspectral data. So the main, it was not done completely at the same time and date, but we had 4 successful flights. It's very depending on the weather in this case, which we have a little bit advantage with the radar system, but we had very good 4 flights collected on the 12th, 13th, and 19th of May. So that's quite interesting. And this has been also done in parallel with some satellite imaging or satellite acquisitions, for example, with NMAP. Some of them have been started in parallel to do it. So these are the flight lines, because they are very narrow lines, much shorter swath width as we have with the F-star system. But however, they are also covering quite well the main region, which is here now displayed in yellow. We have also collected during the whole time where we had our radar acquisitions, also satellite images and hyperspectral, mainly NMAP, DESIS, and PRISMA. And you see here how many collections do we had within this time frame. So which is 13, 16, and 11. Okay, oh yes, oh yeah, I'm not sure if you see it. So if you switch now, you see here now one of the, it's one quick look image already of this hyperspectral imaging that you see here. So very, very high resolution, very great display in principle of the fields in May. We had also another, let me say, instrument, which has been flown by Czech Globe. They have flown twice over the same area in 19th of July and 3rd of October. And they had 3 instruments which they were collecting data, the high plant, the TASI, and the LiDAR. The high plant is in principle a hyperspectral, let me say, imaging instrument, which can have also fluorescence on top, which is great. And then we see TASI has also 22 bands, and the LiDAR just in order to see really at the same time what are the height variations. We had then, and the same happens also then in October, and in between, so the 1st and 3rd of October, we had a UAV platform, again with a hyperspectral imaging instrument from the GFZ, Geophysical Geoforschungszentrum in Potsdam. And they were doing also several flights, as you can hear, again with a hyperspectral instrument. Again, this has been data that has been collected in let me say, in correspondence also for the future mission that will be launched in this respect. Let us have a little bit of look how the data look like, or not the data itself, but in this case, the area. So this is one of the very early images that you see from April, one of the first, let me say, campaign data that we had with wheat, potato, and corn. You see they are quite huge, these are huge fields, less vegetation on top. Wheat started already, because it's winter, wheat started already to grow up. Potatoes was bar, and also cornfield was bar. And you see below also a little bit the roughnesses and the amount of vegetation available. And here now at the end of the campaign in July 23rd, we see the wheat is already very, let me say, so far that it can be harvested, it's close to harvesting, is already brownish, already drying out. Potatoes were growing, and corn is already on a high stage, not the highest stage, but already in a 2-meter range. So if you look now very shortly now to the data itself, I'm just showing some of them. It's just an example from April, some collection until July, and some images in between. This is now the L-band image. Again, as said in the first one, you see the flashing fields. They're appearing not in the beginning. In the beginning, we have, you see it already here, still quite dark areas. Here also quite dark areas because we have low vegetation on top. But then slowly in May, they are growing up, and also here it's become reddish and greenish also until it's getting really, really very green, specifically certain fields that we have. So which means it's an indication of having a growth on corn and other corn types here. And then in C-band, you see everything is lower. It's not so, the dynamic range is much smaller. Again, in April, we have much more these bluish fields here. They're popping up slowly in May to have more reddish parts, and then becoming much more greener than in July. So you see we have different sensitivities using L or C-band, and that's important also for the investigation and analysis, how to combine L and C-band acquisitions in future also for the mission concepts. I was just showing also some of the images for the interferometry. You see we have quite high coherences in L-band over the different dates. So these are adjacent days, so 6-day coherences and 3-day coherences, as you can see. And if you look now to the C-band, even if I have 6 days or 3 days, the decorrelation is quite strongly because the growth is specifically in May, or the change is very, very strong. So therefore we have quite strong changes also, and therefore stronger decorrelation. As said, we have also acquired tomographic data in C and L bands, on both of them. Here you still see a display of the baseline in terms of kappa zeta, a point spread function, in order to see how good we can really separate our signals. Very well seen, and I have a small video just to go along. So what you see now is a profile over this line when it's moving, and you can see it's a very, very preliminary analysis in terms of we see a change when, in principle, the line is moving, how the change looks like in the vertical change. And sometimes you see some disturbance, which means we have some forest on this. You see now passing a forest, therefore you have a very strong jump of this line. Sometimes the line is a little bit spread, which means I have some agricultural fields already in between, which are also showing some variations there. So there's just that you have a view on how the data look like. This is displayed on top in HV polarization and below in VV polarization. Also here we have smaller differences. We had also a WB-SCAD instrument on top, which is an instrument that we have rented from ESA and in principle provided by Gamma. We have installed it on the tower, so we were building up the tower, putting the instrument on top. The instrument looks like this here when it is installed. You see with a boom here in order to have a look on the wheat field. That's a wheat field you see here behind. We have also done calibration of these of parameters on the wheat, and then here now you see how they're deinstalled after the campaign. Just to get a little bit of a look how WBSCAT data looks like, this is now in C and L band over the time. So you see in different polarizations in C and L band how it looks like. It is what we would, it's just the first order analysis, what we would expect. So you have variation in terms of variation over this wheat field that we have depending on the day and time, also depending a little bit on the weather conditions that we had. And we see also very, very well that we have also spread in terms of polarization diversity. Okay, what are the next steps? So the data have been already processed now. We have done the campaign last year. As said, from April to July, we have started to process all the data. So we have all the tomographic stack processed. And we have also now done the simulation for Sentinel and ROSE-L. So some of these data, in at least the interferometric stacks, are in principle simulated in terms of mission parameters. So that's great. What we are still doing or working on is in principle the analysis of this data now to the 6-day and 3-day temporal decorrelation. And then we would also do first order soil moisture performance estimation with vegetation. So we are just taking very shortly now the images to see how it looks like if you just apply a standard model on it. And then doing also some trade-off analysis, dual versus quad pole. That's important. And all the data will be also transformed in an IE-ready data compilation so that everybody who's using IE can, in principle, also directly use this data. Yeah, that's all. And thank you for your attention.
Thank you, Irina. Thank you very much. Are there questions about this rich campaign? I have a couple of questions. The first is, so you have a good opportunity to use tomography. How do you think you can use it to improve soil moisture analysis?
Yeah, the main idea in order to use tomography is in principle try to separate between vegetation and non-vegetated area, and specifically here where we see the whole evolution, right? You can estimate very well the sensitivity in terms of having bar fields, right? Which we have, I mean, models and they're working, but what happens when you have vegetation on top? You try in principle to separate the volume from the ground. And like this, yeah, we hope that we are able to have a better estimate.
So you think to apply the ground notch, or you just use a usual tomography?
No, I mean, there's different approaches. One is the ground notching, but there are also other ones that we would like to apply on.
And the other is these data are available for public or
yeah,
still,
so as said, this is an ESA campaign. Yeah, ESA campaign, which means all the data available. We are, as said, we are just now so far that we are transferring this data to ESA probably in the next months. And then they will be hopefully soon available on the server so that everybody from you, therefore I was also presenting a little bit more in detail what you can expect from this data so that you can download them and use them. So we are really hopefully to see in next conferences results coming out of this data set. Would be great.
That's good. Thank you. Are there other questions? No? Okay. Thank you, Irina.
Yeah,
thank you again.
I'd just like to thank also the team which is behind. So there are a lot of people doing and having fun, a lot of students, as you can see, and I'd just like to acknowledge them too.
Oh, many. Okay, thank you.
Thank you very much. Next presenter is Luca Dell'Amore. So the talk is about deep learning framework for joint onboard interface denoising and compression. Thank you very much.
So thank you very much, and good morning also to everyone from my side. So I'm Luca Dell'Amore. I work in DLR, so in Oberpfaffenhofen, close to Munich. So today I would like to talk about a deep learning framework for joint onboard interface denoising and compression. So to start the presentation, I would like just to show you a real interferogram. This is a tandem mix interferogram in a single look strip map. So as we all know, the interferograms are typically strongly impaired by phase noise, as we can see here. And in particular, if we want to generate reliable and high quality insert products, we need somehow to denoise, to apply effective denoising strategies. So this is typically done, as you can see here, for example, using a boxcar filter, which basically improves the denoising capability, but at the cost of spatial resolution, as you can see here. So moving now to the problem definition, just to give you a little bit of context for this investigation. So we are in the framework of planetary missions. So in general, planetary missions have really strong constraints in terms of downlink capability. So which means that somehow we need to apply effective onboard compression and also denoising strategies. Here, I wanted just to report some past missions, and I will say also exceptional missions. So we have Venera 15 and 16, NASA's Magellan mission, and hopefully also in the next years we will have Veritas. So just a few words about Veritas. So basically the main goal here is the generation of a global DM digital elevation model on Venus. So the goal of our investigation was basically to try to use a neural network in order to denoise and compress the interferometric phase on board. So this is basically the concept that we have proposed. So the main idea here, so basically we are going to focus first of all just on the insert phase. We are not going to consider the coherence. And the concept here is basically to have an encoder on board the satellite, which basically compress the spatial dimensionality of the input interferogram. Basically then we want to downlink this compressed representation, which is called latent space. And we will have also a decoder on ground, which basically reconstructs a denoised version of the input interferogram. So if we want to perform this kind of denoising and compression using a neural network, the natural choice is basically convolutional autoencoder. Then why? So using a convolutional autoencoder, so we are talking about complex data, so we are going to have two channels input, which correspond to real and imaginary parts of the noise interferogram. And the idea is to have this encoder on board the satellite, which basically performs 2D convolutions using different kernels. And very important, the encoder is also performing pooling operations, which are basically downsampling operations. So basically we are gonna compress the spatial dimensionality of the input data, and of course we are gonna lose also a little bit of, let's say, higher resolution details information. Then when we reach this latent space, which is this compressed representation of the input data, the idea is to downlink it to ground. And on ground, we will have a decoder, which is typically symmetric to the encoder part, which is going to perform, again, 2D convolutions, but in this case, is going to upsample again in order to reconstruct the original sampling of the input interferogram. And as we all know, when we apply standard upsampling strategies, basically, we are going to lose some higher resolution information. So in order to investigate different performance trade-offs, basically, so we decided to play a little bit with the parameters of our convolutional autoencoder. So basically, the first main driver for the performance is the autoencoder depth. So basically, is the number of encoding and decoder stages that we have. And as you can see, here, basically, if we just assume one encoder and decoder stage, we are not gonna compress so much because we are not gonna reduce so much the spatial dimensionality. But of course, we can add more. We can add more stages. In this way, we can compress more. But of course, the drawback is that we are gonna lose also a little bit of information. Then we don't have just the spatial dimensionality into account, but we can look also in the feature dimensionality. So basically the feature dimension of the latent space corresponds basically to the number of output channels in the latent space. And here again, if we will have more channels, we are going to keep more information. If we are going to keep less features, we are going to lose a bit more information, of course. On top, one could also think about applying an additional compression strategy. Typically, we want to have it lossless. So for our investigation, we use the deflate method, which is basically just like a standard zip, basically. So moving now to the supervised strategy that we adopted in order to train our network. So what we have here, we have shown to the network basically a reference phase, a clean phase that we want to teach the network, basically. We want the network that it should reconstruct this noiseless phase. And then based also on the estimation, we can compute a loss function, which for our case is basically weighted absolute phase error. Why weighted? Because where in presence basically of very low coherent areas, we want to weight a bit less our phase error, since we can assume that the network already is struggling, or in most cases is not even able to reconstruct the real phase behind the noise, let's say. Also, moving then to the dataset generation, of course, since we use a supervised strategy, we needed also to generate a proper dataset. So I'm talking here just about synthetic datasets. In particular, for the generation of the dataset, we started from the covariance matrix of the two SLCs, basically. And if we assume that the signal and the additive noise term are statistically independent, we can basically model just the covariance matrix of the noiseless signal and the covariance matrix of the additive noise. Just to show you a little bit more in details, so basically for the noise part, we use the tandem mix noise profiles, while for the signal part, we also started from tandem mix quantities. So we have here the amplitude, coherence, and a noiseless phase. So basically this phase, it comes from by back geocoding an external DM and using the actual tandem mix geometry. And what you can see here is just basically the model synthetic noise interferogram. And in this case, we have the noisy input, and of course, we have also the reference phase that we want to reconstruct using the network. So as comparison, basically, we also consider a combination of traditional methods. So basically for the noising task, we have used just different boxcar windows from 3 to 9, while for the compression part, we have considered basically the JPEG 2000 approach. And also here, we can assume a lossless compression, but we have considered also some lossy compressions. Basically, we have a compression ratio of 2, 3, and 5. So talking about performance metrics, of course, since we want to denoise and compress the interferometric phase, we are going to look into the denoising performance, compression ratio, but also, as I said at the beginning, since the decoder is going to apply basically just standard upsampling strategies, some upsampling operations, we are going to look also at the percentage of preserved high resolution details, which is also quite important, actually. So looking now at the 3D performance space, we can rearrange this axis in this way, basically. And what is important to notice here is that this yellow star basically corresponds to the optimum ideal performance combination. So basically, consider this yellow star as the reference, let's say. Let's call it in this way. So moving now into the results. So we have performed this investigation, again, just using a synthetic dataset. And actually, we have focused over mid and high coherence values, so basically higher than 0.4. And this is what we can get. And actually, the main achievement here is that, as you can see, we are more flexible compared to the boxcar. So basically, if we take the boxcar, the baseline performance here, we can see that we are quite constrained in basically in the performance space. While if you take a look at the solutions using the autoencoder, basically, we can see that we can explore this 3D performance space a bit better. So now, just to understand a little bit better what's going on here, I wanted just to take a look at the cross sections. So again, here, maybe I think it's very interesting to take a look at what's happening basically for each family of train models, of tune models, basically. We can start here just with the denoiser. Basically what we see is that we get a very nice denoising performance in terms of the standard deviation of the phase error. We actually preserve also quite well the, I would say, the higher resolution spatial details. But of course, since we are optimizing just for the denoising, we lose a little bit in compression. So basically, we are not compressing, here, sorry, we are not compressing so much in this case. And here you can see also an example of the reconstruction by the network. And I think it's quite nice. This result is also quite similar actually to the reference noiseless phase. Then, if we take a look, for example, at the family of models tuned just for the compression task only, what we see just taking here is that basically the estimation is going to be a bit smoother, which makes sense, since actually we are optimizing just for the compression task, and while actually the other performance, they get a little bit poorer. Mainly, also, you can see here that basically if we optimize for the compression task, of course, we are not going to preserve many high resolution details, which makes totally sense, of course. Then we might also take a look, we can also take a look at the family of models which have been tuned just in order to preserve as much as possible the higher resolution details. And here, what is very interesting to notice is that basically the autoencoder is behaving similarly to a 3x3 or 5x5 boxcar approach, basically. So the denoising and the compression performance are going to be poor, but this is because basically the network is trying to maximize, let's say, the preservation of high resolution details. Last but not least, we have also evaluated another family of models, so basically which we call the best compromise. So basically these models have been derived by looking at the normalized score between the three performance metrics. And what is actually very interesting here is that this family of models, they achieve a very good compression, actually, compared also to the baseline, together with a good denoising, I will say. And actually also the amount of high resolution details which are preserved is actually also not so bad. So just to summarize a little bit all these achievements, again, here is the main achievement is not to say our technique works better than the baseline approach or is worse, but the main achievement here is really the flexibility. So compared to the baseline approach, we are way more flexible to explore the 3D performance space. So moving now to the conclusions. So basically, we are in the framework of planetary missions, so which are typically very constrained by downlink capability. Basically, we have looked just at the in-surface. No, we didn't consider so far the coherence. And what we have proposed is a convolutional autoencoder, which allows basically to achieve some compression on board using an encoder. And basically, the decoder and ground is going to reconstruct the denoised version of the original interferogram. And as I said before, since in the decoder we have upsampling operations, we are going to lose, of course, some high resolution details. Then what we have done is basically an hyperparameters tuning on different settings just to explore different performance trade-offs. We have proposed for this, for the supervised strategy, training strategy, also a novel mathematical noise model, which basically describe a real case interferogram prior to assumptions. And we have compared our results with respect to a combination of traditional methods, so basically boxcar filtering and JPEG 2000. We have assessed our results in terms of denoising capability, compression ratio, and high resolution feed details preservation. And again, the main achievement is that we have got an enhanced overall flexibility with respect to the baseline, but also we can take our results as a valid alternative in terms of absolute performance as well. Mainly, I would say, targeting the denoising capability and the high resolution details preservation. As outlook, we could think also about taking a look at the interferometric coherence as well, so basically estimating not only the interferometric phase, but also the interferometric coherence. And of course, it will be great also to have a performance assessment on final DMs as well, and not only on a synthetic data set, basically. So that's all from my side, and thank you very much for your attention.
Thank you very much, Luca. Questions? There, Paul.
Very interesting. I'm not really familiar with the computational aspects of these neural networks. Is it time consuming to run a neural network like this to do it? Because another resource that's important for planetary missions is computation time and power.
So actually, for this kind of analysis, we didn't really look so far at the computational time, but of course, it's a super valid point. I can say already that it's quite fast, also the inference. So let's say the next step is really to try to look also into real data, for example, tandem mix interferogram, since we have a lot of tandem mix data, I will say, but it's quite convenient also in terms of processing time. This I can already say it.
Thank you. I might have missed the beginning part. What's the pairing strategy? When you install pairing strategy in your study, are you considering nearest neighbor in time only or more? Oh, it's a single pass interferometry.
So in this case, basically, was just a proof of concept just to use a neural network, so basically convolutional autoencoder for this joint compression and denoising. So basically, we have modeled everything starting from tandem mix quantities. So, I mean, we have estimated the coherence from tandem mix data, we have estimated the amplitude, we have retrieved a noiseless phase via backgeocoding coding of an external DM. But yeah, actually, I mean, it's everything based on synthetic data sets model using tandem mix quantities. So we are talking
so in that
about
case,
single pass or interferometry.
Coherence would be mostly like volume decorrelation.
I mean, in this case, yes, it's, I mean, using tandem mix data, we don't have temporal decorrelation, of course, but let's say this theoretical model actually is basically inserting an amount of noise into the noiseless interferogram, let's say, basically depending on the coherence. So I would say that we have used, as again, tandem mix data, but this could be also extended to other sensors, even if you consider some temporal decorrelations. It could be already included in the coherence.
Thank you.
Yep.
Thank you. One of the questions I had was, so deep learning models are quite nice, but they are not very transferable. So have you tested if they are domain adaptive, or they can be used for different scenes than that you have trained? Like, do you know how good they will perform in different domains?
So you are basically asking about, let's say, if the data set that we used for training, it might match also a kind of data like, let's say, kind of data similar to what we could get for Veritas. So actually the answer for this, it's just related about the insert phase. We have used around 400 different acquisitions, so really with different also bistatic geometries. So the network has seen all possible combinations of fringes. So we go from low frequency fringes to high frequency fringes. So basically the network has seen all these kind of phases, basically. And also we have tried to insert the noise, basically, in a balanced way for every level of noise. So basically the coherence that we use to insert the noise using our theoretical noise model is taking basically a balanced coherence from low coherence values to high coherence values. So the network has seen probably all possible combinations between coherence and phases.
Okay, yeah, thank you.
Thank you. So I have just a quick one. I've seen a lot of combination, but not what will come from Venus. So do you expect the interferograms from Venus to be very similar? Because we know CNN are trained on Earth. So are the interferograms from Veritas similar to what we have from Tandemix?
So this I'm not really sure, honestly. But it's, let's say, again, if by showing to the network all possible combinations going from low frequency fringes to high frequency fringes, I expect that somehow also in the interference on Venus, we should get more or less the same patterns. Exactly.
Thank you very much. Yeah, so we should move on to the next.
Okay, thank you. Thank you. This very challenging presentation. Now, the last of the morning is Otmar Frey. Otmar Frey is gamma remote sensing and also ATH, Zurich, and is presenting monostatic and bistatic SAR imaging and SAR interferometry with compact UAV borne and cardboard SAR system, L-band, S-band, and results from latest campaign. So,
sorry for the long title. Yeah, thanks for reading that out. Thank you for the introduction. My name is Otmar Frey. This is work I've been doing at Gamma Remote Sensing together with a number of colleagues you see listed, also colleagues at CREL in the US and the University of South Florida. And it's sort of about our L-band radar systems used in different ways, and I'll walk through some applications and things we have been doing the last couple of years, also related to some easy campaigning. So this is just an overview slide that gives you an overview of what we have been starting to do using our system for repeat pass interferometry mostly from cars, so driving on roads, looking at glaciers, landslides, but also from drones more recently. And this is already quite established. So I'll just pick a few examples to show you that, and then we'll go on and talk a bit more about work in progress, which is the bistatic experience we have been doing recently. So this is some of the very first acquisitions we did in Switzerland, looking at a glacier, and you see that visualized. So we're driving basically on this road here, from which, and this is of course not a general thing you can do, but you can see a glacier and you can track the velocity. So this is a 17-hour time span between the acquisitions, and this was sort of a first test we were doing with our radar, and also first demonstration of applications we did back in 2018, so quite a while ago. Another example I want to pick is this landslide here, and one of the reasons is also this has been studied again within a project, the ESA Modulate project, which is led by Tazio Strozzi, and also Andrea Manconi actually is involved in that, and a few other colleagues from Ticino and Northern Italy. And this is just an example where we used a combination of these car-based measurements, but also satellite-based L-band measurements for this specific site. So as you can see, the orientation of the landslide here, I go maybe one slide back. So here you see what's happening there, like in a larger time frame. That's a laser scanning based digital elevation model between 2019 and 23, including this large collapse that happened in June in 23. And you can see that not only up here, like above this little village, but also the entire region here is sort of moving like a sponge. whereas the fast movements are happening there and substantial danger for the village. So the situation has improved a lot now because there was a lot of investment, tunneling to drain the water out of that. So the displacements are much slower now and people can go back to live in the village. But this is one of the sites we have been visiting a lot with our system. And in this campaign, we have been measuring from a road on the other side here and looking to that region over there, doing repeated passes. You see the example result here from that measurement using this radar. Of course, here looking into the wrong direction, just that you nicely see the antennas also. But of course, we're looking to the other side when we measure. And on the middle and the right, you see L-band measurements from SAOCOM ascending and ALOS pulse descending, where you can see that due to the orientation of the landslide, they have a hard time capturing all the areas for displacement, whereas with this view angle and also the different resolution, we get a more clear picture of the displacement velocity in light. Still line of sight only, but it's complementary to the other ones. So Tatsia was then also stitching the information together. So this is sort of 3D displacement derived from this combination of measurements for this specific site here. Then another one also done in this Modulate project, and I think it's a nice example where you can see sort of the mixed land cover that we have here. So we are observing over roughly half a year, so October 24 and then June 25. And interestingly enough, we managed to get almost the same acquisition dates as the SAOCOM satellite. So it's just 1 day off here in June, whereas it's the same day actually in October. So it's almost the same time span. And you should see exactly the same thing. So you see the differences, the resolution, the spatial resolution is much better here, of course, but you have shadows because you're up looking. Direction is from that side. So we're sort of looking into the scene from here. So this is that patch over here is that region here. And of course, you see the difference is that some of the areas you cannot capture with the car-based radar, but this is quite complementary. But the main features are really there, so you can sort of visually see that we capture that in both cases very well. You can see the better resolution, and also especially in that area here where it's forested, also slightly better performance here with the radar from the car. So there's a publication that is out, as I said, led by Tazio, who is managing the project and leading the project, and also Andrea has an important role, mostly in the spaceborne part as well. If you're interested, here's the reference. So now jumping a bit from the car base to what we do on the drones. So we have been starting doing measurements in 2019 already from larger drones, and then the first ones from octocopter drones with our newer, smaller, compact L-band radar. So you see here the radar and the two antennas. So it's a FMCW transmit and receive antenna. It's well, dual-pole antenna, so we can do alternating transmit modes. We can get quad-pole data as well. Mostly have been using it for interferometry so far. This is one of the very first examples. We did imaging in the US near Philadelphia, and just also we usually do these very short repeat pass interferograms to check for the performance, because it shows you very well whether you have some residual problems with residual positioning errors that may show up then in the repeat pass interferograms. So coherence is very high and also very smooth phase in this case. We have a S-band version of the same radar as well, which you see up here. So the radar from outside looks the same, just the antennas, of course, are a bit different because we want to have also the same elevation beam width. This is an example image we took last year in quad-pole mode using this S-band radar in close to Krell in Vermont, but very close to New Hampshire, actually. And at the same site, we're also doing the bistatic experiments that I'm going to show in a minute. Just here also short image of like the short-term repeat pass interferogram, relatively smooth phase, except where you have a bit of topography because there's residual baseline, and as soon as you have unknown topography, which is not included in the processing, then of course the phase show up. But otherwise, we have a very good phase screen and also high coherence. So what we're using is a time domain processor, including a DEM and a post-processed GNSS and INS fused navigation data to get the full 3D information about the trajectory and the ground information. So this is the bistatic setup we were using last year for the first time, and very unfortunately, it's still the data we have until now. So we're hoping a lot that the colleagues could fly again. We go to the US again this summer, so that's how we make sure that they fly again, that we show up. But I will show you what we have for now. We did some first experiments last year. And of course, the motivation, I think I'm preaching to the choir here, so I think I don't have to go through that slide so much. I think these bistatic concept has been discussed at length. We see that, and I think ESA has some projects running as well, that with the UAV you can, once you manage to do the bistatic focusing, as we'll see, it's not so easy to do, but once you have that, it's a flexible means to explore different acquisitions and explore data with different bistatic configuration. And of course, it may in the future also be valid as a sort of benchmarking or validation tool for biophysical and geophysical parameter retrieval. So this is the setup that we were using, sketched roughly, and I'm also showing like the way we were actually flying for this particular data set that I'm showing. So we try to fly really behind each other, and that was a bit hard to achieve in practice because we had to program to achieve the bistatic synchronization. You program the time when we start the acquisitions, and that meant that the pilots had to make sure they can actually start flying at the right time. And sometimes they managed, sometimes they didn't. So we have a number of data sets that were not successful because of that, but some of them were. So you see here the two drones flying in action, so the little dots here as they pass by over this test site. The way the radar is organized, so these two gamma L-band radars, they are equipped with a GPS discipline oscillator, and so the time synchronization, at least the PPS accuracy of those, is at the order of 30 nanoseconds. So that's sort of the offsets that you get up front, and then there's also drifting happening as well, as I think many people know here. So the idea was to capture the direct signal transmitted by GLSAR-1 through the back globe of the first one, and that also put some constraints on how we would fly. And because the direct signal will be superposed with the same channel that has the backscatter, so it should be closer than the nadir return. And what I'm showing here is sort of the flight track of these acquisitions. So we see here that they're slightly offset in azimuth, so you're flying from here to here, and then also back again, and looking into this area here. What I'm showing here on the right-hand side is the distance between the two radars, just calculated from the position. So you see here, that's one of the tracks, and usually when they stop and go back, so there's a bit of variation, but once they're flying again, they kind of manage quite okay-ish the let's say, constant velocity and also positioning within a certain tube. If you look at the height difference, you see that there's a bit of more variation in the height. The main reason for that is that one of those, at the time when we were using those drones, was not using in RTK, so only one of them was guided with RTK for the flight directions. For the post-processing, we use always INS and PPK, GNSS, so that's the full quality. But to sort of fly the right tube, one of those drones was not equipped with the state-of-the-art, you could say. So that is the monostatic L-band image just from the transmitter that we receive here. So you see, I go maybe back here. So this agriculture land, there is a horse stable. There are a bunch of horses actually running around here, partially during acquisition. So we have some moving targets as well. And there is also a power line that is crossing here that you see very well in the scene. So if I just do a bistatic focusing in the time domain without doing any additional synchronization, just sort of use the geometry, that is what I get. So you see an image, but it's very distorted. maybe I can flip forth and back. So it's also shifted, of course, and there's quite a large shift in range mostly, and we saw that this is way beyond, in this case, than actually what we would expect from this PPS accuracy that we have. And the worst case actually happened in the sense that that was shifting towards 0, which is the region where actually we have analog filters that filter out the lower frequencies in the beat signal, because we, of course, want to get rid of the direct response between the transmitter and the receiver. So in the end, that means we did not really capture the direct signal, which we'll see later still leads to problems in the focusing. And once I sort of make a correction for this large range shift by 35 meters, I first show the repeat pass coherence here just to verify that that looks okay. So this is the monostatic acquisition, which is always the reference, what we should get, the good phase screen and the good coherence. So now if I go to, I'm sorry, I jumped over one of those. So that's the correction that I apply. So I jump forth and back. That's the pi static one without any correction. And then if I apply this 35-meter correction, that's what I get. So it looks much better, but it's still not very close. So that's the monostatic again, and that's the bistatic corrected one. Don't be confused by this jump here, because that's just because we have a slightly different view angle. But if you focus on a certain target here, you'll see that it still jumps around a little bit, on the order of maybe a meter or so. So it's still not co-registered well because there's a drift and there's defocusing happening. And this is something we see much better in the interferogram. So again, now the reference, that's the repeat pass coherence of the monostatic one, and the phase screen that you get also just the monostatic one in the repeat pass. If I now do a bistatic coherence of my acquisitions, the bistatic mode, I see that I just have coherence at the beginning. So we're flying here, and then it degrades as there's still a gradual drift and defocusing as well, which also leads to a phase ramp, which we can see here in the bistatic interferogram. So the quality is certainly not there yet because we were not able to track that direct signal for the compensation. And yes, if we look at the monostatic received signal, we see here very well the nadir return. And if we look at the bistatic one, we see that this is shifted by 35 meters. This is not a direct signal, but just a nadir return confirming that. So we did a few bistatic delay line measurements in the meantime to sort of just verify a bit better what we can expect from our system. So we're using two newer versions of the same system, GLSAW 4 and 5 here in the lab, with a delay line setup, just looking at how the drift over time is happening. And in this animation here, you see on the right-hand side the monostatic signal, just an acquisition over 60 seconds here, so 1 minute, and I'm jumping here just from a couple of seconds here through the acquisition, and you see that, of course, the slant range here is very stable, just at the delay line, whereas for the bistatic one, you can see that this is moving around quite a bit as we progress in time because there is a drifting happening. And also, if we look then at the phase, if I track that signal here, we see that there's substantial phase ramp, whereas for the monostatic one, we have a very consistent phase of below 0.1 degree. And the good news is that if I look at this in more detail here, the phase variation that we have is not so fast that it would be within one pulse sequence. So I think we're very confident once we have the direct signal, we can actually track that and remove it. So to summarize that a bit, so as I was showing the monostatic modes, we have sort of an operational scenario. We can use that for repeat pass. We have demonstrated that. We have also used that for services quite a bit and various projects. The bistatic imaging and interferometry is still work in progress. So we think with the next campaign, with an optimized setup, which I show here, we have a broad beam width antenna that will look backwards from GLSAR2 and capture the direct signal in a separate channel. So we have a 4-channel receive system, so we can receive that in a separate channel. And we also will increase the distance between the two receivers just to the transmit and the receiver, just to make sure that we will not have the same problem again, that we will not be able to see the signal because of the filtering. And the colleagues have obtained permission already to fly higher, so to actually achieve this. Maybe a bit broader, quickly, the other colleagues in Germany at EUSA, there was a presentation by Max Eitel from Michael Schmidt's group. They have put our S-band radar on an airplane. So in the end, it's a very versatile system that can not only be used on drones, so you can image out to 10 kilometers or more. We think it can even go on a HAPS. So we are actually discussing with a few people on making this happen as a test case. With that, I would like to close, and I'm open to questions.
Thank you, Otmar. Our questions? Yes, there are a couple.
Yeah, thanks. Very impressive results already. Since you basically, out of the reasons that you said, like you couldn't record this direct signal, do you think there's information in the nadir response towards synchronization?
I mean, that's sort of the last resort, maybe, or but we would really like to first try, like, do it properly. The thing is that the topography variation is quite a bit, and it's complicated. It's even just for the focusing, we realize that we're flying so low that if there's topography and you do not account for them really well, you see it immediately in the interferogram, even the monostatic ones. So I think it's really hard to capture that well, but that would be a last option, also trying to infer it from the data. We want to do the right thing and track the direct signal first.
Sure, thanks.
Okay, next question there.
Thank you. In your car-based versus SAOCOM, same wavelength, did you intentionally try to match the look direction of SAOCOM for the purpose of comparison?
Yes, I mean so we had 3 sites in this Modulate project where we were doing the car-based measurements, and this one in Italy was a case where we had this opportunity to have almost once looking downwards, once upwards, but more or less the same direction, just with different resolution. So the idea was to see what we get from the 2 measurements. In other cases, we have more like complementary setups, as one in Brienz, where we look from a different angle. So we tried, in this project, we tried to really explore as many setups for validation, but also complementary measurements at L-band as possible.
But in general case, would you say you have better look angle from the ground compared to satellite look direction?
Well, so the next step, and actually I should say there is a CCN of the ESA Modulate project running, so we actually continue and we hope to do some measurements with the drone. So with the car, you're of course constrained to the road, so there's usually shadowing issues, so you don't, as you see in this example here, so you don't see those areas up here, whereas from the satellite you can see them. So I think there's no general answer to that. The regulatory constraints are high, but if you manage to fly higher with the drone, for instance, you can see that, but usually you are not allowed to because it's 120 meters above ground, unless you have a special permit, but we are not so far yet. It's also in Italy, so we want to fly in Switzerland first because we have to do Carniata stuff. We can do that, but it's not the first thing to try here. Yeah.
So max 120 meters, good to know. Thank you.
120 is the regulatory constraint.
Good. Thank you very much. I think we can close the session. Thanks again, Otmar. Just to thank all the speakers and all the participants to the session, we remind you there will be the round table for this session today in this room at 5:50 p.m. Here is half an hour. It's the role now of the conveners just to find out some seat questions, but we hope you will join us in this round table to discuss the main points that were coming out from these presentations. Thanks a lot again, and have a nice lunch.
Yeah, Mr. Chair, you're getting
Ja, jetzt geht's los.
difficult here.
Aber, okay, das ist geil.
Introducing
They see you. Okay. Okay, ladies and gentlemen, I want to welcome you for this first afternoon session on ice and snow. So Bernd Scheuchel from Urban University and myself, we are chairing this session. And there will be two sessions. So this is the first part of ice and snow. There will be a second part after the coffee break. And I think you expect a couple of very, very interesting talks. And the first talk will be given by Jan Voite on monitoring ice velocity and discharge with SAR satellite missions, present capabilities and future perspectives. Jan.
Hello, everyone. Yeah, very happy to kick off the first talk of the thematic session on snow and ice today. So the presentation I have today complements the presentation that Thomas gave earlier in the week in the Sentinel-1 session. So I'm going to present and give an overview of the work that me and my colleagues at Envio have been doing in the framework of the ESA, CCI, and Polar cluster projects and Copernicus Climate Change Service. And I'm going to talk about our work on the ice velocity and ice discharge from SAR satellite missions. First, I would like to acknowledge my colleagues, Thomas, Marcus, Brian, and Helmut. So most of the products that I will be presenting today are coming from Sentinel-1. Sentinel-1 does not need an introduction for this audience, but the mission has now been active for more than 11 years, more than a decade, almost 12 years actually. And it has really changed the way we can look at the polar regions. And one of the very unique aspects is the systematic acquisition planning in the polar regions. And this ensured that we have continuous observations of the Greenland ice sheet, in particular the margins, and also large parts of the Antarctic margins. And this continuous acquisition has actually enabled us to set up automatic system for retrieval of ice velocity for ice dynamic studies. And yeah, so what you see here is the coverage of the Sentinel-1 interferometric white swat mode data. And this is actually the primary data product that we use for ice velocity retrieval. And you see the evolution of the data coverage throughout the last 11 years. You see changes caused by the acquisition planning, but you're also visible here in Greenland. You see a reduction in the coverage when we lost Sentinel-1B, but an increase again in 2025 when Sentinel-1C was back up and we were back on a 6-day repeat pass. Also in Antarctica, you can see that most of the margin was covered, but the interior ice sheet up to the polar gap was only covered once, several times in 2015, but after that it was not covered. So Sentinel-1 has acquired a wealth of data, and we used it to make ice velocity maps of the polar regions. Not just Greenland and Antarctica, but also subantarctic islands, South Georgia, with the Patagonian ice fields, Iceland, Svalbard, and also Russian Arctic, Canadian Arctic. So we've processed all this data and generated an archive of ice velocity maps for these regions. Here you see the Greenland ice velocity map. This particular map is, so this is based on Sentinel-1 SAR data. This particular map is based on offset tracking data and covers the period 2014 to 2024. So this is a multi-annual velocity maps. And this is provided at 250 meter, and in total, about 55,000 Sentinel-1 SLC products have been used and processed to generate this particular map. You can see very nicely in the interior of the ice sheet, this dark blue band is the ice divide with very slow velocities. And you see the fast-moving outlet glaciers at the margins, some of them reaching up several hundred kilometers until the ice divide almost. And you can see here on the right some close-up of some glaciers on the east coast and also on the west coast, and also ice velocity of Zermatt-Kujalleq, or also Jakobshavn Glacier, which is one of the fastest flowing glaciers in the world. And sometimes it reaches velocities up to 50 meters per day. So in Greenland, we have annual winter mapping campaigns that cover the complete ice sheet already since 2014, and this enabled us to make nearly gapless ice sheet-wide velocity maps. And these are the annual maps. You can see here we have about 11 maps in the meantime. And also we have generated monthly ice velocity maps. These do not all of them cover the interior, but they cover the margins where the most dynamic changes occur. So the development of this processing line started in CCI, but now the production has moved over to the Copernicus Climate Change Service on the cryosphere. And there are products available on the Copernicus Climate Data Store, but we also provide velocity products on our own cryoportal at NVO, and these are all freely available. I should say that the main method for you making these maps are offset tracking. So the high density of data enables us also to look at time series of velocity measurements. So this shows velocity along fixed point of several glaciers over the last 15 years. And you can see that the data very clearly resolves seasonal fluctuations and also longer-term trends. And this also enables us to look at, for instance, velocity anomalies. You can see that in this plot on the right. You can see annual velocity anomalies relative to the longer mean 2014-2024. And with this, you can actually see where glaciers, where something is going on, if glaciers suddenly speed up or slow down. So this is a very nice tool to look at this. It has also enabled us to look at ice discharge. So ice discharge is a very important parameter for determining sea level rise, the freshwater flux in the ocean, or the mass balance of the ice sheet. And the main input for calculating the solid ice discharge is actually the velocity maps. The discharge can be calculated from the product of the velocity and the glacier cross-section at the specific gate. And so to calculate the ice discharge, we have set up an automatic system which uses our velocity maps and combines this with ice thickness model from that machine. And this week, and then we have selected more than 250 marine terminating outlet glaciers in Greenland. And this was done manually close to the calving front, as you can see here in this image. And so we selected these flux gates all over the perimeter of the ice sheet. And I should say that the ice thickness we also correct for surface elevation change. So this shows some example of this. You can see here at the top 3 figures for Petermann Glacier, Academy Glacier, and Narsap Sirmia. You can see the cross velocity profiles. It is colored, and also in gray, the ice thickness. And at the bottom, you can see 3 time series of ice discharge. So this is at a monthly basis. And you can very clearly see that each of these glaciers has a distinct discharge signal or pattern, with also peaks in the early summer and drop-offs. And besides telling something about the discharge, it also tells us something about the subglacial drainage network and how it evolves from an inefficient distributed network underneath the glacier to a more efficient channelized system during the course of a melt season. So this has a lot of information in there. Yeah, so this now shows the ice discharge on a monthly basis, summed up for individual drainage basins. So the colors of these graphs, they correspond to the drainage basins in Greenland. These are the main drainage basins. And the black graph shows the total ice discharge of the entire ice sheet, which is plotted on the right-hand axis. And this shows also very clearly an annual pattern with peaks in the early summer and sharp drop-off afterwards. So what we see is over this 10-year period, an increase. I've plotted here a second-order trend, but we find an increase in this last 10 years in the order of 6.5% in ice discharge. Yeah, now moving to the other pole. This is over here. You see a velocity map of Antarctica. This is also a multi-annual map with a zoom in here on the Antarctic Peninsula, which also very nicely shows all the outlet glaciers coming from the high plateau in the middle, draining towards the sea. So this product contains actually more than 100, is derived from more than 100,000 Sentinel-1 SLC products. But for Antarctica, we have also produced annual maps, just like Greenland, and also monthly maps. Yeah, a specific thing to think about in Antarctica is that we have a lot of Antarctica's fringed with floating ice shelves. And this heavily affects the ice velocity retrieval. Because of the nature of the side-looking geometry, a displacement in the slant range direction on an ice shelf that moves often up and down is either over or underestimated, depending on the loop direction and the tide level. And you can see the effect of that on a profile that I took along a glacier on Larsen C ice shelf. And these are velocity profiles based on 6-day repeat pass velocity maps. And you can see very clearly that there is this large shift, and this is due to the tide. And this is caused by ocean tide, but also by pressure differences. And to get rid of this effect, we have developed a processing line which corrects for this. And it uses as input state-of-the-art tide model, as well as ERA 5 atmospheric pressure data. And so our processing line computes with this information the vertical displacement on the floating ice and corrects for this. Where the ice transitions from grounded ice to floating ice, we apply an elastic beam model to ensure a realistic transition from grounded to floating ice. And this takes into account the flexure of the ice shelf when it starts to float. So to illustrate the improvement, wait, I should go to the next one. Yeah. To illustrate the improvement of this, we plotted a histogram and a map with the residuals, and this is derived from subtracting a longer term average map where we assume that the tides have been cancelled out from these single repeat pass velocity maps. And what you see here in the uncorrected version is that you have this bimodal distribution with one centered close to 0, which is representing the grounded ice, and the other one is a peak which is coming from the floating ice. And this is also very clearly illustrated in this plots at the bottom, where you see a distinct difference between the floating ice of Larsen C ice shelf and the grounded ice in all these three figures. And then this is after the correction, you see that we don't have this bimodal distribution anymore, and the long-term average map very closely resembles the individual's 6 or 12-day velocity maps. Yeah, so this now shows velocity profile of Pine Island Glacier. This shows velocity profiles on a monthly basis since 2015. And this shows the ice discharge. We calculated also ice discharge for the glaciers in Antarctica. And so Pine Island Glacier is one of the largest glaciers in Antarctica. It's draining a large part of the West Antarctic ice sheet. And what we see in our data is that this glacier shows a near linear increase in velocity over this full time series. And we calculated this to be close to 20%. I'll go to the next one. Then before I come to my final slide, I just wanted to show you something that if we've been looking at, prompted by the laws of Sentinel-1B, we also started to investigate synergies with other satellite systems, also looking ahead at future upcoming and new L-band missions such as Roselle and NISAR. We started to looking at synergies with L-band data, and we looked at SAOCOM data, so that's the Argentinian L-band mission, to look at if we can use this together with Sentinel-1. So this shows for this region in Antarctic Peninsula velocity map. And this is from Sentinel-1 offset tracking. Then this shows actually the SAOCOM results, also from offset tracking. But when we look now at fringes, you can see here Sentinel-1 with very nicely developed fringe patterns, but we are losing fringes here at the fast shear margins, but with With SAOCOM, it's very dense, but we have very clearly defined fringes even in the fast-flowing part. And we use this data together with the Sentinel-1 data to make an INSAR velocity map of this region. And you can see it very nicely, much sharper than the offset tracking results. But we are missing here a part because we are missing Sentinel-1. And then we can still fill this in when we assume that the flow direction is constant by just using this to scale the INSAR line of sight direction from SAOCOM. So then my final slide, key take-home message is that Sentinel-1 fundamentally changed the way we were able to monitor the ice sheets and ice cap by systematically acquiring dense time series of SAR data in the polar regions. And if you want some more information about what I presented today, I would like to refer to you to my paper, which we published earlier this year, but also you can send me an email.
Thank you, Jan.
Yeah.
We have time for one or two quick questions. Paul.
Do you know what radar mode the SAOCOM was using in this slide that you showed?
What was it? The
strip map.
Yeah, I think strip map. Yeah.
Strip map mode. So this was strip map mode because TOPS mode was not.
Yeah, I mean bandwidth, noise equivalent, sigma naught, that kind of thing.
The bandwidth I don't know, but noise equivalent sigma 0 was below -25, so it was working out quite nicely there.
Okay, thank you.
But bandwidth I don't know. Sorry.
Okay, yeah, thanks. Very impressive results and good work. I mean, over the whole time, right? 10 years and more. Independent, if it's not Greenland or Antarctica, very, very great. My question is a little bit velocity. I think it's something that is quite well managed up to now. I think that's great. What I'm a little bit worried is about this discharge. And my question is because you use a model, right, in order to get the thickness. And the question, and the question a little bit is, at least our experience is that if you do a model-based thickness estimation, it's not so accurate, and it's varying a little bit. The question is, do you have checked how accurate is this model in order then to estimate the discharge, or is it the error bars that you have on a discharge? Is this already included, the errors of the model?
Yeah, correct. Actually, most of the error is coming from the model. The models that we use, they include also error estimates, and we propagate this. So the ice velocity is only a small error, small part of that. Most of it's coming from the ice thickness. But there have been several initiatives in the last couple of years to improve the ice thickness, such as in Antarctica, the RINGS project. So we are waiting for the data for that, and yeah, this will improve the discharge.
Yeah, the question is also if you would have other parameters that we could estimate it. For example, just using DEM differences, right, in order just to see. It's a question, right? I think what could be interesting to check, cross-check what you can get out of this, which are then data that we have, right? It's a data-driven approach then, and not a model-based approach, but could be also interesting.
Yeah.
Just as a suggestion. Great, thanks.
Okay, so there is time for more questions in the coffee break, but we have to go on now. And I want to introduce the next speaker, which is Bernd Scheuchel. So Eric was unfortunately not able to come, but he will give now the talk on behalf of him on the early results with NISAR, Sentinel-1 CD, and ICI in Antarctica. Please, Bernd.
Good afternoon, everyone. As I said, this was supposed to be Eric presenting. He was kind enough to prepare the slides for me. We will be talking a bit about grounding line mapping, based also on a recent publication from our group. I will show some examples with ICI, the capabilities of which we found really intriguing, and we sort of continuing working with that sensor. We show some first results with NISAR. I'm very excited about this mission. And obviously the Sentinel-1 1D mission was something that we are thankful to ESA for not doing this once, but twice. And we hope that every launch sort of will include a little phase where we have a one-day campaign in the future. So yes, launches are spaced widely, but I'm really hoping for that. So Jan already introduced the area of interest. We're working mostly in Antarctica, although we do some Greenland work. In addition to measuring ice velocity, we can also measure the grounding line. That's the boundary where ice meets the ocean. And the way to do this is to use the tides. We're not correcting for tides. We use the tides to isolate the vertical motion and have this fringe pattern, a dense fringe pattern that allows us to delineate the grounding line. Doing grounding line measurements more than once, sort of that happened more recently with sort of ongoing acquisition campaigns. And with ISA, we have daily acquisitions. Allowed us to see that we have short-term migration of the grounding line that's tidally driven. In this case, this is Thwaites Glacier. Jan already also in West Antarctica mentioned. The red lines are the grounding lines. Sort of, this is an ensemble. The width of that band is the ice grounding zone that has an impact for melt of the ice, because majority of ice melting is subglacial melt. That's sort of warm ocean water reaching the ice shelf and melting the glacier from underneath. And we also found evidence that ocean water is intruding past the grounding line, and sort of these are these orange and green lines. One of the colors is in sync with the tide, and the other color is out of sync. So we have evidence of intrusion of warm water, but we also have evidence of subglacial meltwater making its way to the grounding line, and I will be talking in the afternoon on the latter. So the grounding zone delineation with INSAR is essentially by measuring a bunch of grounding lines in short order and basically taking the width of this. I mentioned interferometry revealed intrusions of seawater that are kilometer sized. The grounding zone itself has an impact of subglacial melt. Here's a paper from one of our recent graduates. And the intrusions happen where the water pressure gets close to the ice overburden pressure, where we then have basically an impact on the surface of the ice. And what's really impressive, what I find still impressive, is in this area, the ice is about a kilometer and a half thick, and we are measuring centimeters of lift from space. This is just this intrusion signal again, but I'll switch to the next slide. This is sort of the summary of the recent publications where we took the satellite record of grounding line measurements and look at 30 years of glacier grounding lines, monitoring and looking at retreat signals. Antarctica has lost about 442 square kilometers of grounded ice in the 30 years. It turns out that about 3/4 of the coastline is very stable, but where it is not stable, retreat can be up to 40 kilometers. These products are available at the National Snow and Ice Data Center. We have the grounding line as well as the ice grounding zone. Here are some examples. The color shows sort of the year of acquisition, and what these plots show a bit better is that we have more acquisitions in later years. So with the start of the Sentinel era, we had sort of ongoing campaigns instead of acquisition, one-off acquisition campaigns every year. That meant we have a lot more acquisitions that allow us measurements. Therefore, we were also able to then map the ice grounding zone. Here are some comparisons between the ERS era, sort of one-day interferograms for 2 glaciers. One was Verdi, and then ISI in 2025. We had a collaboration with ISI that showed us the capability. We were sort of early adopters of their INSAR capability. We then pushed to make this data set more broadly available by going through the NASA third-party purchase program. So that's a CSDA program. And we did receive a data quota for that. And as we were working on this paper, we had the flexibility to fill some coverage gaps where we hadn't collected grounding line data in many years or never. Some more examples, comparison again, ERS and ISI. This is not the example, here's the grounding line for recovery. And a first example with a NISAR grounding line. We still have sort of a fair bit of ionosphere, but the signal is strong enough. The differential tides in the area are quite good, so we have a strong grounding line signal, and we're quite excited about the availability. I will show a mosaic in a bit that just shows the coverage. NISAR will cover Antarctica pretty much back to back in ascending and descending. So for grounding line measurements, we have coast-wide coverage, and for velocity measurements, we have essentially ice sheet-wide coverage every 12 days in ascending and descending mode. Another one, support force, never mapped with INSAR. That was essentially decorrelation, just bad luck, or mission not being available. And again, very nice differential tide signal that gives us this very typical fringe pattern. And again, very excited about this. If you read support force, there's sort of a little bullseye. That's sort of an indication of subglacial water upstream, but that's not sort of an intrusion, in my opinion. That's more an example of subglacial water making its way to the grounding line. Here is an area that has less differential tide, so that's where L-band has a minor weakness, I would say, where the sensitivity, you have fewer fringes for the same tide compared to a C-band or an X-band radar, but the correlation is excellent, and even with this, we have a good sense where the grounding line is, and we can work with that. The NIT-7, that's just a GPS station that we put in for NISAR Calval. And it was a lucky streak because this area is less affected by an ionosphere. We have 5 more stations near McMurdo, and that area happens to be a lot more affected. Going on to Sentinel-1 1D. Very excited about sort of this 1D mission, even though it's not even a one-off. I can't call it a one-off because it's the second time we've done it. But it's a fantastic mission, and I will also show some results in the afternoon. Pine Island tends to decorrelate with many missions. That's why we also have an ongoing ISI campaign with 1-day repeat orbit, but Sentinel-1 also covers it. Thwaites, again, this is the main trunk of Thwaites, is decorrelating a little bit. That's the area where we have high-resolution ISI coverage. But again, pretty much well-covered, a very difficult glacier with Sentinel-1 1D. Our product line also includes a reference map, sort of as much coverage as possible with as many data sets that we can get our hands on. We then also had sort of period reference maps, maximizing the coverage while limiting the observation period, annual maps, and we will be releasing soon also monthly maps. Our reference map is built on phase analysis, INSAR phase analysis. Jan also already alluded that phase is much more accurate measurement. This is a hybrid map where the fast glaciers are based on speckle tracking, but the interior is mostly on phase, except that this data set, the collection was about 5 years. In order to get as much covered as possible, we included data collected over 20 years. With NISAR, again, ascending, descending coverage every 12 days. So this will change the game fundamentally. Here is just a mosaic. It's incomplete, part our fault, part just the mission not quite having collected everything, I believe, and there is a gremlin or two still in the system that will be worked out soon. First, ascending, descending velocity map. This is the region near McMurdo's Bird Glacier. And so we are developing the capability to use NISAR. The other advantage that I wanted to mention is NISAR is a mission that produces level 2 products. So the heavy lifting of speckle tracking and things of that for ice sheet will be done by the project. So researchers can then take those products and do the final analysis at a lot less computational cost. And here's some monthly maps, just an animation for Pine Island and Thwaites. We talked a bit about a little bit of evidence of seasonal variability, not as pronounced as in Greenland, but there has been evidence on the peninsula for seasonal variability, and it looks like we're seeing some of that. So all in all, the Sentinel-1D mission is excellent for grounding line mapping, and it will also be a boon for phase unwrapping of fast glaciers. I want to mention that ISI provides essential information for the fastest moving glaciers. We have currently 3 stacks running, one for Pine Island, one for Thwaites, and one for Denman Glacier. These are not replacing any agency mission. These are augmenting, and we're trying to carefully use the resource to fill in data gaps that just happened because of the way the missions are designed. NISA provides continent-wide coverage, and already I showed some results of never mapped before grounding lines, mapped with INSAR, I should say. And the combination of the sensors will provide us sort of an opportunity to do a phase-only ice velocity map of all of Antarctica, which in principle should be 10 times more accurate than a speckle tracking produced product. With that, thank you.
Thank you, Bernd, for this very nice overview presentation. The floor is open for questions. Okay, Dirk.
Thank you for the presentation. Missions like ICE-I have issues with the perpendicular baseline, so I'm wondering if that is an issue for mapping the velocity in Antarctica, because they are not. I mean, these missions do not necessarily have a small perpendicular baseline by default.
So we started using ISI for grounding line mapping. That was sort of the initial intent. We are slowly moving into looking into also velocities for that. For grounding line mapping, there is no alternative for these fast glaciers. And having daily observations, I will talk later in the afternoon in the second session, I will show a result where the daily observations really make a difference. So from that perspective, it's a real resource. On the velocity side, we haven't really looked. Daily has some disadvantages because, you know, within a day there is the signal to noise is not ideal. And I call them the postage stamps, so the area coverage is quite small. I would argue placing that postage stamps in the right spot still makes a huge scientific difference.
Yeah, similar question. You mentioned it already, the posting stamps. What is the area extent or the swath width of the ISI?
I think the product is 50 by 70 kilometers. We have a representative from ISA in the room. Correct me if I'm wrong. 30 by 70 is, I think, the formal, but the scenes are a little bit larger, if I remember correctly. Yeah. But we found sort of in Greenland, so the first test run that we had was Petermann Glacier in northern Greenland, and that covers the glacier nicely. In Antarctica, we fill some really, some real gaps, and the size, yes, would we want larger scenes? In principle, yes. Can we work with what we have? Absolutely.
Okay, thanks.
Okay. I have also a question for you, Bernd. NICE is very interesting. You showed a few examples. My question is related to this overall coverage. Did you already look to the interferometric pairs, which are really not affected so heavily by ionospheric that they can be used for ice velocity, also for unwrapping? Because you mentioned NICE here for grounding line, but not directly for phase velocity.
The one example I showed with the velocity arrows, yes, that was a nice example.
But for the Thwaites Glacier, this example in Pine Island, what you showed, if I remember right, there was a lot of ionosphere in there.
So Thwaites Glacier and Pine Island are special cases. The current plan has a mode that's, it's a very, very radar dark or L-band radar dark area. So we experience a lot of noise, and the mode has a relatively high noise level. So the cryoscience team made a recommendation to switch to a different mode, give up a little bit of resolution for 3 dB gain in noise level. So we are quite hopeful that this will resolve things and give us the opportunity to use that.
And how many pairs do you need to test in order to get a good example like you have shown there for the
well, right now, you know, we're working with what we have, so there's a few data available. The JPL team is kind enough to work with us, and sort of, because we're on a science team, we have some privileged access, but it's also more, you know, we are also the people who are supposed to sign off on yes, the data meets the quality criteria.
And which strategy are you actually going in order to correct for the ionosphere? Using the
so I can refer to a JPL colleague who is in the room if he wants to speak up on this.
Okay. Ionosphere was the question. Which strategy are you actually going in or planning to go in the polar regions in order to correct for ionosphere?
So at the moment, we're using split spectrum techniques, and that's it. And there are residuals. Some of the co-registration algorithms to deal with the azimuth offsets that are quite strong in those regions. We're experimenting now with the best approach, but probably we will need eventually to develop something like the multi-squint approach that ESA's using for biomass, I suspect. At the moment, we're not doing that, and the first products that we'll be releasing will likely have some of these artifacts in them.
Well, but in terms of, to mention one thing, the ascending-descending coverage affords us the luxury to throw out the azimuth offsets and use range for a velocity map.
Yeah, the offsets can be thrown out for use per se, but it doesn't fix the
it doesn't fix
the phase issues.
sort of
Yeah, I was talking about,
remnants
I mean,
imaging.
the,
Yeah.
the claim here is that you're going to be making phase-only maps everywhere, not use speckle tracking. So the idea is to make the phase as accurate as possible. And it's still a little bit of a research project, I'm afraid. But fortunately, the ionosphere is getting less severe as time goes on. So maybe by the time we figure it out, there won't be any ionosphere to correct.
Okay, that's a fantastic strategy. That's fine. But anyhow, we have to go on with the next talk. It is given by Jacob Connolly. He will talk on a decade of Antarctic calving front measurements using a weekly supervised natural network with automated pseudo-labeling of Sentinel-1 data. Jacob.
Thank you. Good afternoon, everyone. So I'm going to present some work we've been doing to train a weekly supervised neural network. Okay, thank you. To delineate calving fronts in Antarctica, so focusing on the Antarctic Peninsula using Sentinel-1 data. So the main reason for using weekly supervised machine learning is trying to overcome the barrier of creating training data. So creating accurate training data is quite time consuming, essentially having to do it manually. So if we can do that somewhat automatically, then we sort of overcome that barrier and we can create a much better model. So we're focusing on the Antarctic Peninsula, and the reason is because calving is a major component of ice loss in general, but in the peninsula it accounts for 14% of ice mass loss between 1992 and 2020. And across the whole of the peninsula we have intense atmospheric and oceanic warming. So it's quite complex behavior and a lot of sort of small tidewater glaciers. And this project is part of a bigger project called Polar Mints. So it's polar ocean mixing by internal tsunamis. And the focus of this project is to understand the role of when a calving event occurs, so an iceberg falls into the ocean, it causes an internal wave in the water, which promotes mixing in the water and melting and so on. It might contribute to the glacier changing more rapidly. So we're focusing on Ryder Bay in Antarctic Peninsula. So this is part of Adelaide Island. It's a tidewater glacier. So this is Rothera Base, and then the sort of Ryder Bay is this part here. Towards the top left of the bay is Sheldon Glacier, and that's sort of the main test site so far. And really this is because it's a fairly simple glacier in terms of there's nothing particularly special going on, which makes it quite a nice test case for this work. Also, we have access to do in situ measurements through the research station there. So there's a whole team, part of Polar Mints, doing field work to get data on what's happening in the oceans as those calving events happen. So as I mentioned, manual delineation of calving fronts using SAR is time consuming. It's not really scalable for a global time series data set. So historically, it will have been done manually, but we're sort of transitioning to lots more machine learning models that have been developed to do this automatically, both sort of supervised machine learning, but then also unsupervised and sort of foundation models and things like that. So here I'm just showing some of the manual delineations that we use for validation from method. And we've got manual delineations for 2015 to 2024 for this Sheldon Glacier. So machine learning is really where this can help. But again, there's still an issue with creating all of the training data. So we need quite a big volume of training data to create a good enough model to be able to delineate this sort of thing. So the question I'm trying to explore is, can we use existing data sets to sort of take a shortcut and create this training data? So here I'm showing a coastline data set from NERC and British Antarctic Survey. So NERC is the National Environment Research Council in the UK. And this is created from a range of sources, primarily remote sensing between 1973 and 2025. So obviously, plenty of it won't be accurate anymore. Sort of the timescales of things changing in the cryosphere can be much less than 6 days, never mind 50 years. But the point is that this gives us a starting point to try and create some training data that we would have to do manually otherwise. And the colors on here, so darker lines are sort of more historic data set, and the lighter lines are more recent measurements. So weakly supervised machine learning uses inaccurate training data. So this could be incomplete, so only some of the training data has labels. Inexact, so it could be quite coarse. You could have just a simple label for a small region of an image and not the entire thing. Or it could be inaccurate, so the labels that you've given to an image are no longer accurate, or you're sort of not 100% sure that it's a pure class that you've labeled. So throughout this, we're using Sentinel-1. Really, the primary reason is because we can get year-round monitoring, but we also have this long time series. And without Sentinel-1 and sort of the work being done for future missions, we wouldn't be able to do this sort of study. And so we're mostly looking data and we're decoding it on 20-meter grid. And that's to sort of try and give us the best chance of getting a good delineation. So obviously your delineation accuracy is sort of bound by whatever resolution imagery you're using. And we're using the Basque Coastline dataset to create the training data. So going into the machine learning model, we have tiles of about 1024 pixels square. So it's roughly 20 kilometers by 20 kilometers. And we clip the SAR imagery between -25 and 5 decibels. But for the labeling, we use the BAS dataset to create an ocean polygon and an ice or land polygon. And then in between, we create like a buffer zone. So this covers the coastline plus minus 150 meters either side. And the point of this is to try and mask out the sort of ambiguous areas where the coastline has actually changed since the coastline dataset was originally created. And so the model will be evaluated on the areas that we know are, we're fairly confident that they're actually ocean or actually land or ice. And we don't evaluate it against the areas that we're not 100% sure about. And then roughly we have 25% validation and then the rest 75%. So this initial study is more of a proof of concept, so it's a relatively small training data set, covering 2 years of Sentinel-1. But because it's relatively automatic, it will be quite easy to scale this up to a much high volume of training data. So we're using the UNet++ architecture. So many of you might be familiar with the UNet. So a standard UNet is just these black circles here. And so your image goes in, it gets downsampled, you learn from it, and then you sort of upsample it into your original resolution, and you're sort of assessing how well you're doing each time. And then this is your model. A UNet++ is the same, but you have dense skip connections in the U part, so it's filling in the gap. And this prevents fine details from being lost, so it's particularly good for SAR data, where we want to retain all of the information that we can as it's being downsampled and upsampled. And this has come from medical image segmentation, so a lot of medical imaging is very similar to SAR data. So it deals with similar things like speckle, and so really it's quite well suited for what we're doing here. And the model is pre-trained, so it's using the ImageNet weights, and this is a model that's trained on millions of photographs of sort of everyday things in RGB. So although it might not have an idea of what glaciers are and what they look like, it has a decent idea of what an object is and what an edge of an object is and things like that. And the encoder is the ResNet 34, so essentially it has 34 layers, and it means it's got plenty of chances to sort of learn the finer details and sort of get past the noise and speckle of the SAR data. And training is split into 2 parts. So the first phase is training it on despeckled data, and the second part is the non-despeckled data. So it's sort of a curriculum learning approach where you give it slightly easier data to learn from. And once it's got a decent idea of what it's looking at, it can learn from the sort of more complex data. So as I mentioned, it's 2 years of time series, and then 150 meter buffer around the coastline. The validation data is a separate tile, a Sentinel-1 tile, so it's not part of the same training data, it's geographically different. And for the training, we're using NVIDIA A100 GPUs, so we can use a batch size of about 16 and 40 gigabyte VRAM, so that's a few hours of training, which is relatively quick for this sort of model. For phase 2, for the non-despeckled data, because this data is more complex, we lower the learning rate to give it a sort of more chance to try and learn what we're trying to show it. So this is initial sort of binary output from the model. So you can see left is the SAR MLI that goes in. This is the segmentation that comes out with a threshold of 0.5 on the probability output. So you can see it does a fairly decent job overall, but there are some issues where sort of inland, it's classifying it as ocean, sort of this top part here, when it's definitely inland. And similarly, sort of some of the smaller glaciers that you might be able to spot in the top are being classified as ice or land. But overall, it does a fairly decent job, and especially of our sort of test case site, it gets the shape quite accurately. But it does still struggle, so particularly surface melt and sort of sea ice can sort of obscure what we're trying to make it learn. So here, this is our rider base, our glacier carving front, and then all of this is sea ice, and then we have a very dark ocean. So this is very confusing to it, but then we also have this very dark ice as there's melt. So you can see that the model actually struggles quite a lot to find where the carving front is. You can see that in this sort of backscatter dropping. So this is an inland area, and then seaward, it's very noisy. So because of that sort of struggle to capture the sort of shorter term variabilities, it can do fairly well on the temporal variability sort of seasonally and yearly, but it does struggle sort of acquisition to acquisition. So hopefully you can see that this black line here is the manually delineated fronts. So this is data that we've done ourselves manually. The dots are the machine learning output fronts. And then this red line is like a smooth version of those dots. So it does capture the temporal variability, and we do get fairly accurate in some places, but yeah, all of these results up here are a result of getting confused, of going too far inland or seaward. And so you can see that in the machine learning fronts here, there's high density of fronts where they should be, but there's not. There's also fronts either side of it as well. And this is the manual delineation here. So yeah, the key takeaway is, I think existing data sets can be used to minimize manual labeling for large-scale machine learning applications. So particularly this sort of application where otherwise we'd have to label an extensive data set ourselves. We can use existing data sets to sort of take a shortcut, and we can capture this sort of seasonal, yearly variability, but it still struggles with the sort of finer temporal details that we would need to be able to feed into sort of more complex work like the modeling of the oceans. So the next steps would be to improve robustness of summer melt conditions. We're doing this by incorporating temporal information. So at the moment, this is just a snapshot. So each image is evaluated individually, has no concept of time really. So we've developed a second model that is using triplets, so 3 images, and then evaluating it on the central image, which does do a better job, but still more work needs to be done to make it a sort of operational product that we can use to generate mass and energy flux, and then go into the work with polymids to understand ocean mixing. Yeah, thank you very much.
Are there any questions for the speaker? If not, I have a question. Have you considered sea ice conditions as input for scene selection? Or are you using just any old image that's available for you?
Yeah, so at the moment, any image. I've experimented with using like clustering approaches to try and cluster the ocean polygon and land polygon separately to get an estimate of how much sea ice there and how much variability in the sea there is. And that can help, but the idea of just using any image was to sort of try and make it more globally useful.
So your system is set up for Sentinel-1, did I understand it correctly?
Yeah.
Have you tried other SAR missions, just out of curiosity?
We haven't. We've got access to some eyesight data, so that will be used for validation, but we haven't used it to sort of train or evaluate it against that.
Okay.
Yeah.
Thank you.
Thanks.
Let's move on to our next speaker. This is François Charbonneau from the Canada Centre for Remote Sensing, and he will be talking about the characterization of ice cover composition with pole INSAR and SAR tomography.
Thank you. Good afternoon, bonjour. Like I said, sorry. So we'll talk about ice cover characterization from pole INSAR and SAR tomographic acquisition for ice road monitoring. I would like to acknowledge my co-author, Joost van der Senden, with his more than 15 years of experience in sour lake ice and river ice monitoring. On my side, I'm pretty new about ice. I'm just giving some help to Joost about SAR, pole INSAR and tomography. So what is the motivation behind that is in northern Canada, there's some area where there's a lot of mining industries and some remote communities, but three-quarters of the time during the year, there's no road access to those areas. So during the winter, they built road over a frozen lake in order to provide machinery supply for the mining industry, fuels, and also to bring back the mineral resources to the processing facility. So you see the kind of road built north and they built on the ice. And our so current methodology to monitor those ice roads is mainly in situ monitoring. So it's a lot of time consuming and it's expensive and things like that. So my colleague Joost, spent a lot of time to understanding that with classical SAR processor and polarimetry, but still not all the full information there. So the study site I was looking at today is that area here, close to Yellowknife. The main project goal in terms of trafficability point of view is to estimate the snow ice layer thickness, because the snow ice is weaker. They cannot support a lot of weight compared to clear ice. But for this presentation, I will more focus on information about INSAR stuff. So since I'm new on INSAR, so not on INSAR, but on ice, was wondering if there's enough INSAR polarization diversity with a really thin layer of ice. We are talking about meters, 1 meters of ice layer and some meters. And also in terms of tomography, can we distinguish the volume scattering center against the ice-water interface at the bottom of the ice? So the project has been supported by fieldwork that has been performed in 2019. The sites were preselected related to polarimetric data analysis a month before. The kind of measurement they have done, they took some ice core, and take the profile, thickness, and the type of ice, impurities, and also some snow thickness characterization and directed constant stuff. And also some GPR measurement by walk, and also some by GPR on helicopter. That field campaign is supported by a DLR airborne perma-SAR campaign conjointly. DLR flew their FSAR system at the three bands, X, C, and L, in fully polymetric configuration. And so they did a transect, Pauline-SAR transect with a 15-meter baseline, the green one here. And also they did tomographic, two tomographic transect, one with 7 baseline up to 100 meters, and the other one with 6 baseline. So they have been covered, 21 sites here, and also 11 sites here in tomographic things. So the yellow line here is the helicopter GPR, and the one is the work. So in the type of area, there's different type of ice cover. On the left here, you have the snow ice. Snow ice in terms of polymetric decomposition, it's more a volumetric scattering. There's a lot of air in that layer, so it's called white ice. So there's a lot of volumetric decorrelation. While on clear ice, it's more react like a surface scattering mechanism. And here there's a bubble ice, they call. So there's gas emanation from the bottom of the lake, and the gas is trapped in the ice column. So that creates some bubbles in it, and that creates some kind of even band scattering, but this is debatable depending to who you talk to. And also lastly, there's the ice road here, where the see some more dense ice, because there's one way to do that, they kind of spray little goutlets on the ice road in order to having a bit of bounce between the ionic molecule, so it's a much stronger ice. So here kind of sample my colleague have collected. So the thickness, the ice thickness goes from the 50 centimeter to 150 centimeter. And we have some good columns of bubbles here and some snow ice here, good thickness. And we have the snow layer here. And the blue one is the slush ice, the man-made ice that we got. So why we are getting things complicated, with Pauline-SAR and tomography, Why not simply use polymetric information? Well, okay, there's a lot of dots, don't try to analyze that. There's a different polarization here, and then we plot against the thickness of the ice. Yes, we see a trend here, but other than that, it's not really clear. Yes, we can use polymetric decomposition, surface versus volume to try to highlight that. Okay, good, we highlight that trend here. But it's not clear for thinner ice and also for thicker ice. We have the same profile here. Okay, so and even if you look at X or C or L band, you have the same kind of trends, and with a weaker slope for the X band. Okay, now if we bring the single polarization in SAR, as we know, we are able to get good mapping of the scattering center, at HH or HV at C band, and same thing for HH and HV for X band. The road are pretty stable, closed, and some special differences. And in case of X band, here the HH is still a bit noisier than HV, but I didn't apply the additive filter, so it could be a good result too. But if we look visually, the difference between HH and HV here, visually, we don't see that much change, It's not sure if we have real difference, more information. So if now we take the HH differential against minus the HV differential, then we can highlight now the variation of the scattering center between the two polarization. And this is what you get at C-band, we highlight the border of the road, which, they are more bumpy and more icy. And also at L-band, what's nice, we see we see that also at C-band, but we highlighted some feature that were not visible, on the top of the ice and on classic differential or on the intensity things. Okay, so what we can get from Pauline-SAR? The point about Pauline-SAR is you create your your differential coherency matrix, and then you play with the transmission and reception polarization configuration here. This is your INSAR coherence matrix, and then you play with transmit and receive. So they can generate all the possible coherence for all possible polarization. And here, and we can display that on the unity circle color plot, where the range is the amplitude of the coherence, and then the phase of each polarization. So all the dots here are different polarization that you can use, but also you can use the maximum coherence over the range of phi angle. And when we see that kind of line here, we are thinking, okay, this is more a random volume over ground model, so can roughly easily estimate the height, or the thickness in this case, of the ice. But when we are diverging from that line, we are not talking about random volume anymore. It's more, could be oriented layer, thing like that, and multi-layers thing. We need to be careful. And for L-band, okay, in this case here, the points are really tight because this is the 15-meter baseline. But if you use the 60-meter or 100-meter, then you can stretch that line and you can do your inversion. Honestly, it has not been successful for me for now in terms of inversion because it seems not really follow the random volume over ground anyway. So for thicker ice, so when we increase the ice thickness, we see an evolution of that copol diagram. But again, we are losing that that information about the homogeneous volume. And we can see, usually the HV is the most volumetric component, should be at the end of that line. And here we see this is more in the middle here instead of being the minus coherence. And so there's an impact of the difference layer. And you see here some bubble example, and here with more snow ice example. So that's have an impact of the amount of coherence amplitude. So then what we can get from tomosar? There's different technique. There's a lot of technique about tomographic SAR. I took the most common one is the high resolution beamforming one, Kaplan one. As you see on the left, it can define pretty well the scattering center, and also, okay, this is height here and a sample range here, center range. You can have, kind of spectral information about the ice thickness here, what's happening in the column. While the music is the multi-signal classification, which is based on the number of sources of scattering, if you need. So you need to define the number of scattering you're looking at before, doing the inversion. In our case, okay, you can speculate easily that this is mostly a 2 scattering center. So that's helped to have a better definition of the line, but we have losing some information about the top and the bottom. So now, for in the real case, this is a classic column of 400 centimeter. So on the top, you see HH and HV. So you see quite well-defined line for the middle scattering center, while but a little bit from the bottom here. But if you're looking for the right-left polarization, which is more sensitive to surface scattering, then you see 2 layers here, which is a scattering center from mainly the volume, and this is from the bottom of the lake ice. And for HV, in this case, it's only volume scattering, and in this case, right, and HH minus VV is relatively stable. So as you can see here, this is the vertical profile at the middle. So you see most of the polarization are aligned in the depolarization component, while the right, left, and HH pop up a little below for the bottom of the lake, at the ice-water interface. Okay, now if we add some snow ice on the top of the ice, so we see, okay, it's a bit more fuzzy in HH and VV, and also, right, left is not clear as before. But what seems to be interesting is there's a little shift here. I need to understand what's happening there compared to the other polarization. But the right left is clearly show the bottom. Okay, what about the bubbles? So we are losing the two layers. Okay, this is a short layer. It's only 60 centimeters. We are losing the two layers separation of the volume center and the bottom of the bubble. Even with the right-left. But what is interesting is the increase of diversity for HV and mainly for right and HH and HV, which are related to double bonds in the theory. And you see that the double bonds appear here below, on top of the surface scattering here. And so that will stimulate a little bit the debate about, is it really surface the interaction of the bubbles with the source signal. So if you don't believe what I just said before about the scattering mechanisms and what's happening, you can use polarimetric decomposition. The classic one is the H-alpha decomposition, where alpha refer to mainly from low alpha is surface scattering. When you increase, you're going to the even bounds, double bound stuff. So if we take a previous example where we have the volume scattering here and the surface, and we can show that, during the low alpha part, that match clearly the bottom of the interface of surface, the ice and water interface. And then we can do the same thing about the bubbles, where you have the bottom of the interface water ice here, and where we said that that was double bond even bounds, we have increase of the alpha that match quite closely the things. Okay, now we saw those little profile. They're kind of bumpy, and is it real? Is it a processing problem I have? Is it noise or something like that? Then I said, okay, what about looking about horizontally those slices and see how the scattering evolve, the scattering center evolves. So this is an animation from a minus 100 centimeter and go up above the snow. So you see the evolution of the scattering mechanisms when you go up and you reach the main scattering site. What is interesting to note is when you look at the road ice here, that match here, you see that the volume scattering center have been raised. Even if it's the deeper part, the volume scatter is higher, probably due to different denser ice things component. Then we can do the same thing by using RGB composite. Putting the surface scattering right, left, and done. Yeah, and on top in the animation, and you see the progression from the bottom is blue, and then you reach the volume scattering part, and then a little bit more surface scattering on the top, and then disappear. So go up, and you can see again the surface scattering and the volume scattering here on the top and on the bottom, at the interface. So, in conclusion, gladly, that the polarization, there's enough phase diversity in the polarization. Sorry, I'm stepping on the wires. Sorry. Then yes, it would be nice, but it would be more complicated than I had expected, since it seems to not follow a random volume things. Need to be clear here. X-band, I have a problem with it, but it's for single pole INSAR, X-band is going well. My colleague Jos with TandemX is a real lover of TandemX, is getting great results with lake ice. But for pole INSAR and tomography, it seems to be too sensitive. And for tomography, yes, I'm surprised. I'm surprised, and at some point, I'm really glad that there's possible to discriminate those kind of layers, even if we are talking only a 1 meter layer step. So the next step is looking more physical modeling. And I would like to acknowledge the DLR because those FSOR data are amazing. I mean, there's a lot of potential to do with that. Thank you.
Thank you. Are there any questions for the speaker? Irena, no question. Okay. So I have one question with respect to, you showed that you can extract some results. What's sort of the monitoring aspect for this? Is it the strength of the ice road, or?
There's the political aspect, economical aspect, and the sorry. If I understood correctly your question, why doing that, and is it feasible in long term doing monitoring with that kind of technique? For me, okay, pollen soil will be feasible to some point if we can increase the spacing, with the baseline. Presently, with the spaceborne mission, is too difficult. No, sorry. We need to be more, and in terms of tomography, then we cannot do that with biomass in a way that doesn't go over our site with biomass. So, for me, it's more a scientific challenge. The real story is, I was looking for a challenge, and my colleague has a beautiful data set in hands. Was sitting under his desk and say, "Oh, can I try it?"
Yeah.
But no, I'm just starting. I start last fall.
No,
So
sometimes.
Sorry, this is too
Yeah.
low quality, but.
Sometimes that's the way to go. Thank you very much again. Another round of applause for the speaker. Let me introduce our final speaker for the session. It's Malte Vöge, who will be talking about operational INSAR monitoring of land-fast sea ice extent and dynamics.
Okay, yeah, thanks for the introduction. I'm giving this presentation on behalf of my colleague Dira Daman, and of course also on behalf of the other co-authors from NGI and from the Norwegian Meteorological Institute, and also from Alfred Wegener Institute in Germany. Let me go back here. So this presentation is about a project called IceView, where we develop an operational Sentinel-1 based INSAR monitoring of land-fast sea ice extent and dynamics. So first of all, what's land-fast sea ice? So it is not free drifting ice, but it is ice that is somehow mechanically linked to the shore. This might either be, how does the pointer work here? Oh no, there's a separate one. Sorry. So this might either be through like grounding of the ice, as it is indicated here, or it might be due to the shape of the shoreline, that sort of like the piece of ice is linked with the shore like a puzzle piece, like puzzle pieces are interlinked with one another. So why is land-fast sea ice critical in Arctic region? So it's of course critical for like shipping, to like optimize routing for vessels, evaluating port access, logistics for operations from sea to shore, military train refueling, industry. Of course, you might have like industrial operations on the ice or offshore. Also, again, like important to have port access. Tourism might be important. Governmental interests could be in the sea ice forecasting for those stakeholders, but also, not the least, social components that, like ice roads that we've also seen like inland in the presentation before, might also be interesting or important in the coastal regions for Arctic communities or also for native communities. So the mapping of landfast sea ice with INSAR is not new. So we are not the first ones to do it, of course. So it can be mapped with INSAR because it is mechanically linked to the coastline. So we only have slow movements, and we can get a coherent interferometric phase. So drifting ice we will not map. So we only get the landfast ice which we want. And from the phase gradients, which I will show, we can get important information about the dynamics within the ice. So our target area was primarily Svalbard. So it's an archipelago between the Norwegian mainland and the North Pole. It's part of Norway, regulated by the Svalbard Treaty from 1920. Has about 2,500 inhabitants and approximate sea ice season from October to June. For our study, we used all three available tracks of Sentinel-1. That's 2 ascending and 1 descending, with a mix of 6 to 12-day revisit time. In total, we processed 10 years of data now from 2016 to 26. Focusing on the period from November to May. The workflow that we used is a quite classic interferometric workflow. So we only do a single pair interferometry. Here, as an interferometric engine, we use IC2, the TOPS app workflow, which goes through the regular steps from merging frames. So we as we see here already in the interferogram that I'm showing, we merge all the frames that we find for one track. So the TOPS app also identifies common bursts, co-registration, and so on, until we get a merged interferogram for all the bursts. So the first crucial step here is the filtering of the interferogram. So here we, just as a starting point, we see the amplitude image already cropped out, in this case on the side here, the land. So we see a fjord, which is on the western side of Svalbard. And on the right-hand side, we see the pure interferometric phase. And we can clearly already see that we get quite nice fringes, although still a bit noisy. So in order to get a good coherence or improved coherence, we filter it with a Goldstein-Werner filter. We use a quite large FFT window of 256 pixels and a very strong filter coherence, which gave us the best results. So that means we have a good we receive with this a good separation between seawater, floating ice, and land-fast ice, meaning a good difference in coherence, which we will see on the next slide, and also a stable basis for calculating strains within the ice. However, a little bit of a problem with this large window is that we get these boundary effects in a way. So like the phase, the very strong or coherent phase from the land sort of like leaking into the sea. And we get like this stripe of, say, apparent ice, which we would, thresholding this by the coherence, which we would falsely interpret as ice. In order to mitigate that, before we apply the Goldstein-Werner filter, we mask the interferogram by basically setting the complex values on land to 0. This gives us this kind of interferogram, which of course has like these artifacts now on land. However, these artifacts are not important for us because we are only interested in the seawater area. So we can simply crop this out, which leaves us then with a quite nice, nicely filtered and clean interferogram, which has no unwanted effects where there is no landfast ice. Okay, already spoke of coherence. So the coherence is, of course, the measure for us to distinguish landfast sea ice from either floating ice or water. So coherence in our case is estimated by or from phase variance. We detrend the phase locally in this process to get rid of these. If we go on back, we have these very high fringe densities here, which we have quite often. So in those cases, the phase variance can be biased, reducing the coherence, and to mitigate that, it's locally detrended, then resulting in a much better contrast of coherent and not coherent areas, distinguishing landfast sea ice from water. Next, we are calculating strain, again from the local phase gradient. We're doing this now just for the coherent areas, so we're thresholding by coherence and have here now already cropped out the not landfast sea ice areas. So on the right-hand side, we now see the strain, which is, of course, only like it's the minimum possible strain that we get, because we do not get 2D measurements. We only have the measurements in the range direction. So this is just like a crude estimate of the actual strain, but we can regard it as like the minimum possible strain. Also, we have projected the phase to the displacement from which this is calculated to the horizontal component, so that we now call it like a ground range strain, indicating that it is horizontal and in range direction. But still, although it is not the real strain, this gives us information about mechanically active fractures. And also it gives us a lot of valuable information about regional differences in ice stability. The next step in our workflow is simple geocoding, and in order to, because we want to have one seamless map for the landfast sea ice, we have to somehow merge these the information from the 3 tracks. After geocoding, we interpolate them all to a 30 by 30 meter resolution grid indicated here by the red frames. So all these products are now geocoded and within the same kind of reference grid. Then taking these 3 maps that we've shown, that we see in the last slide. So we kind of stack them here, and now we start producing the actual map. So we take the first product that we have from 23rd of March to 4th of April. Then we take the next one and just superimpose it onto the map, overwriting sort of what's already outdated, because this is the newer acquisition or the newer interferomantic pair. Then we take the next one of track 14, which ended up here, again overwriting even more of the older interferogram from track 155. So, but you will see that now we have mixed a product of a 12-day interferogram and of 2 6-day interferograms. Of course, the strains that we calculate from those are not quite comparable, because in the one that we had double the time to accumulate strain. And therefore, we normalize this to you see, like a ground range strain rate. So this would be then, it's centimeter by kilometer strain per day. So this gives us a strain rate independent of the temporal baseline that has been used for the specific product. Now going forward in time, we will see that, well, it takes a couple of days now to actually get to the next available interferometric pair. So basically just stepping through the days here, we do not have any change. But now we see that on the 30th, we run out of the range of this interferometric product here. And so then we take the next one, which would go from 30th of March to 5th of April, and do the same thing again and overwrite the previous data. And with this, we always update to get a continuous time series. And that's basically the entire workflow. So here we see now the preliminary results. This is exemplary from the winter season 19 to 20. This is now a time lapse with monthly snapshots. So we actually see that already on the 1st of November, we already have some landfast sea ice. It's quite a bit of strain here, less strain inside the fjord, which makes sense. But then it also vanishes again, so there must be some fluctuations. However, here we have emerging ice. And then in starting with January, we get much more ice, like here, a big piece of landfast sea ice. Also the fjord that we've been looking at previously fills with landfast ice. But again, some fluctuations. March to May is usually the highest ice coverage. Like here in May, also here in the north, we have a fair bit of ice. And then at the end of May, actually all the ice already vanished. One remark, these are preliminary results. So one thing that we've noticed is that we have a slight shift in the data due to an incorrectly referenced height model, but this is only a couple of pixels and does not seem to affect the results itself. So again, back to the 1st of April, which is a nice example. Here we can also see like one thing we have to notice is that also like in a fjord, we might have gaps in this landfast sea ice, which is a little bit counterintuitive as one would expect this completely filled with ice. But it might also be snow cover, which is causing decorrelation or other effects. Just here, zoom in into this large sheet with very low strain, but we still see some interesting features here, which might obviously also be some kind of height variations that we obviously cannot cancel out from the interferogram, as we do not have that kind of information. Okay. We also did this for other areas. Here is an example from Barrow Point in Alaska, where we see, just very quickly, a very high strain, especially here at this tipping point. I would say like where one would expect a lot of currents. This part here is a lagoon, so it's natural that we have very low strain here, but also on this side, here we have a patch with a lot of strain. So then we also did this in the Gulf of Bothnia, which is wedged in between Sweden here and Finland here. So not open to the ocean in that sense, very sheltered, so less currents to be expected. And subsequently, we also generally see much less strain in the ice. So this would be from February 26, and also from also a nice example from the Caspian Sea. Similar, this Caspian Sea is of course not has less currents because it's not an open ocean, and subsequently we have less strain in the ice, very low strain here. Okay, back to the Svalbard example. The good thing about our 10-year data set is, of course, that we can do some statistics. So very quickly, we here, this is the maximum ice extent count. So, so that means how many seasons have shown ice at a particular pixel. So which gives us a likelihood of seeing ice at some point during a winter at this location. Here we see the onset of the landfast sea ice, so like the first day when we observed ice. Particularly early seem to have been the season 19 to 20. In the later seasons, we see relatively late onsets, but also generally less ice in total. Yeah, this is just a decadal strain distribution, like on fixed dates. And you can see that early on in the season, we might see a bit broader distribution here, like more strain, but this is something where we're still looking into. Which leads me to my conclusion. So IceView provides a complete automated solution to map and monitor landfast sea ice. We calculate proxies for strain and strain rate, which gives really interesting valuable insights for the dynamics within the ice. The decadal data set is a not yet fully utilized basis for investigating the behavior and evolution of the sea ice over time. You can see these preliminary results for Svalbard on the ESA Carillion Information Factory. You will see here the QR code. It's planned to implement IceView into the Norwegian National Ice Service, which will be very exciting. And regarding future plans, of course, we want to extend IceView to further regions, and not mentioned here, but obviously also NISAR will be really interesting to be integrated into this. Okay, thank you.
Thank you. Thank you for this talk. There is time for a very, very quick question. Jan? No, take the microphone.
Thank you for the presentation. I think this would also be very interesting for Antarctica. Do you have any plans to extend this to Antarctica as well?
Yes, yes. Just not come to do it, but we're planning to do it. Well, obviously a good candidate is near the Norwegian polar station. But we're open to suggestions if there is some particularly interesting place that would be interesting to hear.
Irina?
Yeah, thank you. It's very interesting and very, great examples that you have. My question was a little bit into the direction how you can separate really the contribution that you have from land, so from fast ice, so land fast, and sea ice in general, because probably it's very difficult to separate them, specifically if it's stuck somehow. It's not easy, right?
Well, if it's stuck, then actually we would still consider that other part also landfast, because it's like then mechanically connected and it's only slow moving. But obviously like really free drifting ice, we get no coherence at all, because it will be in a different place in the two acquisitions that we analyze. So that is a clear separation.
Okay, good, thanks.
Thanks. Okay, one more question, Franz.
Yeah, I mean, the benefit of NISAR is that the base data you need is already there. So there's the GUN-W, the interferograms exist. I don't know if there's a wrapped phase layer in there too. But it would be interesting with the data that exists now to see if your algorithm to get the strain rates would work out of the box.
Yeah, that would be really interesting. Regarding the wrap, so we're actually working on, we don't do unwrapping because that would, first of all, add quite a complexity, and you will have in the landfast sea ice still quite separate pieces of ice that and the motion in between those is not that interesting for us. It's really like the strain and stress within one solid piece of ice. And for that we only really need the local phase gradient, and for that we don't unwrap the phase.
And I think the wrap phase is contained in the
Okay.
HDA5 file, so you should be able to just. So there are sample data sets around right now that we've already looked at, so it might be worth.
We'll definitely
just
look
trying
into
your-
it.
Yep.
Thanks.
Okay, now I have to say that we have now the coffee break for half an hour. Use it. We will come back at 4:10 for the next ice and snow session with very, very interesting talks. And afterwards, we have the discussion where we prepared a couple of key questions for you. So it's your opportunity to shape the future and to give input to ESA for the near future. So please come back and discuss it with us. Yeah, now a good coffee break. Thanks.
Looking mission and perhaps less that works. Yeah, the other ones are again, out of reach. Okay,
Later. 1, 2, 3. Yes. So welcome to the second snow and ice session for this afternoon. And we will continue with cold things to talk about. You will see snow, maybe also some permafrost. And for the first speaker, I invite Gökhan Aslan to open the floor. He will talk about operational INSAR monitoring in the high Arctic, the INSAR Svalbard ground motions service.
Okay, yeah, I can see clearly, yes. Hi, everybody. Good afternoon. My name is Gökhan Aslan from Geological Survey of Norway, and today I will introduce you INSAR Svalbard, a new ground motion service for Svalbard. This service was launched in February this year in Svalbard, and it has been developed by NORSE in collaboration with Geological Survey of Norway and Norwegian Space Agency. It's an open access service based on Sentinel-1 SAR products for selected areas in Svalbard for now. So how we move here? Okay, yeah. So the first question: why monitor ground motion in Svalbard. Svalbard is one of the fastest warming region on Earth, and the Arctic is warming about 3 times faster than the global average, and Svalbard here is a kind of hotspot. A certain part of Svalbard is warming up to 7 times faster than the global average. So, of course, this warming is changing the permafrost condition, and then permafrost thawing, it also causes permafrost thawing. It leads to ground instability, and it affects the infrastructure and contributes slope hazard in the region. So as you see in this example, on the right side, there is this type of large debris flow occurs more frequently due to increasing global warming in this region. This is the typical permafrost valley landscape in Svalbard. If we take a cross section through this one of the valley, like this here, we can start to understand the process that drive the ground motion. So here, ground dynamics in Svalbard or in any Arctic region is controlled by several factors like climate, vegetation, snow, sediment, rock, ground temperature, and of course, how much water and ice present in the soil. So all these factors together control seasonal movements such as frost heave in winter, thaw subsidence in summer, or slope processes, different types of slope processes. These are very subtle movements, but very widespread all over Arctic region. These movements are important for 2 different aspects. From research perspective, they are valuable to know because they tell us how the terrain is responding to the changing environment, changing climate condition. And from a management perspective, it is also valuable because it affects the stability of the structures and in certain cases contribute to slope processes. So that's why it is important to better understand those processes. Okay, there is something wrong, just a second. Okay, yeah. So of course we can measure these movements using different type of measurement technique, in situ measurements or field mapping, or underground investigation like geophone or boreholes. Of course, this gives a precise and important information in the local scale, but they are very local. So this is where INSAR becomes valuable to monitor the larger area. So in this area, Sentinel-1 provides ascending and standing with multiple overlapping data coverage. And when it comes to a timeline of the data, the resolution changed from 12 to 6 days depending on the availability of the Sentinel-1 units. So the lower panel actually shows the timeline window of the INSAR Norway, not INSAR Svalbard, but the similar logic here in INSAR Svalbard. So in INSAR Norway, we have different time windows, that's sliding time windows. Every year we process the past 5 years with sliding 1 year, but in INSAR Svalbard, this is not the case. Here I wanted to show, since because of the snow coverage, we don't use the whole data, only snow-free data we can use, as you see here. So this is also the case in INSAR Svalbard. So most of you might be familiar with EGMS and INSAR Norway platform. INSAR Norway is an operational ground motion service. It was launched in 2018, and since then, Geological Survey of Norway, we and some other state agencies, we are using it actively to monitor the unstable slope, rock slides, different types of periglacial activities, permafrost in the high Arctic and over entire mainland of Norway, and also anthropogenic activities. As you see here in the panel, in the figure on the left side, following the launch of this service, the total identified total number of unstable slope is just increased dramatically. And still we are, every passing day, we are identifying a new unstable slope to better understand. So, and beside this, there is also EGMS, as you well know. But in these two services, Svalbard is missing. Of course, there are two main reasons for this. First of all, there is a unique technical challenges that require different processing strategies that we don't face in similar challenges in Europe, in continental Europe. And also there are different user needs and communities that require tailored product types here in Svalbard. During the development phase of this product, of this service, there were 3 years, during the first 3 years, there were close collaboration with the local stakeholders in Svalbard. We organized regular meetings and listen what they need, what type of problem they are facing there. So during development, it has been their needs has been considered during the development phase. This WebGIS platform, and I am sure you are familiar with from EGMS and INSAR Norway, the same WebGIS platform, but only designed for INSAR Svalbard. For now, there are only 5 selected pilot areas. And these areas were selected based on different criteria. There are main settlements in those sites, research stations, cultural heritage sites, and of course, scientific activities. There are 2 types of product type here, seasonal and interannual type. I would like to draw your attention to the figure in the center that shows the permafrost change during the one permafrost season. In the early spring, we see a permafrost layer and active layer. As temperature increase, we see how active layer starts showing the decomposition due to the melting. And then in late summer, this melt shows its maximum. And with the winter, the heave season starts and it again goes up again. And this repeats itself during the observation period. So in the seasonal product is tailored to identify the deformation that starts with the thaw onset, between thaw onset and freeze onset. Only this pattern of movements we want to identify during the seasonal product. And in long-term interannual product, we see the more long-term trend of the deformation. So that's why in this service, there are two different products that complement each other to understand this type of phenomena. Also same for sloping terrain. Okay, this is from the same region, that shows 2 different products view in the platform. Upper panel shows the seasonal products. In the seasonal product, each point shows the maximum displacement that we are observing here. Oops. Don't press black button, and I pressed. Okay, I thought it's a pointer.
No, the pointer is like this.
Okay. Like this, okay. So in this first seasonal product, we visualize here the maximum displacement. If I go back, this is the maximum displacement for each time series in the seasonal product. This is what we visualize. And in the interannual product, we calculate the long-term deformation, and here we see the longer-term velocity pattern. So they are in different color scale and in different also color palettes. So that's why there is a difference between 2 deformation patterns. When we look a closer look here, again, I will take this pointer. Again, from the same region, in the seasonal product, it is only from one snow-free season within 5-6 months period. If we take time series from two different points, for example, this little polygon within this blue point, we can see how this seasonal pattern is behaving. So the maximum value here, like maybe 80 millimeter per year, is visualized here. And in the green point, we have more stable in the beginning, and then it shows a bit acceleration, and its maximum value here. Then what we show here is more 10 millimeter per year. So it's an absolute maximum displacement in the seasonal product. And each year processed separately. In the server here, we have for each year separate product. So they are not connected to each other. Okay, now when it comes to interannual product, again from two different, when we take a time series from two different points, we see the long-term deformation pattern, which shows this time interannual product between entire, which is here 7-8 years long, entire snow-free season, how the deformation trend is changing. One example just to verify, to validate this measurements. So this example, this shows the one on the upper panel, shows the 2-meter depth temperature measurements of one of the sites. And it starts from April till September, till November. And we can see in one borehole which time of the year and which depth shows the active layer feature. And the panel in the middle shows the ground surface temperature. And the last panel, it shows the deformation obtained from INSAR. As you see here, when it starts active layer start melting, we see the deformation goes down, subsiding, and when it shows its maximum at the end of the melting season, late summer, and it again starts with the heaving, it starts again going up, and here we can't see anymore how much it goes because of the snow cover. Again, this is one example from a seasonal product. In this platform, WebGIS platform, when user activate all the seasonal layer, they will see the time series like this all together, but actually each of them are independently processed. They are not connected, and each of them start with the first acquisition. So this might be misleading when users activate all layers. Here, what's interesting, we can see the seasonal product each year shows different pattern. Of course, this is controlled by meteorological factors every year. And also the acquisition frequency, acquisition density is also different from year to year. That's why in some years we have much less points that represent the seasonal product of the relevant year. As you see, in some years we see the full coverage, and in some years we only see the subsidence part. And also another example from Longyearbyen in Svalbard. This shows the permafrost creep in one of the area here. This is mining dumping area. It also creeping. This is the seasonal product. Just to show this, I prepared this animation to easily explain this behavior. So here we have the seasonal product. Of course, during this blue area where we actually have a gap, we don't have any measurement. If we assume there is a permafrost degradation or long-term subsidence here due to the different factors such as permafrost degradation, so this figure shows seasonal product plus long-term interannual product visualized together. Okay, what is INSAR not measuring here? Of course, the results are spatially discontinuous, and in some areas there is no data. That doesn't mean there is no movements. In some areas we have shadow That's why we can't see it. And due to different reasons, as most of you know, we can't see the deformation. We can measure it due to the loss of signal, due to high rate movements. The green, for example, shows loss of signal stability due to or bias due to the snow cover, and dark blue, glaciers. Some of the glaciers are not reported in our database. There are several studies published from this region using this product before the product was released. I will share with you some of them with you. This is a hotspot analysis again from Longyearbyen in Svalbard that identifies all active areas, permafrost, intense permafrost areas, slope processes, solifluction, rock glaciers. Again, this is the valley in Longyearbyen. In front of the Longyearbyen here, we can see also different features, morphologic features shows a different velocity in 2 minutes. Okay. In lowlands, the amplitude. Another study shows the comparison with ground type. In lowland, the amplitude and spatial distribution of the seasonal signal aligns with the sedimentary type because different type of sediment have different ice thickness and frost susceptibility. Another study using the borehole from the same area and compare what we have measured from INSTAR, what is calculated, and what is modeled, and this shows the correlation between two data sets, how well they are correlated. Same study. I will skip this. Same. Okay. And again, this is also hotspot analysis of the entire one of the study area that shows slope movements in one of the region in Svalbard. And this example is from mining pile, seasonal product. All seasonal products are visualized together. As we see, it is more linear movements during the seasonal period. And there was another project to map the susceptibility in Svalbard, in Longyearbyen, where we have more cultural heritage buildings, structures. And this project's output is here that shows which building or which cultural heritage sites are affected by permafrost and its classification. Potential application areas of this product, of this service, include permafrost tolerant subsidence, ground ice distribution, terrain stability for assessing the terrain stability for infrastructure, slow-moving slopes, monitoring them, and mapping glacial forefields, evolution and sediment dynamics. And next development stage includes extending to larger areas, more pilot areas, or if possible, to the entire Svalbard, including other product types, and refining the process strategies. And thank you for listening. Yeah, that's all.
Thank you for the interesting presentations. We have time for one short question. This does not mean that there's no question. So at least one, please.
Improvement processing strategies. Are you using this specific product that we are making available that we call the ETAD for Extend Timing Annotation Dataset that would allow to reduce the error bar in your measurement, which is pretty short in time?
I don't know this detail. I am not in the development team, so that's why I will not be able to answer.
Okay, we can discuss later. Then.
Yeah.
Maybe I missed it, But what's the reason that you have these 5 focus areas on the map?
They are selected based on different criteria, like that we should have some construction, some interest, like cultural heritage, scientific activities. Some of them are already known phenomena, so that's why they are selected strategically.
Okay. Yeah, thanks.
Okay, so thank you very much. We have to move on. So I invite the next speaker is Marisha Jumkatze. She will present something on the assessment of season-dependent Sentinel-1 SAR coherence reliability in freeze-throw dominated terrain, a case study on Long Brian.
Thank you. Good evening, everyone. My name is Marisha, and I'm very happy today to be talking to you about our research, which is about the effects and the influence, basically, that the seasonal Arctic conditions can have on the Sentinel-1 SAR coherence reliability, specifically on Longyearbyen case study, which is in Svalbard. And our study is actually very closely related to and addresses the complementing question of the previous very interesting presentation, by the way. And the question being, before interpreting basically absolutely any deformation results, we need to know just how reliable is the underlying radar coherence that even enables these measurements to be possible to begin with. So to investigate this, what we did with my colleague is we investigated the Sentinel-1 data and analyzed it from 2019 to 2021 period and basically investigated the behavior of the coherence and evaluated how this coherence behaves specifically in the Arctic conditions, as you can see in the freeze-thaw dominated terrain. But before we start speaking about the results, I think it's really important to understand why even Arctic conditions can pose a challenge for INSAR and Sentinel-1 generally. To put it very simply, coherence, what it does is it measures basically or shows just how similar the radar signal remains between two satellite acquisitions. And as you all probably already know, in the Arctic region specifically, the surface conditions are constantly changing. For example, freeze-thaw cycles can alter, and then it causes to alter the scattering conditions. There's snow that can accumulate, and then it melts away and creates these mushy ground instead of like very solid ice. And that obviously can affect and does affect the coherence generally. And as you can imagine, the decrease in coherence obviously leads to the decrease in the confidence in the interferometric parameters and measurements, which we obviously do not want. And so for this reason, I'm going to repeat myself that basically understanding the behavior of coherence is, you can easily say, one of the first critical steps that we need to take before we even start speaking about the interferometric results and the products. Moving on, as I already mentioned, our study specifically focuses on Longyearbyen, which you probably have heard of. It's one of the northernmost towns. It's a very, very beautiful town in the Svalbard archipelago. And this region is amazing because it contains not only constant permafrost, but also has seasonal snow coverage, as well as exposed water and rock bodies, and just generally very variable environmental conditions. And because of this contrasting surface types, we basically end up with a wide variety of radar signal scattering possibilities and conditions. And that basically makes Longyearbyen an ideal and pretty logical place to understand and observe and learn and investigate and analyze the behavior of coherence. And of course, one of the biggest advantages also that Longyearbyen offers is that it has a long archive of Sentinel-1 data, which basically allows us to experiment and analyze multi-year data and analysis, as well as investigate different cases in different environmental states. Here you see on the screen the research objective, more or less, and we wanted to demonstrate in the simplest way possible what the workflow looks like, more or less, with this very simple diagram. As you can literally directly read from the screen, we started with a Sentinel-1 SAR imagery, moving on to the coherence maps that were generated, and then the reliability assessment, and then, of course, the seasonal comparison, which means that we took the data that we got from the multi-year analysis and then compared them side to side and decided how they varied from each other in terms of coherence, not only in terms of years, but also obviously seasons, because our main focus was on winter and summer to simplify the case, but of course you can work on other seasons as well. When it comes to data and methodology, what we did is, of course, we used Sentinel-1, but in terms of product types, we applied the single lock complex product, or SLC for short, which you see on the screen. And SLC is great because SLC data basically retains the phase information, which is required in order to for interferometric processing and coherence estimation. We also use the interferometric wide swath mode, or IV for short, and then the HH type polarization, again within the period of 2019 to 2021. And also, it's important to note that we process the image pairs using the consistent six-day temporal baseline. This is a more in-depth, I guess, a diagram to show what the workflow looked like. What we used also, I forgot to mention, is that we were working with ESA's SNAP software workflow, and we were using that to generate the coherence maps. And initially, what happens first is that you take these two Sentinel-1 acquisitions and then you load them into the system, and then you apply the appropriate and adequate orbital information. Using back geocoding and enhanced spectral diversity, you basically end up generating the interferogram. And then using things like phase removal and multi-look, which multi-look, for example, removes the speckle noise, if I pronounce that correctly, speckle noise. And so we end up with the interferogram maps, which, as a result, help us analyze the behavior as we move forward. Now, this slide basically demonstrates the analysis, more or less, of the image pairs that we have analyzed over the years from 2019 to 2021. As you can clearly see, maybe I'll use the laser, but you don't really need the laser, but obviously the highest peak or mean coherence that we've had or found in our study was in 2020, where the coherence was approximately 0.51, which isn't necessarily the best coherence that you can get, but what we decided with our research, obviously one being, for example, the perfect coherence, 0.5 and above would be considered usable, and you don't need to necessarily proceed with caution, as opposed to if you were to get coherence 0.3 to 0.5, for example, you would consider this data reliable, but you would proceed with caution, of course. And so overall results suggested that Sentinel-1 observations remained reliable for the monitoring purposes in the Arctic environments. And also, one important thing that I need to mention is that for our study, specifically for our coherence values, we used the filtering mechanisms and filtering algorithms in order to mask the water bodies, basically, to get the coherence to be as clear and clean as possible, and exactly what we needed. Generally speaking, to understand the observed reliability, we also need to talk about and understand and learn the physical processes occurring on the surfaces. As you would know and assume, in the winter seasons when you have a solid ice, solid ground, you have the radar signal scattering almost perfectly, or at least better than compared to summer. And generally speaking, winter does have a or favors stronger coherence, as opposed to summer, where, like I already mentioned a couple times, when the snow starts to melt and the ice starts to melt and you end up with this mushy texture, the radar signals scatter in multiple directions, and also the soil moisture density is very variable, so that affects it as well. And you end up with much lower coherence. But it's not one of the most interesting things that we found in our study is that even though you would expect, okay, winter has great coherence and summer has lower, it's not necessarily that, because you can't observe and understand the behavior of coherence solely based on seasonal parameters, because there's so many other things that affect coherence as well, like the snow condition, the soil moisture density and content, and so much more. So that was really interesting to see. The difference between the winter and summer wasn't as dramatic as one would maybe, or at least we expected. Here you have a table which shows from 2019 to 2021 some of the data that we have acquired from our analysis. And as you can see, they all have the constant or consistent 6-day time period, as well as the different mean coherence values, even though some of them are in the same season. And again, this basically not promotes, but it reinforces the idea that the coherence isn't necessarily only dependent on the season, because you can see, for example, some of the image pairs, yes, they are both from winter, but they have different mean coherent values, and that's also really interesting, we found. And here you have another, I guess, table showing a similar thing, but here you have the more in-depth analysis. Again, we underlined, I guess, that in 2020 we found the highest mean coherence being approximately 0.64, so far at least that we've found, and 2019 exhibited the weakest annual coherence. Yeah, this is important because this is essentially what we were looking for to begin with. These are the coherence heat maps, and the purple that you see around, that's water, that's the water body. And like I already mentioned, but I'll repeat myself, we had to use some filtering algorithms in order to mask these to get a clear coherence. But here you will see better examples. I'm not sure if that's really visible, but we wanted just to show a couple more examples, this specifically from the summer coherence heat maps. Same thing here. I would like to also mention that the warmer colors indicate higher coherence and cooler tones are the lower coherences, and this is specifically for summer acquisitions. But what was interesting is that, like I already said, even though summer has the conditions supporting lower coherence, it was still interesting to find out that it doesn't necessarily mean that you're ending up with bad coherence, because our data suggested that it was at least moderate. So that means that the Sentinel-1 data can be used to conduct research and experiments and so on, even during summer times, and get great results, basically. And this is the same thing except for winter. And the winter coherence maps show generally stronger and higher coherence, as you would expect, because again, you have a solid ground and you have simply just the better conditions for the coherence. But even here, you don't get the perfect coherence of like simply one, for example, because we did find that in specific regions in Longyearbyen, in the same winter season, you did have different mean coherence values, which was also really interesting, and again, shows the idea that many things and many environmental conditions and the soil moisture and so on affect the overall mean coherence value. And another thing that we decided to include in our presentation is the histograms, which is just an alternative way, basically, of observing the coherence behavior. And this specifically is for summer coherence histograms. And on the axis you have the coherence, and on the y-axis you have the pixel concentration. And you see the distribution, and when it's shifted toward the higher values, it indicates a greater proportion of the stable scatterers. And you will see the similar histograms for the winter Here you go, winter coherence histograms, which again, as expected, shows that the winter conditions normally, not always again, of course, and not everywhere, show and exhibit just stronger coherence. And the winter, yeah, and as you can read on the screen as well, exhibits general stronger concentrations of higher coherence values. And just to summarize these two histograms really quickly, I already said this, but summer is more mixed. Winter, you have a stronger coherence, but again, doesn't necessarily mean that this is always the case. This is why it's so important to look into and analyze the specific separate acquisitions instead of assuming it's all bad in summer and all good in winter. It just necessarily doesn't work that way. And just to quickly summarize, it was really interesting actually to look into this research because I personally but recently got into it and am still very interested in this research. And I think it does have a big future because there's still so many things to learn and so many things to analyze. And even this, it might look like simple research, but it's important because obviously it lays out almost the foundation to some extent for future work. And if there are researchers that are looking forward to working in long year period, myself included, hopefully, you can use this research to basically proceed with more confidence and then higher coherence, if that's what you're looking for, which you usually are, would result in a higher or better confidence in the interferometric measurements. And yeah, overall, the Sentinel-1 SAR coherence reliability shows to be great, actually, in long European. And like I already said, we have multiple years of archive and data that support this. And now a little bit our research hopefully helps as well. So I hope I didn't miss anything. And thank you so much for your attention. And that's it, basically. Thank you.
Thank you very much. So, from the audience, some questions for Marisha. Oh, it's coming.
Hi, thank you so much for the presentation. I was just wondering, looking at the histograms, if you also compared what the actual weather was during the interferometric pairs, because January from one year is not the same to January next year, and the same with summer, so that could kind of be interesting looking into.
Exactly. Thank you so much for your question. I think that's a great question actually, because weather that seems like a simple idea, but of course, like you said, it definitely affects. In one day, you can have one weather, this next day completely different, especially in Arctic regions like long European. I was personally really surprised to see, of course, you expect like harsh environment and extreme conditions in Arctic regions generally, but especially here, you have to consider everything, I think. We did consider weather, but I think that because we're planning on moving on forward with this exact research and like learning more about it and hopefully doing as much research and analysis as we can, we were actually planning to do our next analysis specifically focusing on weather. So hopefully next time I'll have a better answer for that. But we did obviously take it into account to some extent, because like I said, just season isn't enough, and you outlined as well, isn't enough to learn the behavior of coherence. You need many things to look at. You can of course miss some things, but the more parameters you analyze and more things you take into account, the better results you'll end up with.
So, and essentially, with, I guess, accounting for, what do you call it, the variation for the exact day, what we did is that we calculated the average for in pairs. So essentially, we don't just present what's it like for one certain week in January, but essentially calculate the average from the beginning, two pairs from the beginning of the month for the 1st and 7th, for example, and also two pairs from the end of the month, 25th and Feb 2nd, for example. So
yeah, just have more variation. Thank you for your question.
Yeah, thank you for your talk. So often when we study the coherence over land, we use models, right, to help the interpretation. I was wondering if you considered models, models exist for the snow cover coherence models, or if you're planning to consider models.
We're definitely planning to consider it. Like I said, in the further research, we want to do a much deeper dive because I personally am pretty new to this research and I'm just getting into it and finding out how much more there is to it. So that is the plan, to be honest. Of course, we looked at the existing research and the models that are already there available to take it into consideration for our own research, but ours is still in the future.
Thank you.
Yeah, thank you.
So just to the last question, did you test already some of these models? Because according to my experience, these coherence models are not working.
Really? What do you mean by not working? If you
So we investigated the decorrelation due to snowfall, for example.
Mhm.
So for snow melt, it anyhow decorrelates completely. But for snowfall, to get a good estimate the rate of decorrelation due to the accumulation of dry snow.
Mhm.
So this is not really in the hands of the models yet.
Okay.
So that's my experience. So do you have any experience on that, or did you look to this?
Not exactly too much experience, if I'm completely honest. I would love to read your research as well, because obviously research is all about getting everybody's opinions and comparing the results. But that is very interesting. Of course, we did see differences in research in terms of coherence specifically, but what we found, at least from, but I also think that we didn't necessarily analyze too many years of data, so I guess that would also have an effect on it, because like I already said, we took 2019 to 2021, so I'm guessing that that would have also had an effect, right? Yeah, I mean, I would love to speak to you after as well, but I'm also wondering what parameters you utilize specifically that maybe we didn't apply at all to our research. That would be interesting. Yeah.
Yes. Sorry, we have to
Thank
go on
you
with
so
the next
much.
presentation. So thank you
Thank you,
very much.
everyone.
So the next presentation will be given by Carolina Gonzalez from DLR, and she will talk about snow depth estimation from SAR interferometry, and mainly addressing the SAR penetration and calibration challenges for accurate seasonal monitoring.
Thank you. Good evening, everyone. I'm going to talk to you about the research we have been doing on snow depth estimation from SAR interferometry. We are going to see how we address the radar penetration and the calibration for seasonal monitoring. We are trying to do monitoring of seasonal snow depth, and we're using tandem X data. And as we all know, this data is, INSAR-derived DMs are biased. Here we identify two critical error sources. One, the geometry. So due to the uncertainties in the baseline, we have residual offsets and tilts in the DMs. And we also have physical bias that comes from the fact that the radar wave penetrates into the snowpack. So we're using this very simple pipeline. So we have raw DMs, we mutually calibrate them, we compensate the penetration bias with a deep learning model, and finally we can estimate snow depth differences. So starting with geometric bias compensation, as I said, baseline uncertainties of about, so Tandem has a baseline accuracy estimation of about 1 millimeter, which when we translate it to the ground, we come up to several meters of tilts and offsets, so slow varying drifting in the heights. And let's assume this as a model of a transect. What do we see here? We can see changes, we see offsets, tilts, and we want to get rid of this too. So we only get changes. For this, we're calibrating the DMs mutually using natural tie points. What we do is we exploit Sentinel-1 repeat pass time series. We estimate the persistent scatter candidates, and from this we derived a set of tie points. And with these tie points and the DM difference between the reference and the target DM, we fit a calibration surface to remove these offsets. So here's an example. As I said before, I chose this example because it manages to capture all of the all of the things here. So we have tilts, offsets, and we have also changes. We have here two DMs. The overlapping region is the orange box. We estimate the tie points, calculate our calibration surface, in this case a plane, and then we get this calibrated DM difference. Here we can see that the distribution of the DM difference over tie points is zero-center, so we managed to compensate for the offsets very well. And we also see that the standard deviation goes, it's narrower, so we compensate for the tilts correctly. What we can see here is actually the changes, and this is due to the trees that have leaves on and off. I know this is not snow, but it manages to show what is the problem. So once we have compensated for the geometric bias, we go to the physical bias. When we are looking into snow-covered regions, the mean phase center is not equal to the surface. So the radar penetrates into the snow, and this is not a constant penetration, but it's influenced by the frequency, the incidence angle, and the snow characteristics, density, water content, etc. What we're doing is we're regressing this penetration bias from SAR features using a deep learning model. Every deep learning model is as good as its references, so we try to do this correctly instead of just doing a difference between the LiDAR and the DM. We account for the refraction using Snell's law, and we use different permittivity for the different snow phases. We also account for noise factor that comes from the temporal displacement between these two. So even if we have this realistic snow penetration bias references, we still don't have enough data to just go directly and regress this from our data, because it's not enough data. So what we do is we go for we train a deep learning model on semantic segmentation to learn or to estimate the snow phases. And once we have this running, we translate the weights into the regression bias task, so as a downstream regression task. The benefit of this is that it reduces the requirements of the data training and improves the convergence. We did a comprehensive testing on Greenland, where we have enough data for doing this. We tested different models and different input features and parameter sets, and in general, all of it. We settled with a CNN with doing multitask, so we're doing at the same time the semantic segmentation and the regression. But the most important thing here, or the takeaway, is that the pretext is the most important part of the selection of the model. We compare this to a physical model, and we can see here how it behaves for different height of ambiguities and local incidence angles, and our model manages to stay zero-centered and with a low standard deviation. We achieve 0.5 meter of a mean absolute error. Here you can also see the distribution. So what happens when we try to regress also in specific places that don't have exactly the same acquisition geometries, is that we are out of distribution. So what we do is we go for the approach of using this baseline model as a pre-training, and we fine-tune just the last, only the regression. And this is called regional adaptation for us. And here we have 2 examples in the Devon ice cap and the Aletsch glacier. I'm going to a little bit of details there. So we have here a time series with respect to November 1st, 2018. And we can see also a reference here that shows the accumulation of the snow. We can see that the uncalibrated, the raw DMs are just completely missing to follow the accumulation. When we look at the calibrated DMs, they're a little bit better, but the best, of course, is when we compensate for the penetration bias and the geometrical offsets. We have also done a geodetic mass balance estimation. Here we have the reference also in orange, and we can also see how it improves when we apply our complete chain. And finally, I'm showing here how we intend to translate from one band to other bands. So this is an example of how we plan to do this for from X band to C band. We are considering SRTM data in overlapping regions with tandem X with similar geometries, and we assume they locally they have similar bias characteristics. So first we do what I showed you before, so the fine-tuning over these regions. And then we use these weights to train, to make a supervised training with the features of XR. And then we estimate the bias of XR to correct the surface. And through the surface, we can then estimate the penetration bias in C band. And with this, finally, trained self-supervised the C band. Exactly. We also plan to do this with airborne in L-band data. Exactly. So, for concluding, the key is, of course, to divide this into different things. So first, we have to neutrally calibrate or calibrate our data, because if we don't do this, it's impossible to try to estimate any penetration correction. We managed to have a centimeter precision for relative snow depth with INSAR derived DMs. We also transfer the learning from data poor regions into data-rich regions. And this framework should be adaptable for upcoming missions in other bands. And this is this research has been done in the context of the Substar Snow project.
Thank you. We have time for questions.
Yeah, thanks, Caroline. I think that's a very interesting approach to go and to transfer this also to other frequencies. My question is, have you done a kind of validation in terms of the penetration bias, what you receive at the end? Is it kind of, did you have reference data to say, is it really compensated well or not?
In other bands? No, we are just, this last part is ongoing.
Yeah, no, I understand. But for X-band?
For X-band, we have, this is, of course, always we separate the training and the validation. So,
but the training, I understood, are the facies. It's not the height, right?
Both. So
okay, because this was not written.
The phases is the pretext. So you learn, you force the model to learn the characteristics of the snowpack.
Okay, so you had also, as a training, you had also kind of LiDAR data or whatever, height data.
Maybe I went too quick in this part.
Okay, sorry.
Yes, with what we do here, when we transfer the weights, is just, so this part, this is pretext part, what it does is it learns only the characteristics of the snow. And then we trained with our surface, so the penetration bias.
But how do you know how much penetration bias do you have?
We do model we have LiDAR data.
Ah, okay, here's your LiDAR. Okay,
yes,
that's what I was looking forward. Sorry,
yes.
Then I missed this part. Yes,
yes, exactly.
This is a question.
Then,
so you do it against LiDAR. This was a question.
Even with this good data, we cannot train a deep learning model because the data, this availability is not. It's not the amounts of data you need for a deep learning model.
I see. Okay.
So this is why we go for the pretext. So the problem, or what the model does is it learns the density of the snowpack in principle, and then translate this density to this understanding of by making the regression part. But already it doesn't start with random values as a normal, so as this model. So you give, it's like when you learn to, I don't know, do the calculus, and then you have to know mathematics first. So this is a little bit the idea. Yes.
Any other questions? No, you're sure. So then thank you again, and
Our next speaker is Franz Meyer, and he will speak about in situ data meets INSAR, validating the NISA Level 3 permafrost requirements.
Yes, back to the permafrost topic, and maybe one of the goals of this work is to highlight that NISA is going to provide very useful data for permafrost monitoring around the globe. There were some presentations about this earlier. And what we'll be talking about a little bit, what the requirement is for NISAR's permafrost observations, what sort of the goal variables are, and how we go about validating them, and showing you some preliminary results. We're still waiting for some final data over the summer, but so far the analysis that we've done looks really good to take away the main outcome of the talk. So I almost skipped the rest. So to remind you, NISAR is unique in the sense that it provides much more data per frame than you maybe are used to from traditional missions. So traditionally, data that you get are the level 0s and the level 1 data sets, the SOCs that a lot of you are working with. But NISAR is operationally processing also level 2 data sets. So you get geocoded SOCs, you get interferometric products and calibrated amplitude products. And then there's a suite of level 3 requirements that NISA has to meet. These products that are shown here at the level 3 end, they are not produced globally, but they will be produced over validation sites for the purpose of mission validation. These level 3 products include a bunch of the ones that are related to the ecosystems discipline. These are the ones here on top in the green colors. There are some that are related to the cryospheric community, so mostly related to sea ice and to glaciers and ice caps. And then the permafrost requirement is actually, even though it's a cryospheric discipline, it's hidden in the solid earth requirements. I'm going to show you in the next slide why this is the case. So briefly, talking about the permafrost requirement itself, it is quite a mouthful. This is sort of the spelling, the full written out requirement for permafrost. I'm going to briefly walk you through that so that you understand what the requirement means. So first, NISAR shall measure surface deformations in permafrost-affected regions, and it has to do this in certain ways. We'll see that we are aiming for a product that would be of 100-meter resolution. So when we validate the requirement, we validate at 100-meter resolution. The requirement is written for the snow-free months. So mostly what we are looking for is the seasonal subsidence that comes with the thawing out of excess ground ice in the permafrost regions. And we measure that over any 90-day period. So we are looking at basically the seasonal subsidence from the beginning of the thaw season to the end of the thaw season over that 90-day period. It needs to be able to measure that with a certain accuracy that is spelled out by this equation. You see it's a scale-dependent equation that accounts for atmospheric delay issues that scale with spatial scales. So we go from about 1 centimeter at the close scales to a requirement of about 4 to 5 centimeters at the large scales. And lastly, we need to meet this over 80% of the affected regions. So for all the data sets we're looking at, 80% of those have to meet these requirement specifications. And again, while physically a cryospheric science discipline, that's why it's also in this session, it is grouped within the solid earth requirements for the sake of NISAR. That's mostly because the discipline, the work we do, the processing we do in order to extract some surface displacements over permafrost sites is very similar to what you would do for looking at seismic or tectonic or volcanic signals. INSAR time series analysis in the end. And also the validation approaches are very similar to the ones used by the solid earth discipline. So in order to validate this requirement, we are doing two different things. One of them is we do a direct comparison of field measurements. So you see in this little figure on the side that we have validation sites in several places where we go out and we actually measure displacement in the field and compare them to displacements measured over 90 days from NISAR data. The second approach is to assess the quality of the data in places where we don't expect displacements. So for that, we identified non-deforming regions in the Arctic and do a structure function analysis in these areas to assess noise performance relative to the NISAR requirement. So firstly, for the field-based methods, we have 4 different validation sites in Alaska, on the Alaska North Slope. These are shown here on this view graph where they are located. They're all in the Alaska tundra. They are all in continuous permafrost sites with varying ground ice content. So there's a lot of variation between these sites in the seasonal displacements that we see. What's true for all of these sites is that if you look at the image on the right, is that there is a lot of variability, small-scale variability in the displacement that you see. Those are driven by variability in surface structure, ice content, and vegetation patterns in the region. So if you look at the Tasaki landscape that you see here, you would expect quite spatially variable displacements within short spatial scales. And in order to account for that spatial variability, when we try to validate a NISAR INSAR measurement made over a 100 by 100 meter pixel, we need enough field observations within that pixel to account for that spatial variability with enough statistical significance. So what we end up doing is within a 100 by 100 meter pixel, we define 3 transects in that pixel. And along each transect, we take, in this case, 51 measurements, 1 every 5 meters, to account and measure the spatial variability. So that dense sampling is needed to account for the spatial change. I'm going to show you in a few slides how much variability there actually is from one measurement to the next. And we picked 153 because sort of an order of magnitude analysis showed that these are enough measurements to get to validate the requirement with some margin. So at each of these 153 points, we end up taking 2 measurements, geodetic measurements, at the beginning of the thaw season, at the end of the thaw season. We use RTK GNSS to measure surface displacements using a reference station, a surveyed and stable benchmark reference station that's nearby. And we also do optical leveling as additional support as a very good measurement technique for relative elevations in the landscape. So these are the base measurements we need for validating the requirement, but we also take some ancillary data such as thaw depth measurements. We take some ice coring to understand what the ice richness is in the permafrost environment in order to be able to eventually relate the displacement measurements to physical permafrost parameters. And what's nice is that all of these data sets, both the geodetic data sets and the ancillary data sets, are available to the community through the NISAR validation database. So you should be able to leverage these data sets also to help you build your permafrost-related workflows. So this plot shows you our seasonal displacement measurements, field-based measurements from the last thaw season in 2025. What you see, this is for one of the sites, the ice cut site. What you see on the left are the 3 transects for this particular 100 by 100 meter pixel that we've analyzed. And the gray line is the GNSS difference, elevation difference from beginning to the end of the thaw season. And the black lines are the leveling-based measurements. And so luckily, we see that those are very similar to each other. And also in the scatter plot you see on the right-hand side, you see that both measurements match each other within some error. So we are confident in both of those observations. If you look back at the left-hand side, along these transects, you see this very strong variability that I mentioned earlier. So from one measurement to the next, you see there's quite a bit of difference in the seasonal thaw subsidence, which relates to variations in vegetation cover and ice content underneath. And so you see that all these numbers are negative, which makes sense. We have a subsidence there in the order of like 5 to 10 centimeters in this particular year, in an average for this pixel of 4 centimeters plus minus 0.1 centimeter. What we do then, once we have all these measurements made, we then form double differences. So we look at displacements between sites from the field and displacements between sites from INSAR, and then calculate the difference between those two. That gives us a scale-dependent estimate that we can then compare to the requirement. This is just to demonstrate how this would work. The blue marks are the field observations. The red line is the requirement. This is for a Sentinel-1 data set. In this case, we wouldn't quite meet it at the 80% level, but again, this is Sentinel-1, and it also hadn't, we didn't apply any corrections for solid earth tides, troposphere, or any other measurements. So we are awaiting the summer observations from NISAR in order to have the 90-day observations from space to compare our field measurements to. In the meantime, we have been out. Actually, the team is still out in the field right now. They sent me from Tulik some of the field shots this year. It's been a very complicated start to the field season. There was a lot of snow this winter in Alaska. It was quite cold. And we still have some snow in the area. There was also snowfall in the first few days. So they actually ended up staying a week longer in Tulik to be able to get all the measurements they need. But we were able to successfully take all the measurements we need for validation this spring. And to show you what the landscape looked like when they arrived after 2 days, because there was snowfall on the first day. So the left-hand side was what the field looked like then. But in the last few days, the snow had melted off and allowed for all the measurements we need. I should also have, they also had moose sightings, and they were haunted by a bear. So anyway, so that's the workflow one. So we are on a good track. We have the observations we need in the spring. We'll take some again in the fall, and then do our final assessment. For the approach 2, which is structure function analysis, here the goal is to look for non-deforming areas. So the workflow is we perform INSAR time series analysis to get the 90-day displacements. We then mask out or sort of identify all the stable ground. We've done this using optical data and geologic data to extract places where we expect very little displacement. And then form structure functions and compare the structure function results to the requirement. So this is what this looks like. This is again done for Sentinel-1 because we're waiting for the summer season data for NISAR this summer. So this is the seasonal subsidence, which then would give us structure functions that we can compare to the requirement. And this is, so what we do is we bin the structure functions in these bins. The lines that you see here, the green and red lines, they indicate the 80% level points. So 80% of all the structure function points are below these lines. And so here we would meet the requirement with the Sentinel-1 data set. And our first results from NISAR GAN-Ws are very encouraging that we also will meet that for NISAR. So while we don't fully have a 90-day interval yet, we have started looking at individual interferograms to see if we are on the right track in terms of meeting the requirements. And so overall, the Solid Earth team has done quite a bit of work here. I'm showing here work from Matt Pritchett from Cornell, who's done a broad analysis of sort of the residual noise in these structure functions on a global scale. One notable thing you should see, which I'm actually quite excited about, is we have higher errors in the Arctic. This is mostly due to ionospheric errors in the interferograms. So if you have interferograms that are not compensated, the error load in those is a little bit higher, which is both a problem and exciting. There's lots of additional data information in these data sets. But we could already show that if you apply the ionospheric correction, if you sort of look at the Arctic region, and I move forward, this is when the ionospheric correction is applied, the operationally processed ionospheric correction layers, and the errors go down quite a bit. It's quite exciting in the Russian Arctic. If you look at the Russian Arctic, you see that most of these areas now meet the requirement just fine. Similarly, in the the Canadian Arctic, the data sets look pretty good. There's some residual noise in the Alaska Arctic, but even there, we are very close to meeting the requirement for most data sets. So once we have the 90-day measurements available, we are pretty confident that we'll meet the requirement with good margin. Just to show you what this looks like, this is a interferogram, a single GUN-W interferogram over the North Slope of Alaska, where you see on the left the structure functions before ionospheric corrections. Here we have some large-scale signatures coming from the ionosphere, which makes us, in this case, not meet the requirement. But once the correction layers are applied, shown here on the right-hand side, we are well within the requirement margin, even with only a single interferogram. So we're quite excited with the way the data look and sort of just the phenomenal coverage that NICER provides for permafrost research that should really enable quite a bit of new discoveries in permafrost environments. We are ready to do the final validation for this summer. We have done the fieldwork already for the spring. We are waiting the fieldwork in the fall and then report back with our final results for the permafrost validation. And again, remember, all of the field observations are available to you, including the ancillary data that we've dropped into the validation database. So you can replicate our analysis and also tune your algorithms for understanding things like ice content, subsurface ice content. And with that, I end, and thank you for your attention.
Thank you, Franz. Are there questions from the audience?
Hello, beautiful presentation. I have two short questions, if that's okay. Firstly, in the global map of the permafrost validation, I see that there are no data points on the Svalbard region for the researchers who are, for us who are into Svalbard. I'm wondering if NISAR does not collect any data from that region?
No, so I should have mentioned that. This was from sort of an early release of data processed with a very specific processor version. There is going to be global coverage. There's going to be plenty of coverage of Svalbard using NISAR. Oh, it's too far north. Is it? Oh. Yeah, that is correct. Sorry, I forgot about that. So we are left-looking sensor.
Ooh.
Thank you, Paul. I saw that.
Oh.
So what's the cutoff latitude? 77 degrees. The instrument is a left-looking instrument, so it has more coverage in the Antarctic and less coverage in the Arctic.
Oh, thank you very much. So I suppose that would be a technological gap to cover in terms of coverage for and research in Svalbard. And another thing on in-field tests that you guys are performing in Alaska. Of course, it seems that if you can go back to the images, most of the region seems pretty flat, but there are mountains in the background. I'm not sure about the elevation, but would you have problems with the delayed snowfall and sort of the salt and pepper effect when we're dealing with?
Yeah, I mean, they're more complicated, like for any surface deformation case, they are more complicated environments and easier environments. In the mountains, we have snow cover, we have glaciers, you have other geophysical signals that you have to account for. You also may have permafrost in forested terrain. That's another thing to account for. So there's plenty of research that will be enabled by NISAR to look at sites where you have competing signals and how to best separate them. So I think it will open up a lot of possibilities for follow-on research once the data are available.
Are there any other questions? Yeah, there's one up there.
Yeah, just a quick question. Thank you, Franz, for the presentation. About your reference measurements here in the field, I'm wondering, what do you use as a reference point? So have you had some bedrock or something where you placed your GPS, or how did you do that?
Yeah, so the reference site we have, we drilled them deep into the permafrost to stabilize them, and we isolate them from the active layer around it using a pipe so that we don't have any frost jacking of the reference site itself. And we do cross measurements between the reference stations as well to sort of ensure that they are stable over time.
So also your leveling, you also started out then from the same kind of base point there.
Yes, yep.
Okay, understood.
Yep.
Thank you.
Then I think we move on to the next speaker. Thank you, Franz, again. And our next speaker and last speaker of this session is Bernd Scheuchel, and he will speak about the utilization of a virtual SAR constellation for ice sheet monitoring.
Thank you very much, and thank you also for those of you who held out and are still in the room. I was going to talk a bit more about grounding line mapping, but Eric sort of in his presentation took care of much of that. So there's a little bit of repeat, just as an introduction to the topic I want to address. So recently we published a paper on 30 years of grounding line mapping. And sort of the outcome is that Antarctic ice sheet lost 442 square kilometers of grounded ice. About 3/4 of the coastline is stable, but the quarter that is unstable, is really unstable. There is retreat up to 40 kilometers. These products are available at the National Snow and Ice Data Center. But what I wanted to really address in this talk is the data sources. So we have used data from all the satellites that we could get our hands on over the years, and sort of this refers to sort of a virtual constellation, and over some period there was a coordination effort that a number of people in this room have worked on. And coordination is a topic that has resurfaced, and there are two parallel efforts for coordinating acquisitions for scientific exploit. So Stephen Hawkins once wrote in a book that if you put an equation in a book, you lose half of your audience. I try this now, but don't worry, this is not the type of equation that I would lose you at. This is just sort of the spatial coverage of the various satellites that we have used with this grounding line. What's not represented here is the number of measurements that were available, and that has increased sort of ever since the Sentinel era started, really, because more and more satellite missions are using ongoing campaigns rather than one-off campaigns for a season, which was the case in the past. This is also sort of a historic slide. A number of the missions in the first row are no longer in orbit, but they certainly have earned their place in history. I just wanted to sort of focus a little bit. Sentinel-1 has become sort of a staple mission with respect to providing long-term consistent acquisitions in coastal Antarctica around the margins. This is in use for ice velocity measurements as well as grounding line measurements. And we have multiple measurements per year, which allowed us also to look at ice grounding zones, which represent sort of the short-term variation of the grounding line position. As part of sort of an international coordination meeting, the Canadian Space Agency said they could commit some resources for Antarctic acquisitions, not in the sort of spatial coverage that they used to do with RADARSAT-2, but we had an immediate idea how we could use RCM, their constellation, put it to good use and use its strength, which is sort of 4-day acquisition capability with 3 satellites, and slightly higher resolution for the strip map mode than Sentinel-1 offers with the 6 days, and focus it on fast glaciers where Sentinel-1 ever so often decorrelates. Sentinel-1 data is free and open. RCM data is freely accessible, but there is a registration process in place. And last but not least, we also used ICEYE data. We started out with a direct collaboration with the company on one site in Antarctica and one in Greenland. We found that quite successful, and we have since moved to work with NASA to acquire ICEYE data through a third-party purchase program. And that has the advantage that the data is more broadly available, but it's within sort of the use license, meaning it's available for NASA-funded researchers. But I believe ESA has sort of a third-party data acquisition program in place as well. So we use radar data double difference interferograms to isolate the vertical motion and use the tidal motion of the ice shelf to delineate the grounding line, which is an important boundary where ice meets the ocean. But let's focus on Thwaites Glacier for the rest of the talk. Here's an example of sort of the historic, the 30-year record of grounding lines, and the paper that we published with respect to specifically the ICEYE record. The red on the top right square is the grounding line ensemble, that's sort of the width of which informs the ice grounding zone. That width has an impact on modeling melt underneath the ice where ocean water has access to the ice all the way up to the grounding line and up to the upstream end of the grounding line. The fringe pattern that you see here, that's typical for grounding line measurement, and this is a very clean interferogram. But ever so often we saw specific fringe patterns that were upstream of the known grounding line, and we sort of started cataloging that, and some of them are in sync with the tide sort of fringe direction, and some are out of sync. And that we interpret as evidence that seawater has at times access past the grounding line and sort of also has an impact of melt on the glacier. But there is also evidence of subglacial water making its way to the grounding line from upstream. Thwaites Glacier, so subglacial water is a known entity in Antarctica, and it has historically been mapped with altimetry, both radar and LiDAR. And there have been, so Thwaites Glacier has a number of mapped subglacial lakes, and there were known discharge events in 2013 and 2017. So here is just an outline again. We have the flow direction. This is the main trunk of Thwaites. This is sort of the part of the grounding line that's really hard to get with any mission. So that's where we have an ICEYE daily stack collected for the last year, and the paper that I just showed was an older stack from a previous generation of ICEYE satellites. We have here the known and cataloged subglacial lakes and the ice flow direction. So this was ICEYE 1 day, and here what we saw was, oh, sorry, I should, somehow this, what I found when I processed 1 day was an interferogram pattern that had upstream, it's unfortunately not showing, but had upstream fringe pattern that was much more significant than the bullseyes that we happened to see in the previous version. And it turned out that phase unwrapping was not really an option for all the samples that I had. So what I did was processed double difference range offsets. And I'm going to show an animation here, what's happening. Keep your eye on this corner. So what we're seeing is red is sort of an uplift signal and blue is subsiding signal. We're seeing subglacial water making its way to the grounding line and sort of choosing a weird part. What you see in the background here is the topography of the bed. So there are even some ridges that need to be crossed, but we talked to some subglacial hydrology modelers and they told us that they haven't seen water moving this quickly. So there has not been evidence collected of water moving this quickly. So the anomaly itself lasts from January 5th to January 11th. So we have about 7 days where this water makes its way through that period. So that I wanted to show you the way I discovered this phenomenon and not necessarily go strict with the timeline, because what happened next was we are in the process also of working on validating NISAR data. And so my colleagues, so I presented this work at an internal meeting, and my colleague then told me, can you send me the map of the subglacial lakes again? Because I think I know what the cause for your phenomenon is. And I should say, we have been working with commissioning phase data that's uncalibrated. This is a low backscatter area, so it's not necessarily representative for the quality of the data. And the first available acquisition that we found was from November 5th. So this is the first interferogram. This is a very old processor version. There's more noise, then you will see an improvement later on thanks to the JPL team that allowed us or provided us with later processor version of the data, except for this one image. But I kept it in because you see there is some activity upstream of the grounding line. But if you keep an eye on this lake, so if I move forward, so we're now sort of with these 3 dates, and because we're only shifting by 1 date, sort of whatever happened between those 2 dates, and we're starting to see a signal on this lake, and I interpret this as this lake is starting to drain, and I move forward, sort of that signal intensifies, and then when we include sort of January 4, this is when we are about to see the ice signal downstream. And the next one, we have sort of a full connection of these 3 lakes and water essentially draining this oddly shaped drain pipe, if you want. And then there's sort of this goes on, and at some point later on, if you have looked closely, the fringe pattern changes direction. So we are starting to see this lake refilling. And you will see that this fizzles out, and sort of by the end of March, with very little signal. So this was a very short-lived event. And there is also evidence that none of the upstream lakes was involved in what happened. So the next thing we had available was the Sentinel-1 one-day mission, and thank you very much. And you turned it on just in the nick of time, because the first available acquisition for the area of interest was made on January 9. So there was a one-day interferogram January 9 and 10. And the mission itself is fantastic for grounding line measurements. And I will come back to this interferogram. So this is the first interferogram. We will discuss this a bit more in just a bit. So there are now 2 times 2 dates involved, and we shift forward and we see sort of things calm down relatively quickly, but we see sort of the 1-day changes on the lake using these interferograms. And I also have pairs up to the end of March. And again, sort of things calm down quite a bit. But what happens is, let's go back to this first interferogram. what we're seeing here, so this is a double difference interferogram. We take the difference of two interferograms that have the topography removed. And so essentially the motion component, the horizontal motion component, because we take the difference, should be 0 unless there was a change in the speed. So the way I interpret this is a mix of vertical motion from these bullseyes that we saw in the other data sets, as well as a response, a speed response from the glacier that's short-lived. And the way I outline this is sort of, I think the speed response is spatially confined. And if you look at the amplitude image, it's confined to an area where we have a highly crevassed region, so the ice is structurally weakened. And so there is ability for the ice to move a bit faster for a bit without dragging the rest of the glacier with it. So we have evidence of a speed response, but there is also evidence that this speed response is short-lived. I've started to look at went back to the eyesight data, looking at the azimuth offsets, which should not be sensitive to vertical motion. And they show that it's about a 4-day response with speed increase. It's just the offsets don't show quite as wide a range, because the phase, if I go back here, the phase sort of there are fewer fringes at the edges. So the azimuth offsets reach about here. I just didn't have time to include that in the presentation. So what do we see here? The eyesight daily observation, we were able for the first time to witness the large release of subglacial meltwater that lasted for about a week. And if you saw, there was uplift as well as subsidence, so that the surface relaxed after that. So if you had just the wrong dates chosen with your 12-day acquisition, you may have almost missed the entire event completely if you had one before, one after. We have nicer observations that cover a larger geographic area that showed, that identify the lake that started draining. And we have sort of, we narrowed the date down to about a 12-day period. There are no lakes upstream that appear to be involved. And the Sentinel one-day campaign, really, the large area coverage had the advantage that we see sort of this fringe pattern that is evidence that we have a speed response to this glacier. So I'm very excited, and this is something I want to wrap up and write up. So what's left for me is to make estimates on the water volumes that are involved. But I want to make the case that virtual interagency constellation is always an advantage. You will always gain information if you use data from multiple sensors. In this, I thought this was really a prime example to show that many missions help tell the full story, and no single mission can match the full information content. Commercial SAR data have a place in this. They will not replace agency missions, but they do augment. They have capabilities at the moment that no agency mission can match. Sort of daily observations, even if it's just for a postage stamp, is something that pushes research also in some. So in recent years, the Polar Space Dust group that some of us here were involved had a hiatus. It sort of, the coordination effort ended, but we had been talking to commercial vendors and to space agencies in the spirit of the PSDG experience and sort of with the lessons that we learned from that, to use the resources responsible, not ask for everything everywhere all the time. Well, I did ask once in a while, but knowing that this would never happen. So the real suggestions came with, I think, responsible use of the resources of the assets. There are now formal efforts underway from WMO as well as from ZEOS. My recommendation in this would be make sure to coordinate the coordinators. because two parallel efforts could also, just as well result in some unwanted conflict, not conflict, but unwanted sort of side effects. So at least that the two teams talk to each other. With that, I want to thank you and wish you a good evening.
Thank you, Bernd. Are there any questions?
Maybe more a comment. So this WMO follow-on from PSTG, this already started a few months ago. So it's called now TTC-POS. So Task Team for Cryospheric Polar Observations of whatever, I don't know. And there are space agencies from all of the world participating and contributing, as well as representatives from different scientific organizations, including ESA. I think NASA is also included from, I don't know who it is yet. But there is, on the WMO side, you find the participants and the team members. So if you are interested in this, this is the part. And then the second question, so it's a more technical one. For the Sentinel-1 part, how did you correct for the tides for Thwaites Glacier? Because that has, of course, an impact on this. Or did you just cut away all the ice?
We're not for this one, I'm not interested in the tides whatsoever. We are upstream, right, of the grounding line.
Okay.
Are there any other questions? Okay, I think that's not the case. Then I thank you, Bernd, again.
Thank you.
So it's almost the end of the day, but not quite. We still have a roundtable discussion now, where we have prepared a few slides, and I hope they can also be shown with the questions. The number of the presentation is 00. Thank you. Okay, Thomas, Bernd, you also want to? Okay. Okay, sure. Okay, so the first question would be, which sensor configurations and acquisition strategies are needed to improve products, so including ice sheets, sea ice, glaciers, snow parameters, etc. Are there any thoughts from the community?
Community first, I have some thoughts, but I'm happy to.
You're also
take
community.
second place. So then I'll take a stab at this. Jan already sort of hinted to looking at phase. We have also processed phase data for ice velocity, and that requires ascending and descending coverage. I know there are some sort of limitations in place that need to be overcome, but if there is, a political aspect to this, if it's a decision, then I would still want to place the request for ascending and descending coverage using Sentinel-1 on the map. If it's not possible, then it's not possible, but I'd want to mention it.
So maybe I would add on this. So I think for the future, we need a very good coordination between Sentinel and Roselle. So Roselle is coming in 3 years, so the preparations are still coming on. And I think, especially for Antarctica, we need a kind of coordination between both frequencies and also to learn how to combine L and C band together in order to maximize grounding line observations, fracturing, ice velocity, and all the other ice sheet parameters. And I think that's something what should be taken over also from the mission advisory groups, but maybe also from other parts of ESA to look into detail on that.
Yeah, so we started to work actually with biomass over Antarctica, which is also a very, very interesting frequency. You see features which you normally do not see. And what is really amazing, actually, you see a lot of more features when you use polarimetry, so not only one polarization. And actually, my recommendation is also to try to see what can you see in L-band using polarization diversity. So I would actually, I mean, probably it's counterintuitive because you do velocity estimation, so you would like to have one polarization potentially to have a time series, but I'm not sure really if polarization would not add a lot of things. So that's my recommendation to also to explore, right, the polarization diversity over Antarctica.
Speaking from our group, we were never opposed to polarization diversity. It was more a trade-off to say, this agency can provide this much data. It's either full coverage of Antarctica or, you know, it's partial coverage with polarimetric data. So it was more a trade-off rather than ruling out polarimetric data. So there's definite interest in this, and so it's a very good suggestion.
So maybe related to biomass and harmony, they are of course included. So for harmony, we are actually preparing for this and optimizing the acquisition plan. For biomass, there is already these different phases are running currently, and I think we cannot change this yet, but we look to, not only we, but also I think DTU and many others were looking to biomass data, and they are very, very useful because I think they provide us the third dimension towards the deep ice, and that's very interesting, which cannot be reached by C-band and L-band. So that's really a new experience what we are facing, and that's really, I think, a step forward. So any questions related to snow or one more on ice?
Thank you. I was wondering if a coordination between sensors would help in the case of inter-ice velocity retrieval, that one sensor does ascending passes, another descending, then you would like have a merged ice velocity product between frequencies, but you have two line of sight. So if like a complete coverage of ascending and descending with Sentinel alone is not possible, but with Roselle, you could coordinate.
This is a very good comment that it's needed, and Nuno is here to take over this comment and remember the next time. So we are currently revising this acquisition plan for Antarctica. For Greenland, I think we are quite happy. For Antarctica, there are some limitations due to the duty cycle of Sentinel-1. But I think ESA is doing the best actually to optimize this, and I hope this is getting better in the near future. So Nuno, you should remember.
Do you want to comment, Nuno? Or maybe not. ESA's always doing its best.
And our group, you know, the phase map that we have published, and that's our reference map, came together from a ragtag of sensors, you know, so and we had to combine, but this was born out of necessity. So if you can plan much better, it would be the much better option to coordinate that. Yes.
I knew it.
So the exercise that we start doing with Thomas, for the time being, it's an exercise in the sense that I was trying to place myself on Roselle is coming. So if we have to operate Sentinel-1 and Roselle in the same way, what does that mean for Sentinel-1? Okay. It means a lot for Sentinel-1, so we have to find trade-offs. So, but the exercise is there. The exercise can be published. The exercise could be shared, and we'll try to accommodate as much as possible what we can do with Sentinel-1. It's clear that Roselle is providing much more capacity than Sentinel-1, so the tendency will be from the community to say, do the same with Sentinel-1. But unfortunately, we cannot. Okay. Now, coming back to one of your points, so you say you want ascending, descending over all the margins, for example. Fine. Would you trade off resolution for that?
interferometric wide spot mode would be excellent. So IW. Extra wide for the interior would be very useful. Okay, so
One orbit direction only?
okay, okay, but that's maybe too detailed now to discuss it. Are there any other contributions to this issue? Otherwise, we go on with the next questions.
Yeah,
There
I
are
think
more
we have to
questions
go
come.
on because we are sharing like
Yeah.
the session also with the future yeah, mission session roundtable, so we don't have like too much time.
So the question is now, oh, okay, you can read it. The question is now, are there any dedicated acquisition campaigns such we had it for the Sentinel-1 one-day repeat acquisitions scientifically useful? I think yes, we saw a lot of examples on Monday and today. And should similar campaigns be planned for upcoming missions? So for cross-calibration of sensors, so if we have two platforms in space, or also to test for the short-term INSAR and learn more about this process. I think even, this is my opinion, even if we have only for half a year such a campaign with one day, this helps a lot because we are looking to a totally different type of processes. So short-term processes which we cannot capture by 6 days or 12 days repeat pass. And then, of course, we can fill gaps or also look into this and learn how to interpret the short-term one. So I think, in my opinion, such campaigns would be useful. And in the very near future, like Roselle, when the second platform is coming on board, something like this could be planned for Sentinel-1 next generation. In legacy mode, together with D or C, I don't know what is running at that time, if technically possible, would make sense. And maybe also for other missions which are available. So to use this opportunity, even if it's only for a very few months available. So what is your opinion on this?
Absolutely, if it's possible.
Thomas doesn't want to wait another 30 years.
I'm not sure if I will be here anymore.
I think that was the risk in doing this campaign. So we provide you that, so you want more. So fair enough. Don't forget that we did that campaign with Sentinel-1D, the force unit. The team was there. The team was trained. The experience was there. We knew the spacecraft. We knew everything. It won't be the case with Roselle. With Roselle, we'll probably suffer a lot, and probably those kind of requirements or a need will be put as a second order of priority. So you need to manage your expectations because we were super ready with a CND. With Roselle, it might be different.
But we will see in 3 or 4 years when the second platform is going in space.
Good. Thank
Any
you.
more comments? It's your chance to shape the future.
Just one comment from our side. We've also been looking at the one-day INSAR for glaciology, and yeah, as you've shown, like in particular for processes that aren't really well understood, like the subglacial hydrology, like it's been absolutely incredible. And I guess in terms of like what campaigns might be like helpful in the future is that, for example, you've shown the potential of the ISI INSAR, and so ISI products are available through the ESA third-party mission. However, the ground track repeat, which is the only one that's compatible for INSAR, is not available through the ESA third-party mission. And so for us, that's something that we would be really, really interested in having. Because yeah, we've had this excellent data. I mean, we're so thankful that it's the first time in 30 years. But it would be really incredible if we had some one-day data in, for example, a different part of the seasonal cycle. But yeah, so that's my comment. Thank you.
I can only recommend it, and the only thing I would say is that NASA and ESA find a way to coordinate in some ways that we're not creating conflict between agencies in site selection. Although the capabilities I think are now such that 3 people could order on Thwaites and not get in each other's hair. So
Okay, shall we move on to the next question?
Okay.
Yep.
If this is done or planned already from ESA's side or NASA, JPL side, to do this really, the data cross-calibration would be interesting. I'm not sure if this works. Is it possible to have kind of repeat paths? I mean, separate, right? Data, but to have at least the deformation maps or whatever calibrated against ROSE-L and NICER.
My understanding is that at the NASA ESA level, through the JPPG process, there's strong interest at ESA to be involved in the NICER validation campaigns over the next year or so in order to prepare for ROSE-L. I don't know if Nuno feels the same way, but that's what I've been told from the top level. So these kinds of things should happen. We could arrange for some polarimetric measurements over Antarctica if we take out some polarimetric measurements elsewhere so that we don't increase the data volume, which is fine with me, and do other experiments in the next couple of years in order to prepare for ROSE-L. We all want to see ROSE-L be perfect so that there's a continuity to the future. So yes, the answer is yes.
Yes,
and I can confirm it's our interest from ESA side too. So the understanding is correct.
No, we will write some slides on this and present it on Friday. Okay, then are there any ideas for Calval activities for upcoming SAR missions? That's ROSE-L, Harmony, Biomass, and so on. Is there a need for this, for the ice sheet parameter, or snow, or glaciers?
Yeah, I'm not sure. I think I said this already today. So what I really like is to have for biomass, what they're doing this, the GeoTree initiative, which means they're collecting ground sites, so super sites where they are collecting ground measurements, and they can be compared then with the heights, right, in biomass itself. So something like this would be really great for ice and snow, to have kind of super sites where, in principle, the ground measurements can be used also from everybody, and just to do some science on it. I'm not sure if this is available by the kind of Calval sites, but with available ground measurements to the community. Can be ground penetrating radar, can be ice cores, whatever, GPS, GNSS measurements, whatever.
So maybe just for information for the community, we were proposing in the ROSE-L MAC the Evans ice stream, what we presented on Monday during the Sentinel-1 session, as a kind of Calval site for ice velocity, grounding line, and other parameters, because we think it's a unique site with just a couple of advantages, and it's covered by most of the missions. So ROSE-L will be covered, Sentinel-1, it's already covering it, biomass data are there, Harmony together with Sentinel will be there, and maybe also commercial systems like ICI and others can jump on the train, and the plan is to install some GPS stations there, but also to take some shallow ice cores and snow information and ice information collected in order to look for penetration issues and learn more about the frequency dependence on that. So it's also a strong tidal component there. We have a strong grounding line there, which is very good to test the tidal correction, what is needed for correcting the ice velocity on ice shelves. So this is not guaranteed yet, but therefore we're asking the question of something like a site like this, which is staying there for 1 or 2 or 3 seasons, could be of valuable for polar regions. Move on. Okay. Then I think we have one more question. Okay, this is now more for data sets. So we heard in one of the other sessions that analysis-ready SAR or INSAR data sets for snow and ice monitoring are on the way. Are they useful for our applications? And if yes, so which are the products? Are they most needed for you, which makes your life a little bit easier? Or do we want to stick or still process from SLC data or PRI data types? And if we want to have such ARD products, which of the products would you like to see in the portfolio of ESA? What should be generated? Everybody wants to stay with SLCs? Or are there any? So Lucas?
Oh, level 2 interferograms would be nice if they are tailored for ice, for moving, varying motion across the scene. And yeah, normally if we talk about level 2 products globally, then this might not always be the case, so that the co-registration is adapted. I don't know how this is with NISA data. That was a question that I addressed Bernd earlier. Yeah, but
the cryosphere products are specially processed to meet your requirements. Yeah,
that's perfect.
But maybe something what makes it easier would be that all the SLC data could be co-registered to one primary master. So when you download it, they are already co-registered for repeat pass data. So is something like this in the queue, or is this useful for you, or do you want to make this processing step by your own? Yes. Co-registered to one main, so that all of the repeat pass data are co-registered to one supermaster stack. As good as this can be done. So is this useful, or is this... So for ice, for example, some people, so in polar regions, use also ice velocity maps in order to co-register. That's probably needed. Ice velocity in some regions are changing, like in West Antarctica and so on. Can this be done by a space agency, or is this then more on the level on service providers or research institutes to correct for this? Okay.
So maybe just to comment on this point, in my opinion, it would be great not to co-register on a single master, but maybe to define a kind of, I don't know, global grid given based on a given resolution, and then just to co-register just on a given grid, not really on a single master acquisition. Kind of just based on really, I would say, if we know that we have, I don't know, 10 meters resolution, just to define it in terms of latitude and longitude, and that will be great, I think.
There's one question up there. Answer.
Okay, I'm not an expert on snow and ice monitoring, but however, working with Sentinel data, I agree with you. The availability of already co-registered data could speed up in general the processing. So not only for ice and snow, but for the formation. This, in my opinion, could be very, very useful because could simplify the processing, speed up, and we can provide advanced product in more efficient and effective way. So also for other communities, not only in ICES, no? Yeah.
in the frame of Roselle, we are moving into having a co-SLC product, right? So we defining a global grid, and we try to co-register to some extent in that grid. But you, Bernd, I think that in NISR data, what you are not, you are mentioning level 2 products, which I think for NISR level 2 are geocoded SLC, right? So here we are doing in one direction for Roselle, and I have the impression that for NISR you are going in another direction.
It's slightly different. The geocoded SLC is a product. The cryo community, though, did not welcome that with open arms, I have to say. Correct me if I'm wrong, but I think that was sort of the sentiment.
Correct. And that's correct. They didn't want it because ice is moving so fast, and the geocoding would be somewhat meaningless after a while, which is also true for the range Doppler imagery. So it's not entirely clear why you'd want to co-register those.
I was more because the DM is changing in the entire periphery, and that would sort of displace the geocoding.
Everything is changing, so and features are moving, the DEM's changing, so
no, but
it's a very difficult environment.
To go back to level 2, sort of the interferograms that are geocoded but that are based on RSLCs, those are heaven. I don't want to spend my life, correlating SAR images.
Those are done at short time intervals, so
yeah.
So the DEM's not changing much between.
So here in NISR you are talking about co-register interferograms, and for the other mission we are talking about co-register SLC. So they are totally different.
Yeah.
And the question is, for this committee, should we go for something specific? Do you want one or the other? Because today we are going apparently in 2 different directions.
Different places, right? We have GSLCs elsewhere, and they are open loop. NISR has GSLCs in other places around the world that are not moving like this, and they are not data-driven co-registered because they are pretty close, as you'll see in Haresh's talk tomorrow, but probably do need some fine registration ultimately, and we chose not to do that. And I think the Opera program, which is doing Sentinel GSLCs, is also not choosing data-driven because there's issues with that when data's missing and that kind of thing. So, but over the cryosphere, we chose a different path at their recommendation because of the special circumstances. Did you want to say something?
Thank you.
Just a quick comment to like maybe if we go application specific for the cryosphere, a stack of at least 3 scenes might be quite usable, as we've seen in a lot of presentations. We often do double differences, so just having 2 co-registered, then you basically, if you want to have them in a stack, you do the co-registration again on your own. But it doesn't have to be very long because the scenes decorrelate after a while. So, but thinking a little bit longer than 2 scenes would be usable, I guess.
No, Thomas, we need to stop now. I think it's very fair for the others.
Okay.
Well, people are still here. Nobody is standing up. So if you start now, I think it's fine. You can.
Macht eigentlich keinen Sinn. Okay, yeah, so then the other slides needs to be uploaded. I'm not sure. Is there somebody? We have uploaded it, but somebody needs to make them on. The seed questions. Yeah, when it's... These are the seed questions for the future mission, because they don't know which one. Yeah, but if you don't have the questions, I don't know what to start.
Maybe these people weren't even in the morning session.
Yeah, therefore. So yeah, I'm very sorry. So probably you've been not in the morning, or who has been in the morning session for the future mission? Please raise your hands. Oh, great. I'm very happy. At least some of you. Great. Perfect. Okay, yeah, we have the last 10 minutes, right? To talk a little bit about it. So I'm very sorry because the seat question is still not displayed. We had 3 questions actually. This I don't know. Ah, yes, you have it. Perfect. Great. Yeah, thank you. That's great. Ah, great. Perfect. Thank you very much. So the first question was a little bit new mission capability have been presented actually in the morning. And the question was a little bit, what are the application behind? Because most of them were more talking about innovation, technology, and it was not clear really for what kind of application. For example, the geostationary along track parts or let's say mission concept that has been presented. This was a question, what kind of applications are behind and who would need these ones? So this was our first questions. I'm just reading all of them and then you can comment on which one you would like. And how much better, the second question, how much better is the performance from this system, from the science or from the science-driven mission? Because we had also some missions which were, I mean, very innovative and probably for certain areas only capable to, I mean, to cover it. And the question is, what is the difference for a mission that we have anyway from ESA and NASA? The third question was, what is still missing to complete the fleet of the space mission in terms of spatial and temporal coverage? Could be also in terms of polarization or in terms of line of sight vector diversity. So any kind of questions. I don't know, do you like to add something? Yes, sorry. So do you have some comments to one of these questions? Yeah.
So with respect to new capabilities, what surprised me is we look at the new data set. When we first got our hands on eyesight data, for example, we thought, what is it going to help us? And then we had sort of daily observations for one glacier, and we started seeing phenomena that we didn't see in the past. So I think some of these we don't know what it's good for, but in terms of is it worth trying, I would say absolutely. And on the third question, coordination and access to data is sort of the prime comment that I would give in terms of if it's not already global coverage, then it should be coordinated between the missions, and access to data should be guaranteed and for the long term.
Okay, I think that is a good idea. Basically, you push a technology that is something that is not very usual, but then you have data and you can see what application comes. It's difficult to invent unless you have the data. Also, interferometry was born because by chance there was a possibility to have interferometry, some interferometric passes, not because you planned the mission with interferometry to work in the other way. And but I wish to remember this morning there was some statement about coherence chain detection. That is a very well-known technique, but with a long revisit is not so profitable because you have so many changes that it's like having no changes at all. But if you bring it at one-day revisit, I remember, they say this could be a new application, but of course, maybe also market-oriented, but unless you have the data, the market will not be able to design mission for that because these small missions are very market-oriented. So I think that ESA or space companies should do something to push in short revisit mission in order to find applications that the market is not ready to play now.
So Andrea is taking a very technology-driven approach to it, and I think that's an important thing to be done. I have lived my last 15 years doing a science-driven approach and being asked, what is enough? And with the cryo teams in particular, who are in this room, nothing is ever enough for them. And 1 hour repeat, vector diversity, 1 hour revisit, it's all very expensive. And I think at some level the winter might be coming for a lot of us. We might not be able to continue with the budgets that even in Europe, which has an incredible program, the world is changing geopolitically. So things may change for all of us, and we may actually need to think a little bit more from a science-driven approach. So since we didn't see too much in the applications this morning and what is really needed as opposed to what would be desired, I thought it would be good to ask these questions here. But anyway, Bernd, you had a...
Yes.
I just wanted to bring back to the table, the commercial sector has some capabilities where they can react fast to changes and run sort of test cases with hardware that's developed in short order. It may not be sort of the ice sheet wide coverage or sort of continent wide coverage that one wants, but to test some technologies, that would be a platform where an agency-driven mission would probably not necessarily.
But you don't have the frequency diversity that you need, right?
Not at the moment, that's correct.
I think, but something like this we have already with the Earth Explorer missions, right? So where we can, in principle, do kind of suggestions of new missions, new technology, whatever, and then to place it. Sorry?
What's the turnaround for an Earth Explorer mission?
I think it's every 3 years, or? Yeah, okay. Every 3 years. New missions are proposed, and then there's a selection process, but it's great. I mean, biomass is kind of an explorer mission, right? It's great. It has been as an experiment launch because nobody knows what P-band is doing. So it's great. So in principle, these kind of facilities we have to have this technology driven, probably also science driven, depending on which sites you go, and to make some experiments. I think that's very great.
But new missions are selected totally different. So in principle, we have also a science-driven approach, not something like the third questions that ESA is looking to the sky and saying, okay, we are missing another band. So in principle, we have a kind of application or a parameter to observe, and then we have to write mission requirements, then we are looking for the right sensor doing this stuff, and then we are going through all this selection process, and one at the end of these many ideas will win. So that's a totally different approach.
So let me make another comment. There are Earth Explorer missions that has a very long time from design to the implementation. The biomass took 20 years, okay? So this is really out of the present way the world change fast. But indeed, ESA has also another set of missions that are the Scout program that are very fast to the market because this is a 3-year program. So there should be really mature and they should run fast. The problem is that the Scout, it's a little small money for a synthetic aperture radar. So either we have very expensive mission in very long term, or we have a cheap mission in too short term for the SAR community. And I think that we could end in a recommendation of some intermediate case that is not an Explorer that is full price, long term, but is something that is faster, but maybe a small satellite, not as small as a CubeSat, but a little more that can prove some demonstration of some new application or principle.
Yeah, good idea. Some other comments? There's one on top.
on this topic, maybe it could be interesting to see an agency-driven, fleet-style commercial mission. Like we are seeing now the direction of science and commercial kind of drifting right now. Like on one side, we're using like this long band mission and science, but on the other hand, the commercial is going in another direction. And we saw also today a lot of very interesting science, but it's get kept by the money that cost to buy the data. And now, yes, there are open data policy, but in the future this could change. And I think maybe this also will answer a medium-term request for a mission where we can actually have an agency that can provide this kind of data for free or on demand for science. And that could help also to develop new application. We were talking about this just before, that can be then found is a technology first, but it's maybe the first time that we can see that there is a market rather than just like first the science, that then the market come afterward. So that can be maybe an idea for the future.
Yes, also good idea.
Just a little things here on behalf of ISA. On the question number one, something that hasn't been mentioned, but it's probably useful, is the science strategy. So ISA is releasing the ISA EO science strategy, which is answering the first question. So it's something that, I invite everybody to read. It has been released 2 years ago. And something else, it's a new program element, rather new, it's called NEOMI, New Earth Observation Mission Idea. That's a really popular program element that is trying to also address some of those questions. So it's for emerging scientists that they have like some ideas. They really do not know how to maybe develop a mission and so on. And we are guiding them towards building this concept for a future mission. So this is a very popular program element. It's small, but I think it's worth mentioning within this context.
So you think these questions are all answered for ESA? Is that what you're saying?
No, absolutely not. That's why we have these program elements. So the science strategy defines questions, but there are like hundreds of those, right? So there are the gaps. So they're definitely not answered, and that's why we have this conference.
I see. And are they prioritized in the strategy?
No, we have science teams. So what we did is that we categorize them, but do not. There is no priority. It's wrong, so, I think, my opinion, to have priorities.
So it's a little like the U.S. Decadal Survey in defining the science strategy for NASA for the next 10 years, that kind of thing?
That's right.
Yeah. Bernd.
I had one comment, sort of going back to the virtual constellation, and I want to say NISA gave an example for that, where you assess what sort of the global constellation can provide. So you have a set of science requirements. You rely on the global community to fulfill some of those, and you focus your mission, which could bring down cost and or give you opportunity to focus on other science sort of requirements. And NISA did that when they said, well, we go left looking because the Arctic is covered by multiple agency missions already. So US researchers have access to SAR data in the Arctic. So that would be one example, but that could be sort of become a model in other disciplines, so that you don't have to fulfill all your science requirements that are identified in the Decadal Survey, for example.
Right, and maybe you're saying this to try to get me to talk about the ICGS and that kind of thing, but there has been for the last 6 years or so a group called the International Coordination of SAR Missions Group or something like that, which involves many space agencies that's been trying to assemble all the requirements, something like the Decadal Survey and ESA strategy requirements, and tabulate what all the missions are doing around the world and what's there, what's missing, what's redundant, to try to come up with coordination strategies. We had talked about doing something similar to the PSTG, but I guess that's already covered by WMO now. So this is a vehicle. This group is actually in the process of being transformed into a CEOS working group, and that will then have agency level mandate for all the agencies to do that kind of coordination.
I want to bring something up that's slightly different. So the HAPS situation. I mean, there was this HAPS for ESA initiatives for a while, and it's also something we're interested in pursuing. I think it's a nice opportunity to look into a couple of different applications, revisit times, very short revisit times, quasi-geostationary cases. Also, of course, not for like a large science community with a long perspective having that data, but just to explore certain things in a cheaper way than having even a scout mission. So it's not a recommendation, rather a question. Are there plans to pursue that at ESA or like push that further with campaigning or like supporting initiatives in that direction?
Well, yes, there are, but at the moment there are no flying platforms available that have shown like reliability. But we are approaching the topic from ESA, and there will also be another workshop in likely 28. So we are still continuing, but waiting for platforms to be up and running and reliable. And then they might be integrated, but it's still some time or like a longer way to go.
Future mission.
Yes, yeah, exactly.
Thanks.
Any other comments? Yeah, well, last question, what's missing? We've got, well, we don't have a geosynchronous SAR yet. That's missing, if that's considered important. Yeah. Do we have a need for more missions beyond P-band, L-band, S-band with partially, C-band, X-band? All of them fully polarimetric? Sure. What about more airborne programs or campaigns that would help with the technology push? Do we think we have enough? Nobody cares about airborne. Okay.
Well, I believe still bistatic capabilities for airborne are not enough at the moment. I think they are on its way to be developed at DLR or UAV based, what we saw from Gamma, but I think they are not around at the moment and are very important also for Calva, for Harmony, for instance, or if we continue further for Duza companion satellite, which we are also started studying recently.
You're talking about bistatic airborne campaigns to support the spaceborne. Yeah, okay. What's your dream mission that doesn't exist around Earth? I guess ESA's doing a good job.
High resolution, supermetric, multi-baseline geographic acquisitions.
Well, that gets back to my original point. Do we need it? What do we need it for?
Maybe then I have a short comment. And
Yeah.
It's not really missing because it is in the new space. It's sort of coming up like orbits that are not full days, so that we have like varying times of day that we acquire with SAR when we get different atmosphere, differences, but we could also observe some nice effects. So
Orbits that are not what?
like
sub-daily?
Yeah,
Sub-daily?
so yeah, sub-daily orbits, but not necessarily 1 hour repeats or so, but so that they don't line up always at the same time of day. Say.
Yeah.
So this is kind of a byproduct of the new space, how they did their mid-inclined orbits, I think, but they did it for a different purpose, right? To increase revisit, but I think there are opportunities there. Yeah.
Yeah, INSAR sub-daily, yeah. Okay. That's good, okay. I think we can release you. Thank you so much for attending.